8. Network security. For the first few decades of their existence, computer networks were primarily used by university researchers for sending email and by corporate employees for sharing printers. Under these conditions, security did not get a lot of attention. But now, as millions of ordinary citizens are using networks for banking, shopping, and filing their tax returns, and weakness after weakness has been found, network security has become a problem of massive proportions. In this chapter, we will study network security from several angles, point out numerous pitfalls, and discuss many algorithms and protocols for making networks more secure. Security is a broad topic and covers a multitude of sins. In its simplest form, it is concerned with making sure that nosy people cannot read, or worse yet, secretly modify messages intended for other recipients. It is concerned with people trying to access remote services that they are not authorized to use. It also deals with ways to tell whether that message purportedly from the eyes pay by Friday or else is really from the eyes and not from the Mayfair. Security also deals with the problems of legitimate messages being captured and replayed, and with people later trying to deny that they sent certain messages. Most security problems are intentionally caused by malicious people trying to gain some benefit, get attention, or harm someone. A few of the most common perpetrators are listed in Figure 8 to 1. It should be clear from this list that making a network secure involves a lot more than just keeping it free of programming errors. It involves outsmarting often intelligent, dedicated, and sometimes well-funded adversaries. It should also be clear that measures that will thwart casual attackers will have little impact on the serious ones. Police records show that the most damaging attacks are not perpetrated by outsiders tapping a phone line, but by insiders bearing a grudge. Security systems should be designed accordingly. Adversary goal: student to have fun snooping on people's email cracker, to test out someone's security system, steal data. Sales rep to claim to represent all of Europe, not just Andorra Corporation, to discover a competitor's strategic marketing plan. Ex-employee to get revenge for being fired. Accountant to embezzle money from a company stockbroker, to deny a promise made to a customer by email. Identity thief to steal credit card numbers for sale. Government to learn an enemy's military or industrial secrets. Terrorist to steal biological warfare secrets. Figure 8 to 1. Some people who may cause security problems, and why. Network security problems can be divided roughly into 4 closely intertwined areas: secrecy, authentication, non-repudiation, and integrity control. Secrecy, also called confidentiality, has to do with keeping information out of the grubby little hands of unauthorized users. This is what usually comes to mind when people think about network security. Authentication deals with determining whom you are talking to before revealing sensitive information or entering into a business deal. Non-repudiation deals with signatures. How do you prove that your customer really placed an electronic order for 10 million left-handed doohickeys at 89 cents each when he later claims the price was 69 cents? Or maybe he claims he never placed any order. Finally, integrity control has to do with how you can be sure that a message you received was really the one sent and not something that a malicious adversary modified in transit or concocted. All these issues, secrecy, authentication, non-repudiation, and integrity control, occur in traditional systems too, but with some significant differences. Integrity and secrecy are achieved by using registered mail and locking documents up. Robbing the mail train is harder now than it was in Jesse James' day. Also, people can usually tell the difference between an original paper document and a photocopy, and it often matters to them. As a test, make a photocopy of a valid check. Try cashing the original check at your bank on Monday. Now try cashing the photocopy of the check on Tuesday. Observe the difference in the bank's behavior. With electronic checks, the original and the copy are indistinguishable. It may take a while for banks to learn how to handle this. People authenticate other people by various means, including recognizing their faces, voices, and handwriting. Proof of signing is handled by signatures on letterhead paper, raised seals, and so on. Tampering can usually be detected by handwriting, ink, and paper experts. None of these options are available electronically. Clearly, other solutions are needed. Before getting into the solutions themselves, it is worth spending a few moments considering where in the protocol stack network security belongs. There is probably no one single place. Every layer has something to contribute. In the physical layer, wiretapping can be foiled by enclosing transmission lines, or better yet, optical fibers, in sealed tubes containing an inert gas at high pressure. Any attempt to drill into a tube will release some gas, reducing the pressure and triggering an alarm. Some military systems use this technique. In the data link layer, packets on a point-to-point line can be encrypted as they leave one machine and decrypted as they enter another. All the details can be handled in the data link layer, with higher layers oblivious to what is going on. This solution breaks down when packets have to traverse multiple routers. However, because packets have to be decrypted at each router, leaving them vulnerable to attacks from within the router. Also, it does not allow some sessions to be protected, for instance, those involving online purchases by credit card, and others not. Nevertheless, link encryption, as this method is called, can be added to any network easily, and is often useful. In the network layer, firewalls can be installed to keep good packets and bad packets out. IP security also functions in this layer. In the transport layer, entire connections can be encrypted end-to-end, that is, process to process. For maximum security, end-to-end security is required. Finally, issues such as user authentication and non-repudiation can only be handled in the application layer. Since security does not fit neatly into any layer, it does not fit into any chapter of this book. For this reason, it rates its own chapter. While this chapter is long, technical, and essential, it is also quasi-irrelevant for the moment. It is well documented that most security failures at banks, for example, are due to lax security procedures and incompetent employees, numerous implementation bugs that enable remote break-ins by unauthorized users, and so-called social engineering attacks, where customers are tricked into revealing their account details. All of these security problems are more prevalent than clever criminals tapping phone lines and then decoding encrypted messages. If a person can walk into a random branch of a bank with an ATM slip he found on the street claiming to have forgotten his PIN and get a new one on the spot in the name of good customer relations, all the cryptography in the world will not prevent abuse. In this respect, Ross Anderson's 2008 book is a real eye-opener, as it documents hundreds of examples of security failures in numerous industries, nearly all of them due to what might politely be called sloppy business practices, or inattention to security. Nevertheless, the technical foundation on which e-commerce is built when all of these other factors are done well is cryptography. Except for physical layer security, nearly all network security is based on cryptographic principles. For this reason, we will begin our study of security by examining cryptography in some detail. In Secretary 8.1, we will look at some of the basic principles. In Secretary 8.2.2 through Secretary 8.2.5, we will examine some of the fundamental algorithms and data structures used in cryptography. Then we will examine in detail how these concepts can be used to achieve security in networks. We will conclude with some brief thoughts about technology and society. Before starting, one last thought is in order: what is not covered? We have tried to focus on networking issues, rather than operating system and application issues, although the line is often hard to draw. For example, there is nothing here about user authentication using biometrics, password security, buffer overflow attacks, Trojan horses, login spoofing, code injection such as cross-site scripting, viruses, worms, and the like. All of these topics are covered at length in Chapter 9 of Modern Operating Systems, Tanenbaum, 2007. The interested reader is referred to that book for the system's aspects of security. Now let us begin our journey. 8.1 Cryptography. Cryptography comes from the Greek words for secret writing. It has a long and colorful history going back thousands of years. In this section, we will just sketch some of the highlights as background information for what follows. For a complete history of cryptography, Kant's 1995 book is recommended reading. For a comprehensive treatment of modern security and cryptographic algorithms, protocols, and applications, and related material, see Kaufman and others, 2002. For a more mathematical approach, see Stinson, 2002. For a less mathematical approach, see Burnett and Payne, 2001. Professionals make a distinction between ciphers and codes. A cipher is a character-for-character or bit-for-bit transformation, without regard to the linguistic structure of the message. In contrast, a code replaces one word with another word or symbol. Codes are not used anymore, although they have a glorious history. The most successful code ever devised was used by the US Armed Forces during World War II in the Pacific. They simply had Navajo Indians talking to each other using specific Navajo words for military terms. For example, Chedagahinalt Sadi, literally, tortoise killer, for anti-tank weapon. The Navajo language is highly tonal, exceedingly complex, and has no written form. And not a single person in Japan knew anything about it. In September 1945, the San Diego Union described the code by saying for 3 years, wherever the Marines landed, the Japanese got an earful of strange gurgling noises interspersed with other sounds resembling the call of a Tibetan monk and the sound of a hot water bottle being emptied. The Japanese never broke the code and many Navajo code talkers were awarded high military honors for extraordinary service and bravery. The fact that the US broke the Japanese code, but the Japanese never broke the Navajo code played a crucial role in the American victories in the Pacific. 8.1.1 Introduction to Cryptography. Historically, 4 groups of people have used and contributed to the art of cryptography: the military, the diplomatic corps, diarists, and lovers. Of these, the military has had the most important role, and has shaped the field over the centuries. Within military organizations, the messages to be encrypted have traditionally been given to poorly paid, low-level code clerks for encryption and transmission. The sheer volume of messages prevented this work from being done by a few elite specialists. Until the advent of computers, one of the main constraints on cryptography had been the ability of the code clerk to perform the necessary transformations, often on a battlefield with little equipment. An additional constraint has been the difficulty in switching over quickly from one cryptographic method to another one, since this entails retraining a large number of people. However, the danger of a code clerk being captured by the enemy has made it essential to be able to change the cryptographic method instantly if need be. These conflicting requirements have given rise to the model of figure 822. Encryption method. Passive intruder just listens. Active intruder can alter messages. Plain text. Plain text. Decryption method. Encryption key. Decryption key. Cipher text. C=EC. Intruder. Figure 822. The encryption model for a symmetric key cipher. The messages to be encrypted, known as the plain text, are transformed by a function that is parameterized by a key. The output of the encryption process, known as the cipher text, is then transmitted, often by messenger or radio. We assume that the enemy, or intruder, hears and accurately copies down the complete cipher text. However, unlike the intended recipient, he does not know what the decryption key is, and so cannot decrypt the cipher text easily. Sometimes the intruder can not only listen to the communication channel, passive intruder, but can also record messages and play them back later, inject his own messages, or modify legitimate messages before they get to the receiver, active intruder. The art of breaking ciphers, known as cryptanalysis, and the art of devising them, cryptography, are collectively known as cryptology. It will often be useful to have a notation for relating plain text, cipher text, and keys. We will use C=EC P to mean that the encryption of the plain text P using key K gives the cipher text C. Similarly, P=DK, C represents the decryption of C to get the plain text again. It then follows that DK, EC, P equals P. This notation suggests that E and D are just mathematical functions, which they are. The only tricky part is that both are functions of two parameters, and we have written one of the parameters, the key, as a subscript, rather than as an argument, to distinguish it from the message. A fundamental rule of cryptography is that one must assume that the cryptanalyst knows the methods used for encryption and decryption. In other words, the cryptanalyst knows how the encryption method, E, and decryption, D, of figure 822 work in detail. The amount of effort necessary to invent, test, and install a new algorithm every time the old method is compromised, or thought to be compromised, has always made it impractical to keep the encryption algorithm secret. Thinking it is secret, when it is not, does more harm than good. This is where the key enters. The key consists of a, relatively, short string that selects one of many potential encryptions. In contrast to the general method, which may only be changed every few years, the key can be changed as often as required. Thus, our basic model is a stable and publicly known general method parameterized by a secret and easily changed key. The idea that the cryptanalyst knows the algorithms, and that the secrecy lies exclusively in the keys, is called Kerckhoffs's principle, named after the Flemish military cryptographer August Kerckhoff, who first stated it in 1883. Kerckhoff, 1883. Thus, we have Kerckhoffs's principle: all algorithms must be public, only the keys are secret. The non-secrecy of the algorithm cannot be emphasized enough. Trying to keep the algorithm secret, known in the trader's security by obscurity, never works. Also, by publicizing the algorithm, the cryptographer gets free consulting from a large number of academic cryptologists eager to break the system, so they can publish papers demonstrating how smart they are. If many experts have tried to break the algorithm for a long time after its publication and no one has succeeded, it is probably pretty solid. Since the real secrecy is in the key, its length is a major design issue. Consider a simple combination lock. The general principle is that you enter digits in sequence. Everyone knows this, but the key is secret. A key length of 2 digits means that there are 100 possibilities. A key length of 3 digits means 1000 possibilities, and a key length of 6 digits means 1,000,000. The longer the key, the higher the work factor the cryptanalyst has to deal with. The work factor for breaking the system by exhaustive search of the key space is exponential in the key length. Secrecy comes from having a strong, but public, algorithm and a long key. To prevent your kid brother from reading your email, 64-bit keys will do. For routine commercial use, at least 128 bits should be used. To keep major governments at bay, keys of at least 256 bits, preferably more, are needed. From the cryptanalyst's point of view, the cryptanalysis problem has 3 principal variations. When he has a quantity of ciphertext and no plain text, he is confronted with a ciphertext-only problem. The cryptograms that appear in the puzzle section of newspapers pose this kind of problem. When the cryptanalyst has some matched ciphertext and plaintext, the problem is called the known plaintext problem. Finally, when the cryptanalyst has the ability to encrypt pieces of plaintext of his own choosing, we have the chosen plaintext problem. Newspaper cryptograms could be broken trivially if the cryptanalyst were allowed to ask such questions as what is the encryption of Abgeftigitl? Novices in the cryptography business often assume that if a cipher can withstand a ciphertext-only attack, it is secure. This assumption is very naive. In many cases, the cryptanalyst can make a good guess at parts of the plaintext. For example, the first thing many computers say when you call them up is login. Equipped with some matched plaintext ciphertext pairs, the cryptanalyst's job becomes much easier. To achieve security, the cryptographer should be conservative and make sure that the system is unbreakable, even if his opponent can encrypt arbitrary amounts of chosen plaintext. Encryption methods have historically been divided into 2 categories: substitution ciphers and transposition ciphers. We will now deal with each of these briefly as background information for modern cryptography. 8.1.2 Substitution ciphers. In a substitution cipher, each letter or group of letters is replaced by another letter or group of letters to disguise it. One of the oldest known ciphers is the Caesar cipher, attributed to Julius Caesar. With this method, A becomes D, B becomes E, C becomes F, and Z becomes C. For example, attack becomes DWWDFN. In our examples, plain text will be given in lowercase letters, and ciphertext in uppercase letters. A slight generalization of the Caesar cipher allows the ciphertext alphabet to be shifted by K letters, instead of always 3. In this case, K becomes a key to the general method of circularly shifted alphabets. The Caesar cipher may have fooled Pompey, but it has not fooled anyone since. The next improvement is to have each of the symbols in the plain text, say, the 26 letters for simplicity, map onto some other letter. For example, A B C D E F G H I J K L M N O P Q R S T U V W X Y Z Q W E R T Y U I O P A S D F G H J K L Z X C V B N M. The general system of symbol for symbol substitution is called a monoalphabetic substitution cipher, with the key being the 26-letter string corresponding to the full alphabet. For the key just given, the plain text attack would be transformed into the ciphertext QZZQEA. At first glance this might appear to be a safe system, because although the cryptanalyst knows the general system, letter-for-letter substitution, he does not know which of the 26, 4x 1026 possible keys is in use. In contrast with the Caesar cipher, trying all of them is not a promising approach. Even at 1 sec per solution, a million computer chips working in parallel would take 10,000 years to try all the keys. Nevertheless, given a surprisingly small amount of ciphertext, the cipher can be broken easily. The basic attack takes advantage of the statistical properties of natural languages. In English, for example, E is the most common letter, followed by T, O, N, I, etc. The most common two-letter combinations, or digrams, are TH, IN, RE, and AN. The most common three-letter combinations, or trigrams, are the, ein, and un. A cryptanalyst trying to break a monoalphabetic cipher would start out by counting the relative frequencies of all letters in the ciphertext. Then he might tentatively assign the most common one to E and the next most common one to T. He would then look at trigrams to find a common one of the form TZ, which strongly suggests that X is H. Similarly, if the pattern TH it occurs frequently, the Y probably stands for A. With this information, he can look for a frequently occurring trigram of the form ZW, which is most likely AN. By making guesses at common letters, digrams, and trigrams and knowing about likely patterns of vowels and consonants, the cryptanalyst builds up a tentative plain text, letter by letter. Another approach is to guess a probable word or phrase. For example, consider the following ciphertext from an accounting firm, blocked into groups of 5 characters. A likely word in a message from an accounting firm is financial. Using our knowledge that financial has a repeated letter, I, with 4 other letters between their occurrences, we look for repeated letters in the ciphertext at this spacing. We find 12 hits at position 6, 15, 27, 31, 42, 48, 56, 66, 70, 71, 76, and 82. However, only 2 of these, 31 and 42, have the next letter, corresponding to N in the plain text, repeated in the proper place. Of these 2, only 31 also has the A correctly positioned, so we know that financial begins at position 30. From this point on, deducing the key is easy by using the frequency statistics for English text and looking for nearly complete words to finish off 8.1.3 transposition cipher substitution ciphers preserve the order of the plain text symbols but disguise them. Transposition ciphers, in contrast, reorder the letters, but do not disguise them. Figure 823 depicts a common transposition cipher, the Kalama transposition. The cipher is keyed by a word or phrase not containing any repeated letters. In this example, megabuck is the key. The purpose of the key is to order the columns, with column 1 being under the key letter closest to the start of the alphabet, and so on. The plain text is written horizontally, in rows, padded to fill the matrix if need be. The ciphertext is read out by columns, starting with the column whose key letter is the lowest. MEGABUCK 7, 4, 5, 1, 2, 8, 3, 6 PLERSETR plain text please transfer an Emiliandala Stoma Swiss bank account 6 Twitwo ciphertext Afelsksosaloyatusktl momentus ilintransoud Pila Bo Rerix Berenes FERONEMILLIONDOLSTOMYSWISBRNKSCCOUNTSIXGWOTWOABCD figure 823. A transposition cipher. To break a transposition cipher, the cryptanalyst must first be aware that he is dealing with a transposition cipher. By looking at the frequency of E, T, A, O, I, N, etc., it is easy to see if they fit the normal pattern for plain text. If so, the cipher is clearly a transposition cipher, because in such a cipher every letter represents itself, keeping the frequency distribution intact. The next step is to make a guess at the number of columns. In many cases, a probable word or phrase may be guessed at from the context. For example, suppose that our cryptanalyst suspects that the plaintext phrase $1,000,000 occurs somewhere in the message. Observe that digrams MO, IL, lines, LA, I, and OS occur in the ciphertext as a result of this phrase wrapping around. The ciphertext letter O follows the ciphertext letter M, that is, they are vertically adjacent in column 4, because they are separated in the probable phrase by a distance equal to the key length. If a key of length 7 had been used, the digrams MD, IO, lines, IA, OR, and NS would have occurred instead. In fact, for each key length, a different set of digrams is produced in the ciphertext. By hunting for the various possibilities, the cryptanalyst can often easily determine the key length. The remaining step is to order the columns. When the number of columns, K, is small, each of the K1 column pairs can be examined in turn to see if its digram frequencies match those for English plain text. The pair with the best match is assumed to be correctly positioned. Now each of the remaining columns is tentatively tried as the successor to this pair. The column whose digram and trigram frequencies give the best match is tentatively assumed to be correct. The next column is found in the same way. The entire process is continued until a potential ordering is found. Chances are that the plain text will be recognizable at this point. For instance, if Milloin occurs, it is clear what the error is. Some transposition ciphers accept a fixed length block of input and produce a fixed length block of output. These ciphers can be completely described by giving a list telling the order in which the characters are to be output. For example, the cipher of figure 823 can be seen as a 64 character block cipher. Its output is 4, 12, 20, 28, 36, 44, 52, 60, 5, 13, 62. In other words, the fourth input character is the first to be output, followed by the 12th, F, and so on. 8.1.4 one-time pads. Constructing an unbreakable cipher is actually quite easy. The technique has been known for decades. First choose a random bit string as the key. Then convert the plain text into a bit string, for example, by using its ASCII representation. Finally, compute the XOR, exclusive, OR, of these two strings, bit by bit. The resulting ciphertext cannot be broken, because in a sufficiently large sample of ciphertext, each letter will occur equally often, as will every digram, every trigram, and so on. This method, known as the one-time pad, is immune to all present and future attacks, no matter how much computational power the intruder has. The reason derives from information theory. There is simply no information in the message, because all possible plain texts of the given length are equally likely. An example of how one-time pads are used is given in figure 824. First, message 1, I love you, is converted to 7-bit ASCII. Then a one-time pad, pad 1, is chosen and stored with the message to get the ciphertext. A cryptanalyst could try all possible one-time pads to see what plaintext came out for each one. For example, the one-time pad listed as pad 2 in the figure could be tried, resulting in plaintext 2, Elvis lives, which may or may not be plausible, a subject beyond the scope of this book. In fact, for every 11 character ASCII plaintext, there is a one-time pad that generates it. That is what we mean by saying there is no information in the ciphertext. You can get any message of the correct length out of it. One-time pads are great in theory, but have a number of disadvantages in practice. To start with, the key cannot be memorized, so both sender and receiver must carry a written copy with them. If either one is subject to capture, written keys are clearly undesirable. Additionally, the total amount of data that can be transmitted is limited by the amount of key available. If the spy strikes it rich and discovers a wealth of data, he may find himself unable to transmit them back to message 1. 1,001,001 0100000 1,101,100 1,101,111 1,110,110 1,100,101 0100000 1,111,001 1,101,111 1,110,101 0101110 pad 1 1,010,010 1,001,011 1,110,010 1,010,101 1,010,010 1,100,011 0001011 0101010 1,010,111 1,100,110 0101011 ciphertext 0011011 1,101,011 0011110 0111010 0100100 0000110 0101011 1,010,011 0111000 0010011 0000101 pad 2 1,011,110 0000111 1,101,000 1,010,011 1,010,111 0100110 1,111 0111010 1,001,110 1,110,110 1,110,110 plaintext 2 1,101 1,101,100 1,110,110 1,101,001 1,110,011 0100000 1,101,100 1,101,001 1,110,110 1,100,101 1,110,011 figure 824. The use of a one-time pad for encryption and the possibility of getting any possible plaintext from the ciphertext by the use of some other pad headquarters, because the key has been used up. Another problem is the sensitivity of the method to lost or inserted characters. If the sender and receiver get out of synchronization, all data from then on will appear garbled. With the advent of computers, the one-time pad might potentially become practical for some applications. The source of the key could be a special DVD that contains several gigabytes of information, and, if transported in a DVD movie box and prefixed by a few minutes of video, would not even be suspicious. Of course, at gigabit network speeds, having to insert a new DVD every 30 seconds could become tedious. And the DVDs must be personally carried from the sender to the receiver before any messages can be sent, which greatly reduces their practical utility. Quantum cryptography. Interestingly, there may be a solution to the problem of how to transmit the one-time pad over the network, and it comes from a very unlikely source, quantum mechanics. This area is still experimental, but initial tests are promising. If it can be perfected and be made efficient, virtually all cryptography will eventually be done using one-time pads, since they are provably secure. Below we will briefly explain how this method, quantum cryptography, works. In particular, we will describe a protocol called BB84 after its authors and publication year, Bennett and Brassard, 1984. Suppose that a user, Alice, wants to establish a one-time pad with a second user, Bob. Alice and Bob are called principals, the main characters in our story. For example, Bob is a banker with whom Alice would like to do business. The names Alice and Bob have been used for the principals in virtually every paper and book on cryptography, since Ron Rivest introduced them many years ago, Rivest and others, 1978. Cryptographers love tradition. If we were to use Andy and Barbara as the principals, no one would believe anything in this chapter. So be it. If Alice and Bob could establish a one-time pad, they could use it to communicate securely. The question is, how can they establish it without previously exchanging DVDs? We can assume that Alice and Bob are at the opposite ends of an optical fiber over which they can send and receive light pulses. However, an intrepid intruder, Trudy, can cut the fiber to splice in an active tap. Trudy can read all the bits sent in both directions. She can also send false messages in both directions. The situation might seem hopeless for Alice and Bob, but quantum cryptography can shed some new light on the subject. Quantum cryptography is based on the fact that light comes in little packets called photons, which have some peculiar properties. Furthermore, light can be polarized by being passed through a polarizing filter, a fact well known to both sunglasses wearers and photographers. If a beam of light, that is, a stream of photons, is passed through a polarizing filter, all the photons emerging from it will be polarized in the direction of the filter's axis, for instance, vertically. If the beam is now passed through a second polarizing filter, the intensity of the light emerging from the second filter is proportional to the square of the cosine of the angle between the axes. If the two axes are perpendicular, no photons get through. The absolute orientation of the two filters does not matter, only the angle between their axes counts. To generate a one-time pad, Alice needs two sets of polarizing filters. Set 1 consists of a vertical filter and a horizontal filter. This choice is called a rectilinear basis. A basis, plural, basis, is just a coordinate system. The second set of filters is the same, except rotated 45 degrees, so one filter runs from the lower left to the upper right and the other filter runs from the upper left to the lower right. This choice is called a diagonal basis. Thus, Alice has two bases, which she can rapidly insert into her beam at will. In reality, Alice does not have 4 separate filters, but a crystal whose polarization can be switched electrically to any of the 4 allowed directions at great speed. Bob has the same equipment as Alice. The fact that Alice and Bob each have 2 bases available is essential to quantum cryptography. For each basis, Alice now assigns one direction as 0 and the other as 1. In the example presented below, we assume she chooses vertical to be 0 and horizontal to be 1. Independently, she also chooses lower left to upper right as 0 and upper left to lower right as 1. She sends these choices to Bob as plain text. Now Alice picks a one-time pad, for example based on a random number generator, a complex subject all by itself. She transfers it bit by bit to Bob, choosing one of her 2 bases at random for each bit. To send a bit, her photon gun emits one photon polarized appropriately for the basis she is using for that bit. For example, she might choose bases of diagonal, rectilinear, rectilinear, diagonal, rectilinear, etc. To send her one-time pad of 100111001001010 with these bases, she would send the photons shown in figure 8 to 5. Given the one-time pad and the sequence of bases, the polarization to use for each bit is uniquely determined. Bits sent 1 photon at a time are called qubits. Bob does not know which bases to use, so he picks one at random for each arriving photon and just uses it, as shown in figure 8 to 5b. If he picks the correct basis, he gets the correct bit. If he picks the incorrect basis, he gets a random bit, because if a photon hits a filter polarized at 45 degrees to its own polarization, it randomly jumps to the polarization of the filter, or to a polarization perpendicular to the filter, with equal probability. This property of photons is fundamental to quantum mechanics. Thus, some of the bits are correct and some are random, but Bob does not know which are which. Bob's results are depicted in figure 8 to 5c. Figure 8 to 5. An example of quantum cryptography. How does Bob find out which basis he got right and which he got wrong? He simply tells Alice which basis he used for each bit in plain text, and she tells him which are right and which are wrong in plain text, as shown in figure 8 to 5d. From this information, both of them can build a bit string from the correct guesses, as shown in figure 8 to 5e. On the average, this bit string will be half the length of the original bit string, but since both parties know it, they can use it as a one-time pad. All Alice has to do is transmit a bit string slightly more than twice the desired length, and she and Bob will have a one-time pad of the desired length. Done. But wait a minute. We forgot Trudy. Suppose that she is curious about what Alice has to say, and cuts the fiber, inserting her own detector and transmitter. Unfortunately for her, she does not know which basis to use for each photon either. The best she can do is pick one at random for each photon, just as Bob does. An example of her choices is shown in figure 8 to 5f. When Bob later reports, in plain text, which basis he used, and Alice tells him, in plain text, which ones are correct, Trudy now knows when she got it right and when she got it wrong. In figure 8 to 5, she got it right for bits 0, 1, 2, 3, 4, 6, 8, 12, and 13. But she knows from Alice's reply in figure 8 to 5d that only bits 1, 3, 7, 8, 10, 11, 12, and 14 are part of the one-time pad. For 4 of these bits, 1, 3, 8, and 12, she guessed right and captured the correct bit. For the other 4, 7, 10, 11, and 14, she guessed wrong and does not know the bit transmitted. Thus, Bob knows the one-time pad starts with 01011001 from figure 8 to 5e, but all Trudy has is 01 question mark 1 question mark 0 question mark from figure 8 to 5g. Of course, Alice and Bob are aware that Trudy may have captured part of their one-time pad, so they would like to reduce the information Trudy has. They can do this by performing a transformation on it. For example, they could divide the one-time pad into blocks of 1024 bits, square each one to form a 2048-bit number, and use the concatenation of these 2048-bit numbers as the one-time pad. With her partial knowledge of the bit string transmitted, Trudy has no way to generate its square, and so has nothing. The transformation from the original one-time pad to a different one that reduces Trudy's knowledge is called privacy amplification. In practice, complex transformations in which every output bit depends on every input bit are used instead of squaring. Poor Trudy. Not only does she have no idea what the one-time pad is, but her presence is not a secret either. After all, she must relay each received bit to Bob to trick him into thinking he is talking to Alice. The trouble is, the best she can do is transmit the cool bit she received using the polarization she used to receive it, and about half the time she will be wrong, causing many errors in Bob's one-time pad. When Alice finally starts sending data, she encodes it using a heavy forward error correcting code. From Bob's point of view, a 1-bit error in the one-time pad is the same as a 1-bit transmission error. Either way, he gets the wrong bit. If there is enough forward error correction, he can recover the original message despite all the errors, but he can easily count how many errors were corrected. If this number is far more than the expected error rate of the equipment, he knows that Trudy has tapped the line and can act accordingly. For instance, tell Alice to switch to a radio channel, call the police, etc. If Trudy had a way to clone a photon, so she had one photon to inspect and an identical photon to send to Bob, she could avoid detection, but at present no way to clone a photon perfectly is known. And even if Trudy could clone photons, the value of quantum cryptography to establish own time pads would not be reduced. Although quantum cryptography has been shown to operate over distances of 60 kilometers of fiber, the equipment is complex and expensive. Still, the idea has promise. For more information about quantum cryptography, see Mullins, 2002, 8.1.52 Fundamental Cryptographic Principles. Although we will study many different cryptographic systems in the pages ahead, two principles underlying all of them are important to understand. Pay attention. You violate them at your peril. Redundancy. The first principle is that all encrypted messages must contain some redundancy, that is, information not needed to understand the message. An example may make it clear why this is needed. Consider a mail order company, the Couch Potato, TCP, with 60,000 products. Thinking they are being very efficient, TCP's programmers decide that ordering messages should consist of a 16-byte customer name followed by a 3-byte data field, 1 byte for the quantity and 2 bytes for the product number. The last 3 bytes are to be encrypted using a very long key known only by the customer and TCP. At first, this might seem secure, and in a sense it is, because passive intruders cannot decrypt the messages. Unfortunately, it also has a fatal flaw that renders it useless. Suppose that a recently fired employee wants to punish TCP for firing her. Just before leaving, she takes the customer list with her. She works through the night writing a program to generate fictitious orders using real customer names. Since she does not have the list of keys, she just puts random numbers in the last 3 bytes and sends hundreds of orders off to TCP. When these messages arrive, TCP's computer uses a customer's name to locate the key and decrypt the message. Unfortunately for TCP, almost every 3-byte message is valid, so the computer begins printing out shipping instructions. While it might seem odd for a customer to order 837 sets of children's swings or 540 sandboxes, for all the computer knows, the customer might be planning to open a chain of franchised playgrounds. In this way, an active intruder, the ex-employee, can cause a massive amount of trouble, even though she cannot understand the messages her computer is generating. This problem can be solved by the addition of redundancy to all messages. For example, if order messages are extended to 12 bytes, the first 9 of which must be zeros, this attack no longer works, because the ex-employee can no longer generate a large stream of valid messages. The moral of the story is that all messages must contain considerable redundancy so that active intruders cannot send random junk and have it be interpreted as a valid message. However, adding redundancy makes it easier for cryptanalysts to break messages. Suppose that the mail order business is highly competitive, and the Couch Potato's main competitor, the Sofa Tuber, would dearly love to know how many sandboxes TCP is selling, so it taps TCP's phone line. In the original scheme with 3-byte messages, cryptanalysis was nearly impossible, because after guessing a key, the cryptanalyst had no way of telling whether it was right because almost every message was technically legal. With the new 12-byte scheme, it is easy for the cryptanalyst to tell a valid message from an invalid one. Thus, we have cryptographic principle 1. Messages must contain some redundancy. In other words, upon decrypting a message, the recipient must be able to tell whether it is valid by simply inspecting the message and perhaps performing a simple computation. This redundancy is needed to prevent active intruders from sending garbage and tricking the receiver into decrypting the garbage and acting on the plain text. However, this same redundancy makes it much easier for passive intruders to break the system, so there is some tension here. Furthermore, the redundancy should never be in the form of end zeros at the start or end of a message, since running such messages through some cryptographic algorithms gives more predictable results, making the cryptanalyst's job easier. A CRC polynomial is much better than a run of zeros, since the receiver can easily verify it, but it generates more work for the cryptanalyst. Even better is to use a cryptographic hash, a concept we will explore later. For the moment, think of it as a better CRC. Getting back to quantum cryptography for a moment, we can also see how redundancy plays a role there. Due to Trudy's interception of the photons, some bits in Bob's one-time pad will be wrong. Bob needs some redundancy in the incoming messages to determine that errors are present. One very crude form of redundancy is repeating the message 2 times. If the 2 copies are not identical, Bob knows that either the fiber is very noisy or someone is tampering with the transmission. Of course, sending everything twice is overkill. A Hamming or Reed-Solomon code is a more efficient way to do error detection and correction. But it should be clear that some redundancy is needed to distinguish a valid message from an invalid message, especially in the face of an active intruder. Freshness. The second cryptographic principle is that measures must be taken to ensure that each message received can be verified as being fresh, that is, sent very recently. This measure is needed to prevent active intruders from playing back old messages. If no such measures were taken, our ex-employee could tap TCP's phone line and just keep repeating previously sent valid messages. Thus, cryptographic principle 2, some method is needed to foil replay attacks. One such measure is including in every message a timestamp valid only for, say, 10 seconds. The receiver can then just keep messages around for 10 seconds and compare newly arrived messages to previous ones to filter out duplicates. Messages older than 10 seconds can be thrown out, since any replays sent more than 10 seconds later will be rejected as too old. Measures other than timestamps will be discussed later. 8.2 Symmetric-key algorithms. Modern cryptography uses the same basic ideas as traditional cryptography, transposition, and substitution, but its emphasis is different. Traditionally, cryptographers have used simple algorithms. Nowadays, the reverse is true. The object is to make the encryption algorithm so complex and involuted that, even if the cryptanalyst acquires vast mounds of enciphered text of his own choosing, he will not be able to make any sense of it at all without the key. The first class of encryption algorithms we will study in this chapter are called symmetric-key algorithms, because they use the same key for encryption and decryption. Figure 8.2 illustrates the use of a symmetric-key algorithm. In particular, we will focus on block ciphers, which take an n-bit block of plain text as input and transform it using the key into an n-bit block of ciphertext. Cryptographic algorithms can be implemented in either hardware, for speed, or software, for flexibility. Although most of our treatment concerns the algorithms and protocols, which are independent of the actual implementation, a few words about building cryptographic hardware may be of interest. Transpositions and substitutions can be implemented with simple electrical circuits. Figure 8.6 shows a device known as a P-box. P stands for permutation, used to effect a transposition on an 8-bit input. If the 8 bits are designated from top to bottom as 0, 1, 2, 3, 4, 5, 6, 7, the output of this particular P-box is 36,071,245. By appropriate internal wiring, a P-box can be made to perform any transposition and do it at practically the speed of light, since no computation is involved, just signal propagation. This design follows Kirchhoff's principle. The attacker knows that the general method is permuting the bits. What he does not know is which bit goes where. S1, S2, P1, P2, P3, P4, S3, S4, S5, S6, S7, S8 product cipher, C, S-box decoder. 3 to 8 encoder. 8 to 3, B, P-box, S9, S10, S11, S12 figure 8 to 6. Basic element of product ciphers, P-box, B, S-box, C, product. Substitutions are performed by S-boxes, as shown in figure 8 to 6, B. In this example, a 3-bit plain text is entered, and a 3-bit ciphertext is output. The 3-bit input selects one of the 8 lines exiting from the first stage and sets it to 1, all the other lines are 0. The second stage is a P box. The third stage encodes a selected input line in binary again. With the wiring shown, if the 8 octal numbers 0, 1, 2, 3, 4, 5, 6, 7 were input one after another, the output sequence would be 24,506,713. In other words, 0 has been replaced by 2, 1 has been replaced by 4, etc. Again, by appropriate wiring of the P box inside the S box, any substitution can be accomplished. Furthermore, such a device can be built in hardware to achieve great speed, since encoders and decoders have only 1 or 2 sub-nanosecond gate delays and the propagation time across the P box may well be less than 1 picosec. The real power of these basic elements only becomes apparent when we cascade a whole series of boxes to form a product cipher, as shown in figure 8 to 6, c. In this example, 12 input lines are transposed, that is, permuted, by the first stage, P1. In the second stage, the input is broken up into 4 groups of 3 bits, each of which is substituted independently of the others, S1 to S4. This arrangement shows a method of approximating a larger S box from multiple, smaller S boxes. It is useful because small S boxes are practical for a hardware implementation. For instance, an 8-bit S box can be realized as a 256 entry lookup table, but large boxes become unwieldy to build. For instance, a 12-bit S box would at a minimum need 212 equals 4096 crossed wires in its middle stage. Although this method is less general, it is still powerful. By inclusion of a sufficiently large number of stages in the product cipher, the output can be made to be an exceedingly complicated function of the input. Product ciphers that operate on k-bit inputs to produce k-bit outputs are very common. Typically, k is 64 to 256. A hardware implementation usually has at least 10 physical stages, instead of just 7 as in figure 8 to 6, c. A software implementation is programmed as a loop with at least 8 iterations, each one performing S-box type substitutions on subblocks of the 64 to 256-bit data block, followed by a permutation that mixes the outputs of the S-boxes. Often there is a special initial permutation, and one at the end as well. In the literature, the iterations are called rounds 8.2.1. These are data encryption standard. In January 1977, the US government adopted a product cipher developed by IBM as its official standard for unclassified information. This cipher, D's, data encryption standard, was widely adopted by the industry for use in security products. It is no longer secure in its original form, but in a modified form it is still useful. We will now explain how D's works. An outline of D's is shown in figure 8 to 7. Plain text is encrypted in blocks of 64 bits, yielding 64 bits of ciphertext. The algorithm, which is parameterized by a 56-bit key, has 19 distinct stages. The first stage is a key-independent transposition on the 64-bit plain text. The last stage is the exact inverse of this transposition. The stage prior to the last one exchanges the leftmost 32 bits with the rightmost 32 bits. The remaining 16 stages are functionally identical, but are parameterized by different functions of the key. The algorithm has been designed to allow decryption to be done with the same key as encryption, a property needed in any symmetric key algorithm. The steps are just run in the reverse order. The operation of one of these intermediate stages is illustrated in figure 8 to 7, b. Each stage takes two 32-bit inputs and produces two 32-bit outputs. The left output is simply a copy of the right input. The right output is the bitwise OR of the left input and a function of the right input and the key for this stage, key. Pretty much all the complexity of the algorithm lies in this function. Figure 8 to 7. The data encryption standard, general outline, b. D10 of one iteration. The circled plus means exclusive OR. The function consists of 4 steps, carried out in sequence. First, a 48-bit number, E, is constructed by expanding the 32-bit Re1 according to a fixed transposition and duplication rule. Second, E and key are stored together. This output is then partitioned into 8 groups of 6 bits each of which is fed into a different S-box. Each of the 64 possible inputs to an S-box is mapped onto a 4-bit output. Finally, these 8x4 bits are passed through a P-box. In each of the 16 iterations, a different key is used. Before the algorithm starts, a 56-bit transposition is applied to the key. Just before each iteration, the key is partitioned into two 28-bit units, each of which is rotated left by a number of bits dependent on the iteration number. Key is derived from this rotated key by applying yet another 56-bit transposition to it. A different 48-bit subset of the 56 bits is extracted and permuted on each round. A technique that is sometimes used to make Ds stronger is called whitening. It consists of XORing a random 64-bit key with each plain text block before feeding it into Ds, and then XORing a second 64-bit key with the resulting ciphertext before transmitting it. Whitening can easily be removed by running the reverse operations if the receiver has the two whitening keys. Since this technique effectively adds more bits to the key length, it makes an exhaustive search of the key space much more time consuming. Note that the same whitening key is used for each block, that is, there is only one whitening key. Ds has been enveloped in controversy since the day it was launched. It was based on a cipher developed and patented by IBM called Lucifer, except that IBM's cipher used a 128-bit key instead of a 56-bit key. When the US federal government wanted to standardize on one cipher for unclassified use, it invited IBM to discuss the matter with NSA, the US government's code-breaking arm, which is the world's largest employer of mathematicians and cryptologists. NSA is so secret that an industry joke goes, Q. What does NSA stand for? A. No such agency. Actually, NSA stands for National Security Agency. After these discussions took place, IBM reduced the key from 128 bits to 56 bits and decided to keep secret the process by which Ds was designed. Many people suspected that the key length was reduced to make sure that NSA could just break Ds, but no organization with a smaller budget could. The point of the secret design was supposedly to hide a backdoor that could make it even easier for NSA to break Ds. When an NSA employee discreetly told IEEE to cancel a planned conference on cryptography, that did not make people any more comfortable. NSA denied everything. In 1977, two Stanford cryptography researchers, Duffy and Hellman, 1977, designed a machine to break Ds and estimated that it could be built for $20 million. Given a small piece of plain text and matched ciphertext, this machine could find the key by exhaustive search of the 256 entry key space in under one day. Nowadays, the game is up. Such a machine exists, is for sale, and costs less than $10,000 to make. Kummer and others, 2006. Triple Ds. As early as 1979, IBM realized that the D's key length was too short and devised a way to effectively increase it using triple encryption. Tuchman, 1979. The method chosen, which has since been incorporated in International Standard 8732, is illustrated in Figure 828. Here, two keys and three stages are used. In the first stage, the plain text is encrypted using Ds in the usual way with K1. In the second stage, Ds is run in decryption mode, using K2 as the key. Finally, another Ds encryption is done with K1. This design immediately gives rise to two questions. First, why are only two keys used, instead of three? Second, why is ED, encrypt decrypt encrypt, used, instead of EEE, encrypt encrypt encrypt? The reason that two keys are used is that even the most paranoid of cryptographers believe that 112 bits is adequate for routine commercial applications for the time being, and among cryptographers, paranoia is considered a feature, not a bug. Going to 168 bits would just add the unnecessary overhead of managing and transporting another key for little real gain. Figure 828. Triple encryption using Ds. B. Decryption. The reason for encrypting, decrypting, and then encrypting again is backward compatibility with existing single key Ds systems. Both the encryption and decryption functions are mappings between sets of 64-bit numbers. From a cryptographic point of view, the two mappings are equally strong. By using EED, however, instead of EEE, a computer using triple encryption can speak to one using single encryption by just setting K1 equals K2. This property allows triple encryption to be phased in gradually, something of no concern to academic cryptographers, but of considerable importance to IBM and its customers. 8.2. To ease their advanced encryption standard as Ds began approaching the end of its useful life, even with triple Ds, NIST, National Institute of Standards and Technology, the agency of the US Department of Commerce, charged with approving standards for the US federal government, decided that the government needed a new cryptographic standard for unclassified use. NIST was keenly aware of all the controversy surrounding Ds and well knew that, if it just announced a new standard, everyone knowing anything about cryptography would automatically assume that NSA had built a backdoor into it, so NSA could read everything encrypted with it. Under these conditions, probably no one would use the standard, and it would have died quietly. So, NIST took a surprisingly different approach for a government bureaucracy. It sponsored a cryptographic bake-off contest. In January 1997, researchers from all over the world were invited to submit proposals for a new standard, to be called Ds, Advanced Encryption Standard. The bake-off rules were: 1. The algorithm must be a symmetric block cipher. 2. The full design must be public. 3. Key lengths of 128, 192, and 256 bits must be supported. 4. Both software and hardware implementations must be possible. 5. The algorithm must be public or licensed on non-discriminatory terms. 15 serious proposals were made, and public conferences were organized in which they were presented, and attendees were actively encouraged to find flaws in all of them. In August 1998, NIST selected 5 finalists, primarily on the basis of their security, efficiency, simplicity, flexibility, and memory requirements, important for embedded systems. More conferences were held, and more potshots taken. In October 2000, NIST announced that it had selected Ridge&Deal by Joan Dieman and Vincent Ridgman. The name Ridge&Deal, pronounced Rindal, more or less, is derived from the last names of the authors, Ridgman plus Dieman. In November 2001, Ridge&Deal became the EASE US government standard, published as FIPS, Federal Information Processing Standard, 197. Due to the extraordinary openness of the competition, the technical properties of Ridge&Deal, and the fact that the winning team consisted of 2 young Belgian cryptographers, who were unlikely to have built in a backdoor just to please NSA, Ridge&Deal has become the world's dominant cryptographic cipher. EASE encryption and decryption is now part of the instruction set for some microprocessors, for instance, Intel. Ridge&Deal supports key lengths and block sizes from 128 bits to 256 bits in steps of 32 bits. The key length and block length may be chosen independently. However, EASE specifies that the block size must be 128 bits and the key length must be 128, 192, or 256 bits. It is doubtful that anyone will ever use 192-bit keys, so de facto, EASE has 2 variants, a 128-bit block with a 128-bit key and a 128-bit block with a 256-bit key. In our treatment of the algorithm, we will examine only the 128 over 128 case, because this is likely to become the commercial norm. A 128-bit key gives a key space of 2128, 3x1038 keys. Even if NSA manages to build a machine with 1 billion parallel processors, each being able to evaluate 1 key per picosecond, it would take such a machine about 1010 years to search the key space. By then the sun will have burned out, so the folks then present will have to read the results by candlelight. Rigendale. From a mathematical perspective, Rigendale is based on Galois field theory, which gives it some provable security properties. However, it can also be viewed as C-code, without getting into the mathematics. Like D's, Rigendale uses substitution and permutations, and it also uses multiple rounds. The number of rounds depends on the key size and block size, being 10 for 128-bit keys with 128-bit blocks, and moving up to 14 for the largest key or the largest block. However, unlike D's, all operations involve entire bytes, to allow for efficient implementations in both hardware and software. An outline of the code is given in Figure 829. Note that this code is for the purpose of illustration. Good implementations of security code will follow additional practices, such as zeroing out sensitive memory after it has been used. See, for example, Ferguson and others, 2010. Define length 16 / hash bytes in data block or key */ define NROWS 4 * number of rows in state */ define cols 4 * number of columns in state */ define rounds 10 * number of iterations. */ type def unsigned char byte / unsigned 8-bit integer */ Rigendale byte plain text length byte ciphertext length byte key length inter / loop index * byte state NROWS cols / current state * struct byte k NROWS cols rk rounds +1 / round keys * expand key rk / construct the round keys * copy plain text to state plain text / init current state * zor round key into state rk 0 / zor key into state * 4 r equals 1 r equals rounds r ++ substitute state / apply s box to each byte * rotate rows state * rotate row I by I bytes * if r rounds mix columns state * mix function * zor round key into state rk r * zor key into state * copy state to ciphertext state * return result * figure 829. An outline of Rigendale in C. The function Rigendale has 3 parameters. They are plain text, an array of 16 bytes containing the input data, ciphertext, an array of 16 bytes where the enciphered output will be returned, and key, the 16-byte key. During the calculation, the current state of the data is maintained in a byte array state, whose size is NROWS x and cols. For 128-bit blocks, this array is 4x4 bytes. With 16 bytes, the full 128-bit data block can be stored. The state array is initialized to the plain text and modified by every step in the computation. In some steps, byte-for-byte substitution is performed. In others, the bytes are permuted within the array. Other transformations are also used. At the end, the contents of the state are returned as the ciphertext. The code starts out by expanding the key into 11 arrays of the same size as the state. They are stored in Rk, which is an array of structs, each containing a state array. One of these will be used at the start of the calculation and the other 10 will be used during the 10 rounds, 1 per round. The calculation of the round keys from the encryption key is too complicated for us to get into here. Suffice it to say that the round keys are produced by repeated rotation and zoring of various groups of key bits. For all the details, see Demon and Ridgeman, 2002. The next step is to copy the plain text into the state array, so it can be processed during the rounds. It is copied in column order, with the first 4 bytes going into column 0, the next 4 bytes going into column 1, and so on. Both the columns and the rows are numbered starting at 0, although the rounds are numbered starting at 1. This initial setup of the 12-byte arrays of size 4x4 is illustrated in figure 8 to 10 state RK0, RK1, RK2, RK3, RK4, RK5, RK6, RK7, RK8, RK9, RK10, 128-bit plaintext 128-bit encryption key round keys figure 8 to 10. Creating the state and RK arrays. There is one more step before the main computation begins. RK0 is stored into state, byte for byte. In other words, each of the 16 bytes in state is replaced by the XOR of itself and the corresponding byte in RK0. Now it is time for the main attraction. The loop executes 10 iterations, 1 per round, transforming state on each iteration. The contents of each round is produced in 4 steps. Step 1 does a byte for byte substitution on state. Each byte in turn is used as an index into an S box to replace its value by the contents of that S box entry. This step is a straight monoalphabetic substitution cipher. Unlike D's, which has multiple S boxes, RIG has only one S box. Step 2 rotates each of the 4 rows to the left. Row 0 is rotated 0 bytes, that is, not changed. Row 1 is rotated 1 byte, row 2 is rotated 2 bytes, and row 3 is rotated 3 bytes. This step diffuses the contents of the current data around the block, analogous to the permutations of figure 8 to 6. Step 3 mixes up each column independently of the other ones. The mixing is done using matrix multiplication, in which the new column is the product of the old column and a constant matrix, with the multiplication done using the finite Galois field, GF28. Although this may sound complicated, an algorithm exists that allows each element of the new column to be computed using 2 table lookups and 3 XORs, Daemon and Ridgman, 2002, Appendix E. Finally, step 4 XORs the key for this round into the state array for use in the next round. Since every step is reversible, decryption can be done just by running the algorithm backward. However, there is also a trick available in which decryption can be done by running the encryption algorithm using different tables. The algorithm has been designed not only for great security, but also for great speed. A good software implementation on a 2 GHz machine should be able to achieve an encryption rate of 700 megabits per second, which is fast enough to encrypt over 100 MPEG-2 videos in real time. Hardware implementations are faster still. 8.2.3 cipher modes. Despite all this complexity, EAS, or Ds, or any block cipher for that matter, is basically a monoalphabetic substitution cipher using big characters, 128-bit characters for EAS and 64-bit characters for Ds. Whenever the same plaintext block goes in the front end, the same ciphertext block comes out the back end. If you encrypt the plaintext AppDef 100 times with the same Ds key, you get the same ciphertext 100 times. An intruder can exploit this property to help subvert the cipher. Electronic codebook mode. To see how this monoalphabetic substitution cipher property can be used to partially defeat the cipher, we will use triple Ds because it is easier to depict 64-bit blocks than 128-bit blocks, but EAS has exactly the same problem. The straightforward way to use Ds to encrypt a long piece of plaintext is to break it up into consecutive 8-byte, 64-bit blocks and encrypt them one after another with the same key. The last piece of plaintext is padded out to 64 bits, if need be. This technique is known as ECB mode, electronic codebook mode, in analogy with old-fashioned codebooks, where each plaintext word was listed, followed by its ciphertext, usually a 5-digit decimal number. In figure 8 to 11, we have the start of a computer file listing the annual bonuses a company has decided to award to its employees. This file consists of consecutive 32-byte records, 1 per employee, in the format shown. 16 bytes for the name, 8 bytes for the position, and 8 bytes for the bonus. Each of the 16 8-byte blocks, numbered from 0 to 15, is encrypted by triple Ds. Leslie just had a fight with the boss and is not expecting much of a bonus. Kim, in contrast, is a boss favorite, and everyone knows this. Leslie can get access to the file after it is encrypted, but before it is sent to the bank. Can Leslie rectify this unfair situation, given only the encrypted file? No problem at all. All Leslie has to do is make a copy of the 12th ciphertext block, which contains Kim's bonus, and use it to replace the 4th ciphertext block, which contains Leslie's bonus. Even without knowing what the 12th block says, Leslie can expect to have a much merrier Christmas this year. Copying the 8th ciphertext block is also a possibility, but is more likely to be detected. Besides, Leslie is not a greedy person. Figure 8 to 11. The plain text of a file encrypted as 16 blocks. Cipher block chaining mode. To thwart this type of attack, all block ciphers can be chained in various ways, so that replacing a block the way Leslie did will cause a plain text decrypted starting at the replaced block to be garbage. One way of chaining is cipher block chaining. In this method, shown in figure 8 to 12, each plain text block is ORed with the previous ciphertext block before being encrypted. Consequently, the same plaintext block no longer maps onto the same ciphertext block, and the encryption is no longer a big monoalphabetic substitution cipher. The first block is ORed with a randomly chosen 4th initialization vector, which is transmitted in plaintext along with the ciphertext. Figure 8 to 12. Cipher block chaining. A. Encryption. B. Decryption. We can see how cipher block chaining mode works by examining the example of figure 8 to 12. We start out by computing C0 equals E, P0s or 4th. Then we compute C1 equals E, P1s or C0, and so on. Decryption also uses OR to reverse the process, with P0 equals 4th OR D, C0, and so on. Note that the encryption of block I is a function of all the plain text in blocks 0 through I1, so the same plaintext generates different ciphertext depending on where it occurs. A transformation of the type Leslie made will result in nonsense for 2 blocks starting at Leslie's bonus field. To an astute security officer, this peculiarity might suggest where to start the ensuing investigation. Cipher block chaining also has the advantage that the same plaintext block will not result in the same ciphertext block, making cryptanalysis more difficult. In fact, this is the main reason it is used. Cipher feedback mode, however, cipher block chaining, has the disadvantage of requiring an entire 64-bit block to arrive before decryption can begin. For byte-by-byte encryption, cipher feedback mode using triple Ds is used, as shown in figure 8 to 13. For ease, the idea is exactly the same, only a 128-bit shift register is used. In this figure, the state of the encryption machine is shown after bytes 0 through 9 have been encrypted and sent. When plaintext byte 10 arrives, as illustrated in figure 8.13, the D's algorithm operates on the 64-bit shift register to generate a 64-bit ciphertext. The leftmost byte of that ciphertext is extracted and stored with P10. That byte is transmitted on the transmission line. In addition, the shift register is shifted left 8 bits, causing C2 to fall off the left end, and C10 is inserted in the position just vacated at the right end by C9. Figure 8 to 13. Cipher feedback mode. A. Encryption. B. Decryption. Note that the contents of the shift register depend on the entire previous history of the plaintext, so a pattern that repeats multiple times in the plaintext will be encrypted differently each time in the ciphertext. As with cipher block chaining, an initialization vector is needed to start the ball rolling. Decryption with cipher feedback mode works the same way as encryption. In particular, the content of the shift register is encrypted, not decrypted, so the selected byte that is ORed with C10 to get P10 is the same one that was ORed with P10 to generate C10 in the first place. As long as the two shift registers remain identical, decryption works correctly. This is illustrated in figure 8 to 13. B. A problem with cipher feedback mode is that, if one bit of the ciphertext is accidentally inverted during transmission, the 8 bytes that are decrypted, while the bad byte is in the shift register will be corrupted. Once the bad byte is pushed out of the shift register, correct plaintext will once again be generated. Thus, the effects of a single inverted bit are relatively localized and do not ruin the rest of the message, but they do ruin as many bits as the shift register is wide. Stream cipher mode. Nevertheless, applications exist in which having a 1-bit transmission error mess up 64 bits of plaintext is to large an effect. For these applications, a fourth option, stream cipher mode, exists. It works by encrypting an initialization vector using a key to get an output block. The output block is then encrypted using the key to get a second output block. This block is then encrypted to get a third block, and so on. The arbitrarily large sequence of output blocks, called the key stream, is treated like a one-time pattern XOR with the plaintext to get the ciphertext, as shown in figure 8 to 14. Note that the fourth is used only on the first step. After that, the output is encrypted. Also note that the key stream is independent of the data, so it can be computed in advance, if need be, and is completely insensitive to transmission errors. Decryption is shown in figure 8 to 14, b. Figure 8 to 14. A stream cipher. Encryption. b. Decryption. Decryption occurs by generating the same key stream at the receiving side. Since the key stream depends only on the fourth and the key, it is not affected by transmission errors in the ciphertext. Thus, a 1-bit error in the transmitted ciphertext generates only a 1-bit error in the decrypted plaintext. It is essential never to use the same key, fourth, pair twice with a stream cipher, because doing so will generate the same key stream each time. Using the same key stream twice exposes the ciphertext to a keystream reuse attack. Imagine that the plaintext block, P0, is encrypted with a keystream to get P0s or K0. Later, a second plaintext block, Q0, is encrypted with the same keystream to get Q0s or K0. An intruder who captures both of these ciphertext blocks can simply XOR them together to get P0s or Q0, which eliminates the key. The intruder now has the XOR of the two plaintext blocks. If one of them is known, or can be guessed, the other can also be found. In any event, the XOR of two plaintext streams can be attacked by using statistical properties of the message. For example, for English text, the most common character in the stream will probably be the XOR of two spaces, followed by the XOR of space and the letter E, etc. In short, equipped with the XOR of two plaintexts, the cryptanalyst has an excellent chance of deducing both of them. Counter mode. One problem that all the modes, except electronic codebook mode have, is that random access to encrypted data is impossible. For example, suppose a file is transmitted over a network and then stored on disk in encrypted form. This might be a reasonable way to operate if the receiving computer is a notebook computer that might be stolen. Storing all critical files in encrypted form greatly reduces the damage due to secret information leaking out in the event that the computer falls into the wrong hands. However, disk files are often accessed in non-sequential order, especially files in databases. With a file encrypted using cipher blockchaining, accessing a random block requires first decrypting all the blocks ahead of it, an expensive proposition. For this reason, yet another mode has been invented, counter mode, as illustrated in figure 8 to 15. Here, the plaintext is not encrypted directly. Instead, the initialization vector plus a constant is encrypted, and the resulting ciphertext is XORed with the plaintext. By stepping the initialization vector by 1 for each new block, it is easy to decrypt a block anywhere in the file without first having to decrypt all of its predecessors. Although counter mode is useful, it has a weakness that is worth pointing out. Suppose that the same key, K, is used again in the future with a different plaintext, but the same fourth, and an attacker requires all the ciphertext from both runs. The key streams are the same in both cases, exposing the cipher to a keystream reuse attack of the same kind we saw with stream ciphers. All the cryptanalyst has to do is XOR the two ciphertexts together to eliminate all the cryptographic protection and just get the XOR of the plaintexts. This weakness does not mean counter mode is a bad idea. It just means that both keys and initialization vectors should be chosen independently and at random. Even if the same key is accidentally used twice, if the fourth is different each time, the plain text is safe. Figure 8 to 15. Encryption using counter mode 8.2.4 other ciphers. These, Ridge and Deal, and these are the best known symmetric key cryptographic algorithms, and the standard industry choices, if only for liability reasons. No one will blame you if you use these in your product and these is cracked, but they will certainly blame you if you use a non-standard cipher, and it is later broken. However, it is worth mentioning that numerous other symmetric key ciphers have been devised. Some of these are embedded inside various products. A few of the more common ones are listed in figure 8 to 16. It is possible to use combinations of these ciphers, for example, ease over twofish, so that both ciphers need to be broken to recover the data. Cipher author key length comments these IBM 56 bits too weak to use now RC4 on all drive est1 to 2048 bits caution. Some keys are weak RC5 on all drive est 128 to 256 bits good, but patented ease, Ridge and Deal, Demon, and Ridgeman. 128 to 256 bits best choice Serpent Anderson, Beham, Knudsen 128 to 256 bits very strong triple D's IBM 168 bits good, but getting old twofish Bruce Schneider 128 to 256 bits very strong. Widely used figure 8 to 16. Some common symmetric key cryptographic algorithms 8.2.5 Cryptanalysis. Before leaving the subject of symmetric key cryptography, it is worth at least mentioning 4 developments in cryptanalysis. The first development is differential cryptanalysis, Beham and Shami, 1997. This technique can be used to attack any block cipher. It works by beginning with a pair of plain text blocks differing in only a small number of bits, and watching carefully what happens on each internal iteration as the encryption proceeds. In many cases, some bit patterns are more common than others, which can lead to probabilistic attacks. The second development worth noting is linear cryptanalysis, Matsu, 1994. It can break these with only 243 known plain texts. It works by storing certain bits in the plain text and ciphertext together, and examining the result. When done repeatedly, half the bits should be zeros and half should be ones. Often, however, ciphers introduce a bias in one direction or the other, and this bias, however small, can be exploited to reduce the work factor. For the details, see Matsu's paper. The third development is using analysis of electrical power consumption to find secret keys. Computers typically use around 3 volts to represent a 1 bit and 0 volts to represent a 0 bit. Thus, processing a 1 takes more electrical energy than processing a 0. If a cryptographic algorithm consists of a loop in which the key bits are processed in order, an attacker who replaces the main NGHZ clock with a slow, for instance, 100 Hz, clock and puts alligator clips on the CPU's power and ground pins can precisely monitor the power consumed by each machine instruction. From this data, deducing the key is surprisingly easy. This kind of cryptanalysis can be defeated only by carefully coding the algorithm in assembly language to make sure power consumption is independent of the key and also independent of all the individual round keys. The fourth development is timing analysis. Cryptographic algorithms are full of if statements that test bits in the round keys. If the then and else parts take different amounts of time by slowing down the clock and seeing how long various steps take, it may also be possible to deduce the round keys. Once all the round keys are known, the original key can usually be computed. Power and timing analysis can also be employed simultaneously to make the job easier. While power and timing analysis may seem exotic, in reality they are powerful techniques that can break any cipher knot. 8.3 Public key algorithms. Historically, distributing the keys has always been the weakest link in most cryptosystems. No matter how strong a cryptosystem was, if an intruder could steal the key, the system was worthless. Cryptologists always took for granted that the encryption key and decryption key were the same, or easily derived from one another. But the key had to be distributed to all users of the system. Thus, it seemed as if there was an inherent problem. keys had to be protected from theft, but they also had to be distributed, so they could not be locked in a bank vault. In 1976, two researchers at Stanford University, Duffy and Hellman, 1976, proposed a radically new kind of crypto system, one in which the encryption and decryption keys were so different that the decryption key could not feasibly be derived from the encryption key. In their proposal, the keyed encryption algorithm, E, and the keyed decryption algorithm, D, had to meet 3 requirements. These requirements can be stated simply as follows. 1. D, E, P equals P2. It is exceedingly difficult to deduce D from E3. E cannot be broken by a chosen plaintext attack. The first requirement says that if we apply D to an encrypted message, E, P, we get the original plaintext message, P, back. Without this property, the legitimate receiver could not decrypt the ciphertext. The second requirement speaks for itself. The third requirement is needed because, as we shall see in a moment, intruders may experiment with the algorithm to their heart's content. Under these conditions, there is no reason that the encryption key cannot be made public. The method works like this. A person, say, Alice, who wants to receive secret messages, first devises 2 algorithms meeting the above requirements. The encryption algorithm and Alice's key are then made public, hence the name public key cryptography. Alice might put her public key on her homepage on the web, for example. We will use the notation EA to mean the encryption algorithm parameterized by Alice's public key. Similarly, the secret decryption algorithm parameterized by Alice's private key is DA. Bob does the same thing, publicizing it but keeping DB secret. Now let us see if we can solve the problem of establishing a secure channel between Alice and Bob, who have never had any previous contact. Both Alice's encryption key, EA, and Bob's encryption key, EB, are assumed to be in publicly readable files. Now Alice takes her first message, P, computes EB, P, and sends it to Bob. Bob then decrypts it by applying his secret key DB, that is, he computes DB, EB, P, equals P. No one else can read the encrypted message, EB, P, because the encryption system is assumed to be strong, and because it is too difficult to derive DB from the publicly known EB. To send a reply, R, Bob transmits EA, R. Alice and Bob can now communicate securely. A note on terminology is perhaps useful here. Public key cryptography requires each user to have 2 keys, a public key, used by the entire world for encrypting messages, to be sent to that user, and a private key, which the user needs for decrypting messages. We will consistently refer to these keys as the public and private keys, respectively, and distinguish them from the secret keys, used for conventional symmetric key cryptography 8.3.1 RSA. The only catch is that we need to find algorithms that indeed satisfy all 3 requirements. Due to the potential advantages of public key cryptography, many researchers are hard at work, and some algorithms have already been published. One good method was discovered by a group at MIT, Rivest and others, 1978. It is known by the initials of the 3 discoverers, Rivest, Shami, Adelman, RSA. It has survived all attempts to break it for more than 30 years, and is considered very strong. Much practical security is based on it. For this reason, Rivest, Shami, and Adelman were given the 2002 ACM Turing Award. Its major disadvantages, that it requires keys of at least 1024 bits for good security, versus 128 bits for symmetric key algorithms, which makes it quite slow. The RSA method is based on some principles from number theory. We will now summarize how to use the method. For details, consult the paper 1. Choose 2 large primes, P and Q, typically 1024 bits, 2. Compute n equals pxq and z equals p1 x q 1 3. Choose a number relatively prime to z and call it d4. Find d such that exd equals 1 mod z. With these parameters computed in advance, we are ready to begin encryption. divide the plain text, regarded as a bit string, into blocks, so that each plain text message, P, falls in the interval 0, P, and do that by grouping the plain text into blocks of k bits, where k is the largest integer for which to k, n is true. To encrypt a message, P, compute C equals P, mod n. To decrypt C, compute P equals CD, mod n. It can be proven that for all P in the specified range, the encryption and decryption functions are inverse. To perform the encryption, you need E and N. To perform the decryption, you need D and N. Therefore, the public key consists of the pair E, N, and the private key consists of D, N. The security of the method is based on the difficulty of factoring large numbers. If the cryptanalyst could factor the publicly known N, he could then find P and Q, and from these Z, equipped with knowledge of Z and E, D can be found using Euclid's algorithm. Fortunately, mathematicians have been trying to factor large numbers for at least 300 years, and the accumulated evidence suggests that it is an exceedingly difficult problem. According to Rivest and colleagues, factoring a 500-digit number would require 1025 years using brute force. In both cases, they assume the best known algorithm and a computer with a 1s instruction time. With a million chips running in parallel, each with an instruction time of 1 sec, it would still take 1016 years. Even if computers continue to get faster by an order of magnitude per decade, it will be many years before factoring a 500-digit number becomes feasible, at which time our descendants can simply choose P and Q still larger. A trivial pedagogical example of how the RSA algorithm works is given in figure 8-17. For this example, we have chosen P equals 3 and Q equals 11, giving N equals 33 and Z equals 20. A suitable value for D is D equals 7, since 7 and 20 have no common factors. With these choices, E can be found by solving the equation 7E equals 1, mod 20, which yields E equals 3. The ciphertext, C, corresponding to a plain text message, P, is given by C equals P3, mod 33. The ciphertext is decrypted by the receiver by making use of the rule P equals C7, mod 33. The figure shows the encryption of the plain text Susan as an example. Figure 8-17. An example of the RSA algorithm. Because the primes chosen for this example are so small, P must be less than 33, so each plain text block can contain only a single character. The result is a monoalphabetic substitution cipher, not very impressive. If instead we had chosen P and Q, 2512, we would have N, 21024, so each block could be up to 1024 bits or 128 8-bit characters, versus 8 characters for Ds and 16 characters for Es. It should be pointed out that using RSA as we have described is similar to using a symmetric algorithm in ECB mode. The same input block gives the same output block. Therefore, some form of chaining is needed for data encryption. However, in practice, most RSA-based systems use public key cryptography primarily for distributing one-time session keys for use with some symmetric key algorithms such as ES or DDDs. RSA is too slow for actually encrypting large volumes of data, but is widely used for key distribution. 8.3.2 other public key algorithms. Although RSA is widely used, it is by no means the only public key algorithm known. The first public key algorithm was the knapsack algorithm, Merkle and Hellman, 1978. The idea here is that someone owns a large number of objects, each with a different weight. The owner encodes the message by secretly selecting a subset of the objects and placing them in the knapsack. The total weight of the objects in the knapsack is made public, as is the list of all possible objects and their corresponding weights. The list of objects in the knapsack is kept secret, with certain additional restrictions. The problem of figuring out a possible list of objects with the given weight was thought to be computationally infeasible and formed the basis of the public key algorithm. The algorithm's inventor, Ralph Merkle, was quite sure that this algorithm could not be broken, so he offered a $100 reward to anyone who could break it. Adi Shamia, The SNRSA promptly broke it and collected the reward. Undeterred, Merkel strengthened the algorithm and offered a $1,000 reward to anyone who could break the new one. Ronald Rivest, the RNRSA, promptly broke the new one and collected the reward. Merkel did not dare offer $10,000 for the next version, so Elena Dadelman was out of luck. Nevertheless, the knapsack algorithm is not considered secure and is not used in practice anymore. Other public key schemes are based on the difficulty of computing discrete logarithms. Algorithms that use this principle have been invented by L. Gamal, 1985, and Sknor, 1991. A few other schemes exist, such as those based on elliptic curves, Menezes and Vanston, 1993, but the two major categories are those based on the difficulty of factoring large numbers and computing discrete logarithms modulo a large prime. These problems are thought to be genuinely difficult to solve. Mathematicians have been working on them for many years without any great breakthroughs. 8.4 Digital signatures. The authenticity of many legal, financial, and other documents is determined by the presence or absence of an authorized handwritten signature. And photocopies do not count. For computerized message systems, to replace the physical transport of paper and ink documents, a method must be found to allow documents to be signed in an unforgeable way. The problem of devising a replacement for handwritten signatures is a difficult one. Basically, what is needed is a system by which one party can send a signed message to another party in such a way that the following conditions hold. 1. The receiver can verify the claimed identity of the sender. 2. The sender cannot later repudiate the contents of the message. 3. The receiver cannot possibly have concocted the message himself. The first requirement is needed, for example, in financial systems. When a customer's computer orders a bank's computer to buy a ton of gold, the bank's computer needs to be able to make sure that the computer giving the order really belongs to the customer whose account is to be debited. In other words, the bank has to authenticate the customer, and the customer has to authenticate the bank. The second requirement is needed to protect the bank against fraud. Suppose that the bank buys the ton of gold, and immediately thereafter the price of gold drops sharply. A dishonest customer might then proceed to sue the bank, claiming that he never issued any order to buy gold. When the bank produces the message in court, the customer may deny having sent it. The property that no party to a contract can later deny having signed it is called non-repudiation. The digital signature schemes that we will now study help provide it. The third requirement is needed to protect the customer in the event that the price of gold shoots up and the bank tries to construct a signed message in which the customer asked for 1 bar of gold instead of 1 ton. In this fraud scenario, the bank just keeps the rest of the gold for itself. 8.4.1 Symmetric-key signatures. One approach to digital signatures is to have a central authority that knows everything and whom everyone trusts, say, Big Brother, BB. Each user then chooses a secret key and carries it by hand to BB's office. Thus, only Alice and BB know Alice's secret key, cap, and so on. When Alice wants to send a signed plain text message, P, to her banker, Bob, she generates cap B, wrap T, P, where B is Bob's identity, RAD is a random number chosen by Alice, T is a timestamp to ensure freshness, and cap B, wrap T, P, is the message encrypted with her key, cap. Then she sends it as depicted in figure 8 to 18. BB sees that the message is from Alice, decrypts it, and sends a message to Bob as shown. The message to Bob contains the plain text of Alice's message and also the signed message KBB, A, T, P. Bob now carries out Alice's request. A, cap, B, wrap T, P, Bob Alice BB KB, A, wrap T, P, KBB, A, T, P, 1, 2 figure 8 to 18. Digital signatures with Big Brother. What happens if Alice later denies sending the message? Step 1 is that everyone sues everyone, at least in the United States. Finally, when the case comes to court, and Alice vigorously denies sending Bob the disputed message, the judge will ask Bob how he can be sure that the disputed message came from Alice, and not from Trudy. Bob first points out that BB will not accept a message from Alice, unless it is encrypted with cap, so there is no possibility of Trudy sending BB a false message from Alice without BB detecting it immediately. Bob then dramatically produces Exhibit A, KBB, A, T, P. Bob says that this is a message signed by BB that proves Alice sent P to Bob. The judge then asks BB, whom everyone trusts, to decrypt Exhibit A. When BB testifies that Bob is telling the truth, the judge decides in favor of Bob. Case dismissed. One potential problem with the signature protocol of figure 8 to 18 is Trudy replaying either message. To minimize this problem, timestamps are used throughout. Furthermore, Bob can check all recent messages to see if RAM was used in any of them. If so, the message is discarded as a replay. Note that based on the timestamp, Bob will reject very old messages. To guard against instant replay attacks, Bob just checks the RAM of every incoming message to see if such a message has been received from Alice in the past hour. If not, Bob can safely assume this is a new request. 8.4.2 Public key signatures. A structural problem with using symmetric key cryptography for digital signatures is that everyone has to agree to trust Big Brother. Furthermore, Big Brother gets to read all signed messages. The most logical candidates for running the Big Brother server are the government, the banks, the accountants, and the lawyers. Unfortunately, none of these inspire total confidence in all citizens. Hence, it would be nice if signing documents did not require a trusted authority. Fortunately, public key cryptography can make an important contribution in this area. Let us assume that the public key encryption and decryption algorithms have the property that E, D, P equals P, in addition, of course, to the usual property that D, E, P equals P. RSA has this property, so the assumption is not unreasonable. Assuming that this is the case, Alice can send a signed plain text message, P, to Bob by transmitting EB, DA, P. Note carefully that Alice knows her own private key, DA, as well as Bob's public key, EB, so constructing this message is something Alice can do. When Bob receives the message, he transforms it using his private key, as usual, yielding DA, P, as shown in figure 8 to 19. He stores this text in a safe place, and then applies EA to get the original plain text. Bob's public key, EB Alice's private key, DA Bob's private key, DB DA, P, EB, DA, P, DA, P, transmission line Alice's computer Bob's computer PP Alice's public key, EA figure 8 to 19. Digital signatures using public key cryptography. To see how the signature property works, suppose that Alice subsequently denies having sent the message P to Bob. When the case comes up in court, Bob can produce both P and DA, P. The judge can easily verify that Bob indeed has a valid message encrypted by DA by simply applying EA to it. Since Bob does not know what Alice's private key is, the only way Bob could have acquired a message encrypted by it is if Alice did indeed send it. While in jail for perjury and fraud, Alice will have much time to devise interesting new public key algorithms. Although using public key cryptography for digital signatures is an elegant scheme, there are problems that are related to the environment in which they operate, rather than to the basic algorithm. For one thing, Bob can prove that a message was sent by Alice only as long as DA remains secret. If Alice discloses her secret key, the argument no longer holds, because anyone could have sent the message, including Bob himself. The problem might arise, for example, if Bob is Alice's stockbroker. Suppose that Alice tells Bob to buy a certain stock or bond. Immediately thereafter, the price drops sharply. To repudiate her message to Bob, Alice runs to the police claiming that her home was burglarized and the PC holding her key was stolen. Depending on the laws in her state or country, she may or may not be legally liable, especially if she claims not to have discovered the break-in until getting home from work, several hours after it allegedly happened. Another problem with the signature scheme is what happens if Alice decides to change her key. Doing so is clearly legal, and it is probably a good idea to do so periodically. If a court case later arises, as described above, the judge will apply the current EA to DA, P, and discover that it does not produce P. Bob will look pretty stupid at this point. In principle, any public key algorithm can be used for digital signatures. The de facto industry standard is the RSA algorithm. Many security products use it. However, in 1991, NIST proposed using a variant of the LGAML public key algorithm for its new digital signature standard, DSS. LGAML gets its security from the difficulty of computing discrete logarithms, rather than from the difficulty of factoring large numbers. As usual when the government tries to dictate cryptographic standards, there was an uproar. DSS was criticized for being too secret. NSA designed the protocol for using LGAML. Too slow, 10 to 40 times slower than RSA for checking signatures. 3. Too new. LGAML had not yet been thoroughly analyzed. 4. Too insecure. Fixed 512-bit key. In a subsequent revision, the fourth point was rendered moot when keys up to 1024 bits were allowed. Nevertheless, the first 2 points remain valid. 8.4.3 Message digests. One criticism of signature methods is that they often couple two distinct functions, authentication and secrecy. Often, authentication is needed, but secrecy is not always needed. Also, getting an export license is often easier if the system in question provides only authentication but not secrecy. Below we will describe an authentication scheme that does not require encrypting the entire message. This scheme is based on the idea of a one-way hash function that takes an arbitrarily long piece of plain text and from it computes a fixed length bit string. This hash function, MD, often called a message digest, has 4 important properties. 1. Given P, it is easy to compute MD, P. 2. Given MD, P, it is effectively impossible to find P3. Given P, no one can find P, such that MD, P, equals MD, P. 4. A change to the input of even 1 bit produces a very different output. To meet criterion 3, the hash should be at least 128 bits long, preferably more. To meet criterion 4, the hash must mangle the bits very thoroughly, not unlike the symmetric key encryption algorithms we have seen. Computing a message digest from a piece of plain text is much faster than encrypting that plain text with a public key algorithm, so message digests can be used to speed up digital signature algorithms. To see how this works, consider the signature protocol of figure 8 to 18 again. Instead of signing P with KBB, A, T, P, BB now computes the message digest by applying MD to P, yielding MD, P. BB then encloses KBB, A, T, MD, P as the 5th item in the list encrypted with KB that is sent to Bob instead of KBB, A, T, P. If a dispute arises, Bob can produce both P and KBB, A, T, MD, P. After Big Brother has decrypted it for the judge, Bob has MD, P, which is guaranteed to be genuine, and the alleged P. However, since it is effectively impossible for Bob to find any other message that gives this hash, the judge will easily be convinced that Bob is telling the truth. Using message digests in this way saves both encryption time and message transport costs. Message digests work in public key cryptosystems too, as shown in figure 8.20. Here, Alice first computes the message digest of her plain text. She then signs the message digest and sends both the signed digest and the plain text to Bob. If Trudy replaces P along the way, Bob will see this when he computes MD, P. P, DA, MD, P, Bob Alice figure 8 to 20. Digital signatures using message digests. SHA-1 and SHA-2 a variety of message digest functions have been proposed. One of the most widely used functions is SHA-1, Secure Hash Algorithm 1, NIST, 1993. Like all message digests, it operates by mangling bits in a sufficiently complicated way that every output bit is affected by every input bit. SHA-1 was developed by NSA and blessed by NIST in FIPS 180:1. It processes input data in 512-bit blocks, and it generates a 160-bit message digest. A typical way for Alice to send a non-secret, but signed message to Bob is illustrated in figure 8-21. Here, her plain text message is fed into the SHA-1 algorithm to get a 160-bit SHA-1 hash. Alice then signs the hash with her RSA private key and sends both the plain text message and the signed hash to Bob. SHA-1 algorithm H 160-bit SHA-1 hash of MDA, H, signed hash RSA algorithm Alice's private key, DA sent to Bob Alice's plain text message M, arbitrary length, figure 8-21. Use of SHA-1 and RSA for signing non-secret messages. After receiving the message, Bob computes the SHA-1 hash himself and also applies Alice's public key to the signed hash to get the original hash, H. If the two agree, the message is considered valid. Since there is no way for Trudy to modify the plain text message while it is in transit and produce a new one that hashes to H, Bob can easily detect any changes Trudy has made to the message. For messages whose integrity is important, but whose contents are not secret, the scheme of figure 8-21 is widely used. For a relatively small cost in computation, it guarantees that any modifications made to the plain text message in transit can be detected with very high probability. Now let us briefly see how SHA-1 works. It starts out by padding the message by adding a 1 bit to the end, followed by as many 0 bits as are necessary, but at least 64, to make the length a multiple of 512 bits. Then a 64-bit number containing the message length before padding is ordered into the low order 64 bits. In figure 8-22, the message is shown with padding on the right because English text and figures go from left to right, that is, the lower right is generally perceived as the end of the figure. With computers, this orientation corresponds to big endian machines such as the SPARC and the IBM 360 and its successors, but SHA-1 always pads the end of the message, no matter which endian machine is used. Figure 8-22. A message padded out to a multiple of 512 bits, B, the output variables, C, the word array. During the computation, SHA-1 maintains 5 32-bit variables, H0 through H4, where the hash accumulates. These are shown in figure 8-22, B. They are initialized to constants specified in the standard. Each of the blocks M0 through Mn?1 is now processed in turn. For the current block, the 16 words are first copied into the start of an auxiliary 80-word array, W, as shown in figure 8-22, C. Then the other 64 words in W are filled in using the formula W equals S1, W question mark, 3s or W question mark, 8s or W question mark, 14s or W, 16, 16, I, 79, where SB, W, represents the left circular rotation of the 32-bit word W by B bits. Now 5 scratch variables, or through E, are initialized from H0 through H4, respectively. The actual calculation can be expressed in pseudo-C as 4, I equals 0, I, 80, I++, temp equals S5, A, plus V, B, C, D, plus C plus W plus key, E equals D, D equals C, C equals S30, B, B equals A, R equals temp, where the key constants are defined in the standard. The mixing functions phi are defined as phi, B, C, D, equals, B, and C, or, not B and D, 0, I, 19, phi, B, C, D, equals B's or C's or D, 20, I, 39, phi, B, C, D, equals, B, and C, or, B and D, or, C and D, 40, I, 59, phi b c d equals b's or c's or d 60 I 79 when all 80 iterations of the loop are completed or through e are added to h0 through h4 respectively. Now that the first 512-bit block has been processed, the next one has started. The W array is reinitialized from the new block, but H is left as it was. When this block is finished, the next one has started, and so on, until all the 512-bit message blocks have been tossed into the soup. When the last block has been finished, the 532-bit words in the H array are output as the 160-bit cryptographic hash. The complete C code for SHA-1 is given in RFC 3174. New versions of SHA-1 have been developed that produce hashes of 224, 256, 384, and 512 bits. Collectively, these versions are called SHA-2. Not only are these hashes longer than SHA-1 hashes, but the digest function has been changed to combat some potential weaknesses of SHA-1. SHA-2 is not yet widely used, but it is likely to be in the future. MD5 for completeness, we will mention another digest that is popular. MD5, Rivest, 1992, is the fifth in a series of message digests designed by Ronald Rivest. Very briefly, the message is padded to a length of 448 bits, modulo 512. Then the original length of the message is appended as a 64-bit integer, to give a total input whose length is a multiple of 512 bits. Each round of the computation takes a 512-bit block of input and mixes it thoroughly with a running 128-bit buffer. For good measure, the mixing uses a table constructed from the sign function. The point of using an own function is to avoid any suspicion that the designer built in a clever backdoor through which only he can enter. This process continues until all the input blocks have been consumed. The contents of the 128-bit buffer form the message digest. After more than a decade of solid use and study, weaknesses in MD5 have led to the ability to find collisions or different messages with the same hash, Sotorov, and others, 2008. This is the death knell for a digest function, because it means that the digest cannot safely be used to represent a message. Thus, the security community considers MD5 to be broken, it should be replaced where possible, and no new systems should use it as part of their design. Nevertheless, you may still see MD5 used in existing systems 8.4. For the birthday attack in the world of crypto, nothing is ever what it seems to be. One might think that it would take on the order of 2-meter operations to subvert an M-bit message digest. In fact, 2M/2 operations will often be using the birthday attack, an approach published by Yuval, 1979, in his now classic paper How to Swindle Rabin. The idea for this attack comes from a technique that math professors often use in their probability courses. The question is, how many students do you need in a class before the probability of having two people with the same birthday exceeds 1/2? Most students expect the answer to be way over 100. In fact, probability theory says it is just 23. Without giving a rigorous analysis, intuitively, with 23 people, we can form 23x22/2 equals 253 different pairs, each of which has a probability of 1/365 of being a hit. In this light, it is not really so surprising anymore. More generally, if there is some mapping between inputs and outputs within inputs, people, messages, etc., and k possible outputs, birthdays, message digests, etc., there are n1/2 input pairs. If n1/2 k, the chance of having at least one match is pretty good. Thus, approximately, a match is likely for n/k. This result means that a 64-bit message digest can probably be broken by generating about 232 messages and looking for two with the same message digest. Let us look at a practical example. The Department of Computer Science at State University has one position for a tenured faculty member and two candidates, Tom and Dick. Tom was hired 2 years before Dick, so he goes up for a view first. If he gets it, Dick is out of luck. Tom knows that the department chairperson, Marilyn, thinks highly of his work, so he asks her to write him a letter of recommendation to the dean, who will decide on Tom's case. Once sent, all letters become confidential. Marilyn tells her secretary, Ellen, to write the dean a letter outlining what she wants in it. When it is ready, Marilyn will review it, compute and sign the 64-bit digest, and send it to the dean. Ellen can send the letter later by email. Unfortunately for Tom, Ellen is romantically involved with Dick, and would like to do Tom in, so she writes the following letter with the 32 bracketed options. Dear Dean Smith, this letter vertical bar message is to give my honest vertical bar frank opinion of Professor Tom Wilson, who is a candidate vertical bar up for tenure, now vertical bar this year. I have known vertical bar worked with Professor Wilson for about vertical bar almost 6 years. He is an outstanding vertical bar excellent researcher of great talent vertical bar ability, known worldwide vertical bar internationally for his brilliant vertical bar creative insights into many vertical bar a wide variety of difficult vertical bar challenging problems. He is also a highly vertical bar greatly respected vertical bar admired teacher vertical bar educator. His students give his classes vertical bar courses, rave vertical bar spectacular reviews. He is our vertical bar the department's most popular vertical bar best loved teacher vertical bar instructor. In addition vertical bar additionally, Professor Wilson is a gifted vertical bar effective fundraiser. His grants vertical bar contracts have brought a large vertical bar substantial amount of money into the vertical bar our department. This money has vertical bar these funds have enabled vertical bar permitted us to pursue vertical bar carry out many special vertical bar important programs such as vertical bar for example your state 2000 program. Without these funds we would be unable vertical bar not be able to continue this program, which is so important vertical bar essential to both of us. I strongly urge you to grant him tenure. Unfortunately for Tom, as soon as Ellen finishes composing and typing in this letter, she also writes a second one. Dear Dean Smith, this letter vertical bar message is to give my honest vertical bar frank opinion of Professor Tom Wilson, who is a candidate vertical bar up for tenure, now vertical bar this year. I have known vertical bar worked with Tom for about vertical bar almost 6 years. He is a poor vertical bar weak researcher not well known in his field vertical bar area. His research hardly ever vertical bar early shows insight in vertical bar understanding of the key vertical bar major problems of the vertical bar our day. Furthermore, he is not a respected vertical bar admired teacher vertical bar educator. His students give his classes vertical bar courses, poor vertical bar bad reviews. He is our vertical bar the department's least popular teacher vertical bar instructor, known mostly vertical bar primarily within the vertical bar our department for his tendency vertical bar propensity to ridicule vertical bar embarrass students, foolish vertical bar imprudent enough to ask questions in his classes. In addition vertical bar additionally, Tom is a poor vertical bar marginal fundraiser. His grants vertical bar contracts have brought only a meager vertical bar insignificant amount of money into the vertical bar our department. Unless new money is vertical bar funds are quickly located, we may have to cancel some essential programs, such as your State 2000 program. Unfortunately, under these conditions vertical bar circumstances, I cannot in good conscience vertical bar faith recommend him to you for tenure vertical bar a permanent position. Now Ellen programs her computer to compute the 232 message digests of each letter overnight. Chances are, one digest of the first letter will match one digest of the second. If not, she can add a few more options and try again tonight. Suppose that she finds a match. call the good letter A and the bad one B. Ellen now emails letter A to Marilyn for approval. Letter B she keeps secret, showing it to no one. Marilyn, of course, approves it, computes a 64-bit message digest, signs the digest, and emails a signed digest off to Dean Smith. Independently, Ellen emails letter B to the Dean, not letter A, as she is supposed to. After getting the letter and signed message digest, the Dean runs the message digest algorithm on letter B, sees that it agrees with what Marilyn sent him, and fires Tom. The Dean does not realize that Ellen managed to generate 2 letters with the same message digest and sent her a different one than the one Marilyn saw and approved. Optional ending. Ellen tells Dick what she did. Dick is appalled and breaks off the affair. Ellen is furious and confesses to Marilyn. Marilyn calls the Dean. Tom gets tenure after all. With SHA-1, the birthday attack is difficult because even at the ridiculous speed of 1 trillion digests per second, it would take over 32,000 years to compute all 280 digests of 2 letters with 80 variants each, and even then a match is not guaranteed. With a cloud of 1 million chips working in parallel, 32,000 years becomes 2 weeks. 8.5 Management of public keys. Public key cryptography makes it possible for people who do not share a common key in advance to nevertheless communicate securely. It also makes signing messages possible without the presence of a trusted third party. Finally, signed message digests make it possible for the recipient to verify the integrity of received messages easily and securely. However, there is one problem that we have glossed over a bit too quickly. If Alice and Bob do not know each other, how do they get each other's public keys to start the communication process? The obvious solution: put your public key on your website does not work for the following reason. Suppose that Alice wants to look up Bob's public key on his website. How does she do it? She starts by typing in Bob's URL. Her browser then looks up the DNS address of Bob's homepage and sends it a GET request, as shown in figure 8 to 23. Unfortunately, Trudy intercepts the request and replies with a fake homepage, probably a copy of Bob's homepage except for the replacement of Bob's public key with Trudy's public key. When Alice now encrypts her first message with it, Trudy decrypts it, reads it, re-encrypts it with Bob's public key, and sends it to Bob, who is none the wiser that Trudy is reading his incoming messages. Worse yet, Trudy could modify the messages before re-encrypting them for Bob. Clearly, some mechanism is needed to make sure that public keys can be exchanged securely. For message, Alice Trudy 1. Get Bob's homepage 2. Fake homepage with 3. Message, Bob figure 8 to 23. A way for Trudy to subvert public key encryption. 8.5.1 certificates. As a first attempt at distributing public keys securely, we could imagine a KDC key distribution center available online 24 hours a day to provide public keys on demand. One of the many problems with this solution is that it is not scalable, and the key distribution center would rapidly become a bottleneck. Also, if it ever went down, internet security would suddenly grind to a halt. For these reasons, people have developed a different solution, one that does not require the key distribution center to be online all the time. In fact, it does not have to be online at all. Instead, what it does is certify the public keys belonging to people, companies, and other organizations. An organization that certifies public keys is now called a CA, Certification Authority. As an example, suppose that Bob wants to allow Alice and other people he does not know to communicate with him securely. He can go to the CA with his public key along with his passport or driver's license and ask to be certified. The CA then issues a certificate similar to the one in figure 8 to 24 and signs its SHA-1 hash with the CA's private key. Bob then pays the CA's fee and gets a CD-ROM containing the certificate and its signed hash. I hereby certify that the public key 19836 R8B03030CF83737 E3837837 FC3S87009,282,726,264 3FFA 82,710,382,828,282 belongs to Robert John Smith 12,345 University Avenue Berkeley, California 9470 birthday, July 4, 1958. Email, bob@superdupernet.com #1 of the above certificate, signed with the CA's private key figure 8 to 24. A possible certificate and its signed hash. The fundamental job of a certificate is to bind a public key to the name of a principal, individual, company, etc. Certificates themselves are not secret or protected. Bob might, for example, decide to put his new certificate on his website, with a link on the main page saying, "Click here for my public key certificate." The resulting click would return both the certificate and the signature block, the signed #1 of the certificate. Now let us run through the scenario of figure 8 to 23 again. When Trudy intercepts Alice's request for Bob's homepage, what can she do? She can put her own certificate and signature block on the fake page, but when Alice reads the contents of the certificate she will immediately see that she is not talking to Bob, because Bob's name is not in it. Trudy can modify Bob's homepage on the fly, replacing Bob's public key with her own. However, when Alice runs the SHA-1 algorithm on the certificate, she will get a hash that does not agree with the one she gets when she applies the CA's well-known public key to the signature block. Since Trudy does not have the CA's private key, she has no way of generating a signature block that contains the hash of the modified web page with her public key on it. In this way, Alice can be sure she has Bob's public key, and not Trudy's or someone else's. And as we promised, this scheme does not require the CA to be online for verification, thus eliminating a potential bottleneck. While the standard function of a certificate is to bind a public key to a principal, a certificate can also be used to bind a public key to an attribute. For example, a certificate could say, "This public key belongs to someone over 18. It could be used to prove that the owner of the private key was not a minor and thus allowed to access material not suitable for children, and so on, but without disclosing the owner's identity. Typically, the person holding the certificate would send it to the website, principal, or process that cared about age. That site, principal, or process would then generate a random number and encrypt it with the public key in the certificate. If the owner were able to decrypt it and send it back, that would be proof that the owner indeed had the attribute stated in the certificate. Alternatively, the random number could be used to generate a session key for the ensuing conversation. Another example of where a certificate might contain an attribute is in an object-oriented distributed system. Each object normally has multiple methods. The owner of the object could provide each customer with a certificate giving a bitmap of which methods the customer is allowed to invoke, and binding the bitmap to a public key using a signed certificate. Again, if the certificate holder can prove possession of the corresponding private key, he will be allowed to perform the methods in the bitmap. This approach has the property that the owner's identity need not be known, a property useful in situations where privacy is important. 8.5.2x509. If everybody who wanted something signed went to the CA with a different kind of certificate, managing all the different formats would soon become a problem. To solve this problem, a standard for certificates has been devised and approved by ITU. The standard is called X509 and is in widespread use on the internet. It has gone through 3 versions since the initial standardization in 1988. We will discuss V3. X509 has been heavily influenced by the OC world, borrowing some of its worst features, for instance, naming and encoding. Surprisingly, IETF went along with X509, even though in nearly every other area, from machine addresses to transport protocols to email formats, IETF generally ignored OC and tried to do it right. The IETF version of X509 is described in RFC 5280. At its core, X509 is a way to describe certificates. The primary fields in a certificate are listed in figure 8 to 25. The descriptions given there should provide a general idea of what the fields do. For additional information, please consult the standard itself or RFC 2459. For example, if Bob works in the loan department of the money bank, his X500 address might be /C=US/OEquals/MONEYBANK/OU=LOAN/CN=BOB/ where C is for country, O is for organization, OU is for organizational unit, and CN is for common name. CAs and other entities are named in a similar way. A substantial problem with X500 names is that if Alice is trying to contact Bob at moneybank.com and is given a certificate with an X500 name, it may not be obvious to her that the certificate refers to the Bob she wants. Fortunately, starting with version 3, DNS names are now permitted instead of X500 names, so this problem may eventually vanish. Certificates are encoded using OCASN1, Abstract Syntax Notation 1, which is sort of like a struct in C, except with a extremely peculiar and verbose notation. More information about X509 is given by Tanenbaum, 2000. Field meaning version. Which version of X509 serial number? This number plus the CA's name uniquely identifies the certificate signature algorithm. The algorithm used to sign the certificate issuer X500 name of the CA validity period, the starting and ending times of the validity period, subject name, the entity whose key is being certified, public key, the subject's public key, and the idea of the algorithm using it, issuer ID and optional ID uniquely identifying the certificate's issuer, subject ID and optional ID uniquely identifying the certificate's subject. Extensions. Many extensions have been defined. Signature, the certificate's signature, signed by the CA's private key, figure 8 to 25. The basic fields of an X509 certificate. 8.5.3 Public key infrastructures. Having a single CA to issue all the world's certificates obviously would not work. It would collapse under the load and be a central point of failure as well. A possible solution might be to have multiple CAs, all run by the same organization and all using the same private key to sign certificates. While this would solve the load and failure problems, it introduces a new problem: key leakage. If there were dozens of servers spread around the world, all holding the CA's private key, the chance of the private key being stolen or otherwise leaking out would be greatly increased. Since the compromise of this key would ruin the world's electronic security infrastructure, having a single central CA is very risky. In addition, which organization would operate the CA? It is hard to imagine any authority that would be accepted worldwide as legitimate and trustworthy. In some countries, people would insist that it be a government, while in other countries they would insist that it not be a government. For these reasons, a different way for certifying public keys has evolved. It goes under the general name of PKI, Public Key Infrastructure. In this section, we will summarize how it works in general, although there have been many proposals, so the details will probably evolve in time. A PKI has multiple components, including users, CAs, certificates, and directories. What the PKI does is provide a way of structuring these components and define standards for the various documents and protocols. A particularly simple form of PKI is a hierarchy of CAs, as depicted in figure 8 to 26. In this example we have shown 3 levels, but in practice there might be fewer or more. The top level CA, the root, certifies second level CAs, which we here call as regional authorities, because they might cover some geographic region, such as a country or continent. This term is not standard, though. In fact, no term is really standard for the different levels of the tree. These in turn certify the real CAs, which issue the X509 certificates to organizations and individuals. When the root authorizes a new RAP, it generates an X509 certificate stating that it has approved the RAP, includes the new RAS public key in it, signs it, and hands it to the RAP. Similarly, when an RA approves a new CA, it produces and signs a certificate stating its approval and containing the CA's public key. CA1, CA2, B, CA3, CA4, CA5, RA2 is approved. Its public key is 47,383 AE 349. Root's signature RA1 root RA2 is approved. Its public key is 47,383 AE349. Root's signature CA5 is approved. Its public key is 6384 AF863B. RATU's signature CA5 is approved. Its public key is 6384 AF863B. RATU's signature figure 8 to 26. A hierarchical PKI. B. A chain of certificates. Our PKI works like this. Suppose that Alice needs Bob's public key in order to communicate with him, so she looks for and finds a certificate containing it, signed by CA5. But Alice has never heard of CA5. For all she knows, CA5 might be Bob's 10-year-old daughter. She could go to CA5 and say, "Prove your legitimacy." CA5 will respond with the certificate it got from RATU, which contains CA5's public key. Now armed with CA5's public key, she can verify that Bob's certificate was indeed signed by CA5 and is thus legal. Unless RATU is Bob's 12-year-old son. So, the next step is for her to ask RATU to prove it is legitimate. The response to her query is a certificate signed by the root and containing RATU's public key. Now Alice is sure she has Bob's public key. But how does Alice find the root's public key? Magic. It is assumed that everyone knows the root's public key. For example, her browser might have been shipped with the root's public key built in. Bob is a friendly sort of guy and does not want to cause Alice a lot of work. He knows that she is going to have to check out CA5 and RATU, so to save her some trouble, he collects the 2 needed certificates and gives her the 2 certificates along with his. Now she can use her own knowledge of the root's public key to verify the top level certificate and the public key contained therein to verify the second one. Alice does not need to contact anyone to do the verification. Because the certificates are all signed, she can easily detect any attempts to tamper with their contents. A chain of certificates going back to the root like this is sometimes called a chain of trust or a certification path. The technique is widely used in practice. Of course, we still have the problem of who is going to run the root. The solution is not to have a single root, but to have many roots, each with its own RAS and CAs. In fact, modern browsers come preloaded with the public keys for over 100 roots, sometimes referred to as trust anchors. In this way, having a single worldwide trusted authority can be avoided. But there is now the issue of how the browser vendor decides which purported trust anchors are reliable and which are sleazy. It all comes down to the user trusting the browser vendor to make wise choices and not simply approve all trust anchors willing to pay its inclusion fee. Most browsers allow users to inspect the root keys, usually in the form of certificates signed by the root, and delete any that seem shady. Directory is another issue for any PKI, is where certificates and their chains back to some known trust anchor are stored. One possibility is to have each user store his or her own certificates. While doing this is safe, that is, there is no way for users to tamper with signed certificates without detection, it is also inconvenient. One alternative that has been proposed is to use DNS as a certificate directory. Before contacting Bob, Alice probably has to look up his IP address using DNS, so why not have DNS return Bob's entire certificate chain along with his IP address? Some people think this is the way to go, but others would prefer dedicated directory servers whose only job is managing X509 certificates. Such directories could provide lookup services by using properties of the X500 names. For example, in theory such a directory service could answer a query such as, "Give me a list of all people named Alice who work in sales departments anywhere in the US or Canada." Revocation. The real world is full of certificates too, such as passports and driver's licenses. Sometimes these certificates can be revoked. For example, driver's licenses can be revoked for drunken driving and other driving offenses. The same problem occurs in the digital world. The grantor of a certificate may decide to revoke it because the person or organization holding it has abused it in some way. It can also be revoked if the subject's private key has been exposed, or, worse yet, the CA's private key has been compromised. Thus, a PKI needs to deal with the issue of revocation. The possibility of revocation complicates matters. A first step in this direction is to have each CA periodically issue a CRL, certificate revocation list, giving the serial numbers of all certificates that it has revoked. Since certificates contain expiry times, the CRL need only contain the serial numbers of certificates that have not yet expired. Once its expiry time has passed, a certificate is automatically invalid, so no distinction is needed between those that just timed out and those that were actually revoked. In both cases, they cannot be used anymore. Unfortunately, introducing CRLs means that a user who is about to use a certificate must now acquire the CRL to see if the certificate has been revoked. If it has been, it should not be used. However, even if the certificate is not on the list, it might have been revoked just after the list was published. Thus, the only way to really be sure is to ask the CA. And on the next use of the same certificate, the CA has to be asked again, since the certificate might have been revoked a few seconds ago. Another complication is that a revoked certificate could conceivably be reinstated, for example, if it was revoked for non-payment of some fee that has since been paid. Having to deal with revocation and possibly reinstatement eliminates one of the best properties of certificates, namely, that they can be used without having to contact a CA. Where should CRLs be stored? A good place would be the same place the certificates themselves are stored. One strategy is for the CA to actively push out CRLs periodically and have the directories process them by simply removing the revoked certificates. If directories are not used for storing certificates, the CRLs can be cached at various places around the network. Since a CRL is itself a signed document, if it is tampered with, that tampering can be easily detected. If certificates have long lifetimes, the CRLs will be long too. For example, if credit cards are valid for 5 years, the number of revocations outstanding will be much longer than if new cards are issued every 3 months. A standard way to deal with long CRLs is to issue a master list infrequently, but issue updates to it more often. Doing this reduces the bandwidth needed for distributing the CRLs. 8.6 Communication Security. We have now finished our study of the tools of the trade. Most of the important techniques and protocols have been covered. The rest of the chapter is about how these techniques are applied in practice to provide network security, plus some thoughts about the social aspects of security at the end of the chapter. In the following 4 sections, we will look at communication security, that is, how to get the bits secretly and without modification from source to destination, and how to keep unwanted bits outside the door. These are by no means the only security issues in networking, but they are certainly among the most important ones, making this a good place to start our study. 8.6.1 IPsec IETF has known for years that security was lacking in the internet. Adding it was not easy because a war broke out about where to put it. Most security experts believe that to be really secure, encryption and integrity checks have to be end-to-end, that is, in the application layer. That is, the source process encrypts and/or integrity protects the data and sends them to the destination process, where they are decrypted and/or verified. Any tampering done in between these two processes, including within either operating system, can then be detected. The trouble with this approach is that it requires changing all the applications to make them security aware. In this view, the next best approach is putting encryption in the transport layer, or in a new layer between the application layer and the transport layer, making it still end-to-end, but not requiring applications to be changed. The opposite view is that users do not understand security and will not be capable of using it correctly, and nobody wants to modify existing programs in any way, so the network layer should authenticate and/or encrypt packets without the users being involved. After years of pitched battles, this view won enough support that a network layer security standard was defined. In part, the argument was that having network layer encryption does not prevent security aware users from doing it, right, and it does help security unaware users to some extent. The result of this war was a design called IPsec, IP security, which is described in RFCs 2401, 2402, and 2406, among others. Not all users want encryption, because it is computationally expensive. Rather than make it optional, it was decided to require encryption all the time, but permit the use of a null algorithm. The null algorithm is described and praised for its simplicity, ease of implementation, and great speed in RFC 2410. The complete IPsec design is a framework for multiple services, algorithms, and granularities. The reason for multiple services is that not everyone wants to pay the price for having all the services all the time, so the services are available a la carte. The major services are secrecy, data integrity, and protection from replay attacks, where the intruder replays a conversation. All of these are based on symmetric-key cryptography, because high performance is crucial. The reason for having multiple algorithms is that an algorithm that is now thought to be secure may be broken in the future. By making IPsec algorithm independent, the framework can survive, even if some particular algorithm is later broken. The reason for having multiple granularities is to make it possible to protect a single TCP connection, all traffic between a pair of hosts, or all traffic between a pair of secure routers, among other possibilities. One slightly surprising aspect of IPsec is that, even though it isn't the IP layer, it is connection oriented. Actually, that is not so surprising, because to have any security, a key must be established and used for some period of time, in essence, a kind of connection by a different name. Also, connections amortize the setup costs over many packets. A connection in the context of IPsec is called an SAP, Security Association. An SAP is a simplex connection between two endpoints, and has a security identifier associated with it. If secure traffic is needed in both directions, two security associations are required. Security identifiers are carried in packets traveling on these secure connections, and are used to look up keys and other relevant information when a secure packet arrives. Technically, IPsec has two principal parts. The first part describes two new headers that can be added to packets to carry the security identifier, integrity control data, and other information. The other part, ISAKMP, Internet Security Association and Key Management Protocol, deals with establishing keys. ISAKMP is a framework. The main protocol for carrying out the work is IKE, Internet Key Exchange. Version 2 of IKE as described in RFC 4306 should be used, as the earlier version was deeply flawed, as pointed out by Perelman and Kaufman, 2000. IPsec can be used in either of two modes. In transport mode, the IPsec header is inserted just after the IP header. The protocol field in the IP header is changed to indicate that an IPsec header follows the normal IP header before the TCP header. The IPsec header contains security information, primarily the SA identifier, a new sequence number, and possibly an integrity check of the payload. In tunnel mode, the entire IP packet, header and all, is encapsulated in the body of a new IP packet with a completely new IP header. Tunnel mode is useful when the tunnel ends at a location other than the final destination. In some cases, the end of the tunnel is a security gateway machine, for example, a company firewall. This is commonly the case for a VPN, virtual private network. In this mode, the security gateway encapsulates and decapsulates packets as they pass through it. By terminating the tunnel at this secure machine, the machines on the company LAN do not have to be aware of IPsec. Only the security gateway has to know about it. Tunnel mode is also useful when a bundle of TCP connections is aggregated and handled as one encrypted stream, because it prevents an intruder from seeing who is sending how many packets to whom. Sometimes just knowing how much traffic is going where is valuable information. For example, if during a military crisis, the amount of traffic flowing between the Pentagon and the White House were to drop sharply, but the amount of traffic between the Pentagon and some military installation deep in the Colorado Rocky Mountains were to increase by the same amount, an intruder might be able to deduce some useful information from these data. Studying the flow patterns of packets, even if they are encrypted, is called traffic analysis. tunnel mode provides a way to foil it to some extent. The disadvantage of tunnel mode is that it adds an extra IP header, thus increasing packet size substantially. In contrast, transport mode does not affect packet size as much. The first new header is our authentication header. It provides integrity checking and interplay security, but not secrecy, that is, no data encryption. The use of R in transport mode is illustrated in figure 8-27. In IPv4, it is interposed between the IP header, including any options, and the TCP header. In IPv6, it is just another extension header, and is treated as such. In fact, the format is close to that of a standard IPv6 extension header. The payload may have to be padded out to some particular length for the authentication algorithm, as shown. IP header are 32-bit security parameters index next header payload len, reserved, sequence number authentication data, HMAC, TCP header authenticated payload plus padding figure 8-27. The IPsec authentication header in transport mode for IPv4. Let us now examine the R header. The next header field is used to store the value that the IP protocol field had before it was replaced with 51 to indicate that an R header follows. In most cases, the code for TCP/6 will go here. The payload length is the number of 32-bit words in the R header -2. The security parameters index is the connection identifier. It is inserted by the sender to indicate a particular record in the receiver's database. This record contains the shared key used on this connection and other information about the connection. If this protocol had been invented by ITA rather than IETF, this field would have been called virtual circuit number. The sequence number field is used to number all the packets sent on and SAP. Every packet gets a unique number, even retransmissions. In other words, the retransmission of a packet gets a different number here than the original, even though its TCP sequence number is the same. The purpose of this field is to detect replay attacks. These sequence numbers may not wrap around. If all 232 are exhausted, a new SAM must be established to continue communication. Finally, we come to authentication data, which is a variable length field that contains the payload's digital signature. When the SAM is established, the two sides negotiate which signature algorithm they are going to use. Normally, public key cryptography is not used here because packets must be processed extremely rapidly and all known public key algorithms are too slow. Since IPsec is based on symmetric key cryptography and the sender and receiver negotiate a shared key before setting up NSAP, the shared key is used in the signature computation. One simple way is to compute the hash over the packet plus the shared key. The shared key is not transmitted, of course. A scheme like this is called an HMAC, hashed message authentication code. It is much faster to compute than first running SHA-1 and then running RSA on the result. The R header does not allow encryption of the data, so it is mostly useful when integrity checking is needed, but secrecy is not needed. One noteworthy feature of R is that the integrity check covers some of the fields in the IP header, namely, those that do not change as the packet moves from router to router. The time to live field changes on each hop, for example, so it cannot be included in the integrity check. However, the IP source address is included in the check, making it impossible for an intruder to falsify the origin of a packet. The alternative IPsec header is ESP, encapsulating security payload. Its use for both transport mode and tunnel mode is shown in figure 8-28. ESP header new IP header rolled IP header TCP header authenticated, B, payload plus padding authentication, HMAC, ESP header IP header TCP, header payload plus padding authentication, HMAC, authenticated encrypted figure 8-28, ESP in transport mode, B, ESP in tunnel mode. The ESP header consists of two 32-bit words. They are the security parameters index and sequence number fields that we saw in R. A third word that generally follows them, but is technically not part of the header, is the initialization vector used for the data encryption, unless null encryption is used, in which case it is omitted. ESP also provides for HMAC integrity checks, as does R, but rather than being included in the header, they come after the payload, as shown in figure 8 to 28. Putting the HMAC at the end has an advantage in a hardware implementation. The HMAC can be calculated as the bits are going out over the network interface and appended to the end. This is why Ethernet and other LANs have their CRCs in a trailer rather than in a header. With R, the packet has to be buffered and the signature computed before the packet can be sent, potentially reducing the number of packets/secretary that can be sent. Given that ESP can do everything R can do, and more and is more efficient to boot, the question arises, why bother having R at all? The answer is mostly historical. Originally, R handled only integrity and ESP handled only secrecy. Later, integrity was added to ESP, but the people who designed R did not want to let it die after all that work. Their only real argument is that R checks part of the IP header, which ESP does not, but other than that, it is really a weak argument. Another weak argument is that a product supporting R, but not ESP, might have less trouble getting an export license because it cannot do encryption. R is likely to be phased out in the future. 8.6.2 firewalls the ability to connect any computer, anywhere, to any other computer, anywhere, is a mixed blessing. For individuals at home, wandering around the internet is lots of fun. For corporate security managers, it is a nightmare. Most companies have large amounts of confidential information, online trade secrets, product development plans, marketing strategies, financial analyses, etc. Disclosure of this information to a competitor could have dire consequences. In addition to the danger of information leaking out, there is also a danger of information leaking in. In particular, viruses, worms, and other digital pests can breach security, destroy valuable data, and waste large amounts of administrators' time trying to clean up the mess they leave. Often they are imported by careless employees who want to play some nifty new game. Consequently, mechanisms are needed to keep good bits in and bad bits out. One method is to use IPsec. This approach protects data in transit between secure sites. However, IPsec does nothing to keep digital pests and intruders from getting onto the company LAN. To see how to accomplish this goal, we need to look at firewalls. Firewalls are just a modern adaptation of that old medieval security standby, digging a deep moat around your castle. This design forced everyone entering or leaving the castle to pass over a single drawbridge, where they could be inspected by the I/O police. With networks, the same trick is possible. A company can have many LANs connected in arbitrary ways, but all traffic to or from the company is forced through an electronic drawbridge, firewall, as shown in figure 8 to 29. No other route exists. Internal network demilitarized zone, external internet email server, web server, security perimeter, firewall, figure 8 to 29. A firewall protecting an internal network. The firewall acts as a packet filter. It inspects each and every incoming and outgoing packet. Packets meeting some criterion described in rules formulated by the network administrator are forwarded normally. Those that fail the test are unceremoniously dropped. The filtering criterion is typically given as rules or tables that list sources and destinations that are acceptable, sources and destinations that are blocked, and default rules about what to do with packets coming from or going to other machines. In the common case of a TCP/IP setting, a source or destination might consist of an IP address and a port. Ports indicate which service is desired. For example, TCP port 25 is for mail, and TCP port 80 is for HTTP. Some ports can simply be blocked. For example, a company could block incoming packets for all IP addresses combined with TCP port 79. It was once popular for the finger service to look up people's email addresses, but is little used today. Other ports are not so easily blocked. The difficulty is that network administrators want security, but cannot cut off communication with the outside world. That arrangement would be much simpler and better for security, but there would be no end to user complaints about it. This is where arrangements such as the DMZ, Demilitarized Zone, shown in figure 8 to 29 come in handy. The DMZ is the part of the company network that lies outside of the security perimeter. Anything goes here. By placing a machine such as a web server in the DMZ, computers on the internet can contact it to browse the company website. Now the firewall can be configured to block incoming TCP traffic to port 80 so that computers on the internet cannot use this port to attack computers on the internal network. To allow the web server to be managed, the firewall can have a rule to permit connections between internal machines and the web server. Firewalls have become much more sophisticated over time and an arms race with attackers. Originally, firewalls applied a rule set independently for each packet, but it proved difficult to write rules that allowed useful functionality but blocked all unwanted traffic. Stateful firewalls map packets to connections and use TCP/IP header fields to keep track of connections. This allows for rules that, for example, allow an external web server to send packets to an internal host, but only if the internal host first establishes a connection with the external web server. Such a rule is not possible with stateless designs that must either pass or drop all packets from the external web server. Another level of sophistication up from stateful processing is for the firewall to implement application level gateways. This processing involves the firewall looking inside packets, beyond even the TCP header, to see what the application is doing. With this capability, it is possible to distinguish HTTP traffic used for web browsing from HTTP traffic used for peer-to-peer file sharing. Administrators can write rules to spare the company from peer-to-peer file sharing, but allow web browsing that is vital for business. For all of these methods, outgoing traffic can be inspected as well as incoming traffic, for example, to prevent sensitive documents from being emailed outside of the company. As the above discussion should make clear, firewalls violate the standard layering of protocols. They are network layer devices, but they peek at the transport and applications layers to do their filtering. This makes them fragile. For instance, firewalls tend to rely on standard port numbering conventions to determine what kind of traffic is carried in a packet. Standard ports are often used, but not by all computers, and not by all applications either. Some peer-to-peer applications select ports dynamically to avoid being easily spotted and blocked. Encryption with IPsec or other schemes hides higher layer information from the firewall. Finally, a firewall cannot readily talk to the computers that communicate through it to tell them what policies are being applied and why their connection is being dropped. It must simply pretend to be a broken wire. For all these reasons, networking purists consider firewalls to be a blemish on the architecture of the internet. However, the internet can be a dangerous place if you are a computer. Firewalls help with that problem, so they are likely to stay. Even if the firewall is perfectly configured, plenty of security problems still exist. For example, if a firewall is configured to allow in packets from only specific networks, for instance, the company's other plants, an intruder outside the firewall can put in false source addresses to bypass this check. If an insider wants to ship out secret documents, he can encrypt them, or even photograph them, and ship the photos as JPG files, which bypasses any email filters. And we have not even discussed the fact that, although 3/4 of all attacks come from outside the firewall, the attacks that come from inside the firewall, for example, from disgruntled employees, are typically the most damaging. Verizon, 2009. A different problem with firewalls is that they provide a single perimeter of defense. If that defense is breached, all bets are off. For this reason, firewalls are often used in a layered defense. For example, a firewall may guard the entrance to the internal network and each computer may also run its own firewall. Readers who think that one security checkpoint is enough clearly have not made an international flight on a scheduled airline recently. In addition, there is a whole other class of attacks that firewalls cannot deal with. The basic idea of a firewall is to prevent intruders from getting in and secret data from getting out. Unfortunately, there are people who have nothing better to do than try to bring certain sites down. They do this by sending legitimate packets at the target in great numbers until it collapses under the load. For example, to cripple a website, an intruder can send a TCP/SYN packet to establish a connection. The site will then allocate a table slot for the connection and send a SYN plus ACK packet in reply. If the intruder does not respond, the table slot will be tied up for a few seconds until it times out. If the intruder sends thousands of connection requests, all the table slots will fill up, and no legitimate connections will be able to get through. Attacks in which the intruder's goal is to shut down the target, rather than steal data, are called DoS, denial of service, attacks. Usually, the request packets have false source addresses, so the intruder cannot be traced easily. DoS attacks against major websites are common on the internet. An even worse variant is one in which the intruder has already broken into hundreds of computers elsewhere in the world, and then commands all of them to attack the same target at the same time. Not only does this approach increase the intruder's firepower, but it also reduces his chances of detection, since the packets are coming from a large number of machines belonging to unsuspecting users. Such an attack is called a DDoS, distributed denial of service, attack. This attack is difficult to defend against. Even if the attacked machine can quickly recognize a bogus request, it does take some time to process and discard the request, and if enough requests per second arrive, the CPU will spend all its time dealing with them. 8.6.3 Virtual private networks. Many companies have offices and plants scattered over many cities, sometimes over multiple countries. In the olden days, before public data networks, it was common for such companies to lease lines from the telephone company between some or all pairs of locations. Some companies still do this. A network built up from company computers and leased telephone lines is called a private network. Private networks work fine and are very secure. If the only lines available are the leased lines, no traffic can leak out of company locations and intruders have to physically wiretap the lines to break in, which is not easy to do. The problem with private networks is that leasing a dedicated T1 line between 2 points costs thousands of dollars a month, and T3 lines are many times more expensive. When public data networks and later the internet appeared, many companies wanted to move their data, and possibly voice, traffic to the public network, but without giving up the security of the private network. This demand soon led to the invention of VPNs, virtual private networks, which are overlay networks on top of public networks, but with most of the properties of private networks. They are called virtual because they are merely an illusion, just as virtual circuits are not real circuits and virtual memory is not real memory. One popular approach is to build VPNs directly over the internet. A common design is to equip each office with a firewall and create tunnels through the internet between all pairs of offices, as illustrated in figure 8.230. A further advantage of using the internet for connectivity is that the tunnels can be set up on demand to include, for example, the computer of an employee who is at home or traveling as long as the person has an internet connection. This flexibility is much greater than as provided with leased lines, yet from the perspective of the computers on the VPN, the topology looks just like the private network case, as shown in figure 8.230b. When the system is brought up, each pair of firewalls has to negotiate the parameters of its SAP, including the services, modes, algorithms, and keys. If IPsec is used for the tunneling, it is possible to aggregate all traffic between any two pairs of offices onto a single authenticated, encrypted SAP, thus providing integrity control, secrecy, and even considerable immunity to traffic analysis. Many firewalls have VPN capabilities built in. Some ordinary routers can do this as well, but since firewalls are primarily in the security business, it is natural to have the tunnels begin and end at the firewalls, providing a clear separation between the company and the internet. Thus, firewalls, VPNs, and IPsec with ESP in tunnel mode are a natural combination and widely used in practice. Home Internet Paris Office London Office Travel Home Travel London Paris. B. Figure 8.230. A virtual private network. B. Topology as seen from the inside. Once the SAS have been established, traffic can begin flowing. To a router within the internet, a packet traveling along a VPN tunnel is just an ordinary packet. The only thing unusual about it is the presence of the IPsec header after the IP header, but since these extra headers have no effect on the forwarding process, the routers do not care about this extra header. Another approach that is gaining popularity is to have the ISP set up the VPN. Using MPLS, as discussed in Chapter 5, paths for the VPN traffic can be set up across the ISP network between the company offices. These paths keep the VPN traffic separate from other internet traffic, and can be guaranteed a certain amount of bandwidth or other quality of service. A key advantage of a VPN is that it is completely transparent to all user software. The firewalls set up and manage the SAS. The only person who is even aware of this setup is the system administrator, who has to configure and manage the security gateways, or the ISP administrator who has to configure the MPLS paths. To everyone else, it is like having a leased line private network again. For more about VPNs, see Lewis, 2006, 8.6.4 Wireless Security. It is surprisingly easy to design a system using VPNs and firewalls that is logically completely secure, but that, in practice, leaks like a sieve. This situation can occur if some of the machines are wireless and use radio communication, which passes right over the firewall in both directions. The range of 802.11 networks is often a few hundred meters, so anyone who wants to spy on a company can simply drive into the employee parking lot in the morning, leave an 802.11 enabled notebook computer in the car to record everything it hears, and take off for the day. By late afternoon, the hard disk will be full of valuable goodies. Theoretically, this leakage is not supposed to happen. Theoretically, people are not supposed to rob banks either. Much of the security problem can be traced to the manufacturers of wireless base stations, access points, trying to make their products user-friendly. Usually, if the user takes the device out of the box and plugs it into the electrical power socket, it begins operating immediately, nearly always with no security at all, blurting secrets to everyone within radio range. If it is then plugged into an Ethernet, all the Ethernet traffic suddenly appears in the parking lot as well. Wireless is a snooper's dream come true, free data without having to do any work. It therefore goes without saying that security is even more important for wireless systems than for wired ones. In this section, we will look at some ways wireless networks handle security. Some additional information is given by Nichols and Lekas, 2002, 802.11 security, part of the 802.11 standard, originally called 802.11i, prescribes a data link level security protocol for preventing a wireless node from reading or interfering with messages sent between another pair of wireless nodes. It also goes by the trade name WPA2, Wi-Fi Protected Access 2. Plain WPA is an interim scheme that implements a subset of 802.11i. It should be avoided in favor of WPA2. We will describe 802.11i shortly, but will first note that it is a replacement for WEP, Wired Equivalent Privacy, the first generation of 802.11 security protocols. WEP was designed by a Networking Standards Committee, which is a completely different process than, for example, the way NIST selected the design of EASE. The results were devastating. What was wrong with it? Pretty much everything from a security perspective, as it turns out. For example, WEP encrypted data for confidentiality by storing it with the output of a stream cipher. Unfortunately, weak keying arrangements meant that the output was often reused. This led to trivial ways to defeat it. As another example, the integrity check was based on a 32-bit CRC. That is an efficient code for detecting transmission errors, but it is not a cryptographically strong mechanism for defeating attackers. These and other design flaws made WEP very easy to compromise. The first practical demonstration that WEP was broken came when Adam Stubblefield was an intern at AT&T, Stubblefield and others, 2002. He was able to code up and test an attack outlined by Fleur and others, 2001, in 1 week, of which most of the time was spent convincing management to buy him a Wi-Fi card to use in his experiments. Software to crack web passwords within a minute is now freely available, and the use of web is very strongly discouraged. While it does prevent casual access, it does not provide any real form of security. The 802.11i group was put together in a hurry when it was clear that web was seriously broken. It produced a formal standard by June 2004. Now we will describe 802.11i, which does provide real security if it is set up and used properly. There are two common scenarios in which WPA2 is used. The first is a corporate setting, in which a company has a separate authentication server that has a username and password database that can be used to determine if a wireless client is allowed to access the network. In this setting, clients use standard protocols to authenticate themselves to the network. The main standards are 802.1x, with which the access point lets the client carry on a dialogue with the authentication server and observes the result, and DEEP, Extensible Authentication Protocol, RFC 3748, which tells how the client and the authentication server interact. Actually, EAP is a framework and other standards define the protocol messages. However, we will not delve into the many details of this exchange, because they do not much matter for an overview. The second scenario is in a home setting in which there is no authentication server. Instead, there is a single shared password that is used by clients to access the wireless network. This setup is less complex than having an authentication server, which is why it is used at home and in small businesses, but it is less secure as well. The main difference is that with an authentication server, each client gets a key for encrypting traffic that is not known by the other clients. With a single shared password, different keys are derived for each client, but all clients have the same password and can derive each other's keys if they want to. The keys that are used to encrypt traffic are computed as part of an authentication handshake. The handshake happens right after the client associates with a wireless network and authenticates with an authentication server, if there is one. At the start of the handshake, the client has either the shared network password or its password for the authentication server. This password is used to derive a master key. However, the master key is not used directly to encrypt packets. It is standard cryptographic practice to derive a session key for each period of usage, to change the key for different sessions, and to expose the master key to observation as little as possible. It is this session key that is computed in the handshake. The session key is computed with the 4-packet handshake shown in figure 8.31. First, the app access point sends a random number for identification. Random numbers used just once in security protocols like this one are called nonces, which is more or less a contraction of number used once. The client also picks its own nonce. It uses the nonces, its MAC address and that of the app, and the master key, to compute a session key, KS. The session key is split into portions, each of which is used for different purposes, but we have omitted this detail. Now the client has session keys, but the app does not. So the client sends its nonce to the app, and the app performs the same computation to derive the same session keys. The nonces can be sent in the clear because the keys cannot be derived from them without extra secret information. The message from the client is protected with an integrity check called a MIC, message integrity check, based on the session key. The app can check that the MIC is correct, and so the message indeed must have come from the client after it computes the session keys. A MIC is just another name for a message authentication code, as in an HMAC. The term MIC is often used instead for networking protocols because of the potential for confusion with MAC, medium access control, addresses. Client nonce app nonce C, MIX KS, kilograms, MIX 2, 4, 1, 3 access point, app, compute session keys KS from MAC addresses, nonces, and master key distribute group key, kilograms verify client has KS verify app has KS acknowledge compute session keys KS. Same as the client KS, AC, MIX figure 8.231. The 802.11i key setup handshake. In the last two messages, the app distributes a group key, kilograms to the client, and the client acknowledges the message. Receipt of these messages lets the client verify that the app has the correct session keys, and vice versa. The group key is used for broadcast and multicast traffic on the 802.11 LAN. Because the result of the handshake is that every client has its own encryption keys, none of these keys can be used by the app to broadcast packets to all of the wireless clients. A separate copy would need to be sent to each client using its key. Instead, a shared key is distributed so that broadcast traffic can be sent only once and received by all the clients. It must be updated as clients leave and join the network. Finally, we get to the part where the keys are actually used to provide security. Two protocols can be used in 802.11i to provide message confidentiality, integrity, and authentication. Like WPA, one of the protocols, called TKIP, Temporary Key Integrity Protocol, was an interim solution. It was designed to improve security on old and slow 802.11 cards, so that at least some security that is better than WEP can be rolled out as a firmware upgrade. However, it too has now been broken, so you are better off with the other recommended protocol, CCMP. What does CCMP stand for? It is short for the somewhat spectacular name Counter Mode with Cipher Blockchaining Message Authentication Code Protocol. We will just call it CCMP. You can call it anything you want. CCMP works in a fairly straightforward way. It uses ease encryption with a 128-bit key and block size. The key comes from the session key. To provide confidentiality, messages are encrypted with ease in counter mode. Recall that we discussed cipher modes in Secretary 8.2.3. These modes are what prevent the same message from being encrypted to the same set of bits each time. Counter mode mixes a counter into the encryption. To provide integrity, the message, including header fields, is encrypted with cipher blockchaining mode and the last 128-bit block is kept as the MIC. Then both the message, encrypted with counter mode, and the MIC are sent. The client and the app can each perform this encryption, or verify this encryption, when a wireless packet is received. For broadcast or multicast messages, the same procedure is used with the group key. Bluetooth security. Bluetooth has a considerably shorter range than 802.11, so it cannot easily be attacked from the parking lot, but security is still an issue here. For example, imagine that Alice's computer is equipped with a wireless Bluetooth keyboard. In the absence of security, if Trudy happened to be in the adjacent office, she could read everything Alice typed in, including all her outgoing email. She could also capture everything Alice's computer sent to the Bluetooth printer sitting next to it, for instance, incoming email and confidential reports. Fortunately, Bluetooth has an elaborate security scheme to try to foil the world's Trudies. We will now summarize the main features of it. Bluetooth version 2.1 and later has 4 security modes, ranging from nothing at all to full data encryption and integrity control. As with 802.11, if security is disabled, the default for older devices, there is no security. Most users have security turned off until a serious breach has occurred, then they turn it on. In the agricultural world, this approach is known as locking the barn door after the horse has escaped. Bluetooth provides security in multiple layers. In the physical layer, frequency hopping provides a tiny little bit of security, but since any Bluetooth device that moves into a piconet has to be told the frequency hopping sequence, this sequence is obviously not a secret. The real security starts when the newly arrived slave asks for a channel with the master. Before Bluetooth 2.1, two devices were assumed to share a secret key set up in advance. In some cases, both are hardwired by the manufacturer, for instance, for a headset and mobile phone sold as a unit. In other cases, one device, for instance, the headset, has a hardwired key and the user has to enter that key into the other device, for instance, the mobile phone, as a decimal number. These shared keys are called passkeys. Unfortunately, the passkeys are often hard-coded to "1234" or another predictable value, and in any case, are 4 decimal digits, allowing only 104 choices. With simple secure pairing in Bluetooth 2.1, devices pick a code from a 6-digit range, which makes the passkey much less predictable, but still far from secure. To establish a channel, the slave and master each check to see if the other one knows the passkey. If so, they negotiate whether that channel will be encrypted, integrity controlled, or both. Then they select a random 128-bit session key, some of whose bits may be public. The point of allowing this key weakening is to comply with government restrictions in various countries designed to prevent the export or use of keys longer than the government can break. Encryption uses a stream cipher called D0, integrity control uses Cipher Plus. Both are traditional symmetric key block ciphers. Cipher Plus was submitted to the EASE bake-off, but was eliminated in the first round because it was slower than the other candidates. Bluetooth was finalized before the EASE cipher was chosen, otherwise, it would most likely have used Deal. The actual encryption using the stream cipher is shown in figure 8 to 14, with the plain text stored with the key stream to generate the ciphertext. Unfortunately, E0 itself, like RC4, may have fatal weaknesses. Jacobson and Wetzel, 2001. While it was not broken at the time of this writing, its similarities to the A5/1 cipher, whose spectacular failure compromises all GSM telephone traffic, are cause for concern. Baryukov and others, 2000. It sometimes amazes people, including the authors of this book, that in the perennial cat and mouse game between the cryptographers and the cryptanalysts, the cryptanalysts are so often on the winning side. Another security issue is that Bluetooth authenticates only devices, not users, so theft of a Bluetooth device may give the thief access to the user's financial and other accounts. However, Bluetooth also implements security in the upper layers, so even in the event of a breach of link-level security, some security may remain, especially for applications that require a PIN code to be entered manually from some kind of keyboard to complete the transaction. 8.7 Authentication Protocols. Authentication is the technique by which a process verifies that its communication partner is who it is supposed to be and not an imposter. Verifying the identity of a remote process in the face of malicious active intruder is surprisingly difficult and requires complex protocols based on cryptography. In this section, we will study some of the many authentication protocols that are used on insecure computer networks. As an aside, some people confuse authorization with authentication. Authentication deals with the question of whether you are actually communicating with a specific process. Authorization is concerned with what that process is permitted to do. For example, say a client process contacts a file server and says, "I'm Scott's process and I want to delete the file cookbook.old." From the file server's point of view, two questions must be answered. 1. Is this actually Scott's process? Authentication. 2. Is Scott allowed to delete cookbook.old? Authorization. Only after both of these questions have been unambiguously answered in the affirmative can the requested action take place. The former question is really the key one. Once the file server knows to whom it is talking, checking authorization is just a matter of looking up entries in local tables or databases. For this reason, we will concentrate on authentication in this section. The general model that essentially all authentication protocols uses this. Alice starts out by sending a message either to Bob or to a trusted KDC, key distribution center, which is expected to be honest. Several other message exchanges follow in various directions. As these messages are being sent, Trudy may intercept, modify, or replay them in order to trick Alice and Bob or just to gum up the works. Nevertheless, when the protocol has been completed, Alice is sure she is talking to Bob, and Bob is sure he is talking to Alice. Furthermore, in most of the protocols, the two of them will also have established a secret session key for use in the upcoming conversation. In practice, For performance reasons, all data traffic is encrypted using symmetric key cryptography, typically ES or triple Ds, although public key cryptography is widely used for the authentication protocols themselves and for establishing the session key. The point of using a new, randomly chosen session key for each new connection is to minimize the amount of traffic that gets sent with the user's secret keys or public keys, to reduce the amount of ciphertext an intruder can obtain, and to minimize the damage done if a process crashes and its core dump falls into the wrong hands. Hopefully, the only key present then will be the session key. All the permanent keys should have been carefully zeroed out after the session was established. 8.7.1 Authentication. Based on a shared secret key for our first authentication protocol, we will assume that Alice and Bob already share a secret key, CAP. This shared key might have been agreed upon on the telephone or in person, but, in any event, not on the insecure network. This protocol is based on a principle found in many authentication protocols. One party sends a random number to the other, who then transforms it in a special way and returns the result. Such protocols are called challenge response protocols. In this and subsequent authentication protocols, the following notation will be used. A, B are the identities of Alice and Bob. Res are the challenges, where I identifies the challenger. Keys are keys, where I indicates the owner. KS is the session key. The message sequence for our first shared key authentication protocol is illustrated in figure 8.232. In message 1, Alice sends her identity, A, to Bob in a way that Bob understands. Bob, of course, has no way of knowing whether this message came from Alice or from Trudy, so he chooses a challenge, a large random number, RB, and sends it back to Alice as message 2, in plain text. Alice then encrypts the message with the key she shares with Bob, and sends the ciphertext, CAP, RB, back in message 3. When Bob sees this message, he immediately knows that it came from Alice, because Trudy does not know CAP, and thus could not have generated it. Furthermore, since RB was chosen randomly from a large space, say, 128-bit random numbers, it is very unlikely that Trudy would have seen RB and its response in an earlier session. It is equally unlikely that she could guess the correct response to any challenge. Figure 8.232. Two-way authentication using a challenge response protocol. At this point, Bob is sure he is talking to Alice, but Alice is not sure of anything. For all Alice knows, Trudy might have intercepted message 1 and sent back RB in response. Maybe Bob died last night. To find out to whom she is talking, Alice picks a random number, RAP, and sends it to Bob as plain text in message 4. When Bob responds with CAP, RAP, Alice knows she is talking to Bob. If they wish to establish a session key now, Alice can pick one, KS, and send it to Bob encrypted with CAB. The protocol of figure 8.232 contains 5 messages. Let us see if we can be clever and eliminate some of them. One approach is illustrated in figure 8.233. Here Alice initiates the challenge response protocol instead of waiting for Bob to do it. Similarly, while he is responding to Alice's challenge, Bob sends his own. The entire protocol can be reduced to 3 messages instead of 5. Is this new protocol an improvement over the original one? In one sense it is shorter. Unfortunately, it is also wrong. Under certain circumstances, Trudy can defeat this protocol by using what is known as a reflection attack. In particular, Trudy can break it if it is possible to open multiple sessions with Bob at once. This situation would be true, for example, if Bob is a bank and is prepared to accept many simultaneous connections from teller machines at once. Figure 8.233. A shortened two-way authentication protocol. Trudy's reflection attack is shown in figure 8.234. It starts out with Trudy claiming she is Alice and sending right. Bob responds, as usual, with his own challenge, RB. Now Trudy is stuck. What can she do? She does not know CAB, RB. Figure 8.234. The reflection attack. She can open a second session with message 3, supplying the RB taken from message 2 as her challenge. Bob calmly encrypts it and sends back cab RB in message 4. We have shaded the messages on the second session to make them stand out. Now Trudy has the missing information, so she can complete the first session and abort the second one. Bob is now convinced that Trudy is Alice, so when she asks for her bank account balance, he gives it to her without question. Then when she asks him to transfer it all to a secret bank account in Switzerland, he does so without a moment's hesitation. The moral of this story is, designing a correct authentication protocol is much harder than it looks. The following 4 general rules often help the designer avoid common pitfalls. 1. Have the initiator prove who she is before the responder has to. This avoids Bob giving away valuable information before Trudy has to give any evidence of who she is to. Have the initiator and responder use different keys for proof, even if this means having to shared keys, cab and K, add 3. Have the initiator and responder draw their challenges from different sets. For example, the initiator must use even numbers and the responder must use odd numbers for. Make the protocol resistant to attacks involving a second parallel session in which information obtained in one session is used in a different one. If even one of these rules is violated, the protocol can frequently be broken. Here, all 4 rules were violated, with disastrous consequences. Now let us go take a closer look at figure 8232. Surely that protocol is not subject to a reflection attack. Maybe. It is quite subtle. Trudy was able to defeat our protocol by using a reflection attack because it was possible to open a second session with Bob and trick him into answering his own questions. What would happen if Alice were a general purpose computer that also accepted multiple sessions rather than a person at a computer? Let us take a look what Trudy can do. To see how Trudy's attack works, see figure 8235. Alice starts out by announcing her identity in message 1. Trudy intercepts this message and begins her own session with message 2, claiming to be Bob. Again we have shaded the session 2 messages. Alice responds to message 2 by saying in message 3, "You claim to be Bob? Prove it." At this point, Trudy is stuck because she cannot prove she is Bob. What does Trudy do now? She goes back to the first session, where it is her turn to send a challenge, and sends the RA she got in message 3. Alice kindly responds to it in message 5, thus supplying Trudy with the information she needs to send in message 6 in session 2. At this point, Trudy is basically home free, because she has successfully responded to Alice's challenge in session 2. She can now cancel session 1, send over any old number for the rest of session 2, and she will have an authenticated session with Alice in session 2. But Trudy is nasty, and she really wants to rub it in. Instead of sending any old number over to complete session 2, she waits until Alice sends message 7, Alice's challenge for session 1. Of course, Trudy does not know how to respond, so she uses the reflection attack again, sending back Ratu as message 8. Alice conveniently encrypts Ratu in message 9. Trudy now switches back to session 1 and sends Alice the number she wants in message 10, conveniently copied from what Alice sent in message 9. At this point Trudy has 2 fully authenticated sessions with Alice. This attack has a somewhat different result than the attack on the 3-message protocol that we saw in figure 8234. This time, Trudy has 2 authenticated connections with Alice. In the previous example, she had 1 authenticated connection with Bob. Again here, if we had applied all the general authentication protocol rules discussed earlier, this attack could have been stopped. For a detailed discussion of these kinds of attacks and how to thwart them, see Bird and others, 1993. They also show how it is possible to systematically construct protocols that are provably correct. The simplest such protocol is nevertheless a bit complicated, so we will now show a different class of protocol that also works. Aralis v1, 2, 4, 5, 3 cab, rap, Trudy ra 6 cab, rap, 7 ratu, 8, 9 cab, ratu, 10 cab, ratu, first session, second session. Figure 8235. a reflection attack on the protocol of figure 8232. The new authentication protocol is shown in figure 8236, Bird and others, 1993. It uses an HMAC of the type we saw when studying IPsec. Alice starts out by sending Bob a nonce, wrap, as message 1. Bob responds by selecting his own nonce, RB, and sending it back along with an HMAC. The HMAC is formed by building a data structure consisting of Alice's nonce, Bob's nonce, their identities, and the shared secret key, cap. This data structure is then hashed into the HMAC, for example, using SHA-1. When Alice receives message 2, she now has wrap, which she picked herself, RB, which arrives as plain text, the two identities, and the secret key, cap, which she has known all along, so she can compute the HMAC herself. If it agrees with the HMAC and the message, she knows she is talking to Bob, because Trudy does not know cap and thus cannot figure out which HMAC to send. Alice responds to Bob with an HMAC containing just the two nonces. Can Trudy somehow subvert this protocol? No, because she cannot force either party to encrypt or hash a value of her choice, as happened in figure 8234 and figure 8235. Both HMACs include values chosen by the sending party, something that Trudy cannot control. Alice 1, 3, to wrap Bob RB, HMAC, wrap RB, A, B, cap, HMAC, wrap RB, cap, figure 8236. Authentication using HMACs. Using HMACs is not the only way to use this idea. An alternative scheme that is often used instead of computing the HMAC over a series of items is to encrypt the items sequentially using cipher blockchaining 8.7. To establishing a shared key, the Diffie-Hellman key exchange. So far, we have assumed that Alice and Bob share a secret key. Suppose that they do not, because so far there is no universally accepted PKI for signing and distributing certificates. How can they establish one? One way would be for Alice to call Bob and give him her key on the phone, but he would probably start out by saying, "How do I know you are Alice and not Trudy?" They could try to arrange a meeting, with each one bringing a passport, a driver's license, and 3 major credit cards, but being busy people, they might not be able to find a mutually acceptable date for months. Fortunately, incredible as it may sound, there is a way for total strangers to establish a shared secret key in broad daylight, even with Trudy carefully recording every message. The protocol that allows strangers to establish a shared secret key is called the Diffie-Hellman key exchange, Diffie and Hellman, 1976, and works as follows. Alice and Bob have to agree on 2 large numbers, n and g, where n is a prime, n1/2 is also a prime, and certain conditions apply to g. These numbers may be public, so either one of them can just pick n and g and tell the other openly. Now Alice picks a large, say, 1024-bit number, x, and keeps it secret. Similarly, Bob picks a large secret number, y. Alice initiates the key exchange protocol by sending Bob a message containing n, g, gx mod n, as shown in figure 8237. Bob responds by sending Alice a message containing J mod n. Now Alice raises the number Bob sent her to the xth power modulo n to get J mod n, x mod n. Bob performs a similar operation to get gx mod n, y mod n. By the laws of modular arithmetic, both calculations yield gx y mod n. Lo and behold, as if by magic, Alice and Bob suddenly share a secret key, gx y mod n. Alice picks x, Bob picks y too. J mod n, g, gx mod n. Alice computes J mod n, x equals gx y mod n. Bob computes gx mod n, y equals gx y mod n. Bob. Alice mod n figure 8237. The Diffie-Hellman key exchange. Trudy, of course, has seen both messages. She knows g and n from message 1. If she could compute x and y, she could figure out the secret key. The trouble is, given only gx mod n, she cannot find x. No practical algorithm for computing discrete logarithms modulo a very large prime number is known. To make this example more concrete, we will use a completely unrealistic Values of n equals 47 and g equals 3. Alice picks x equals 8 and Bob picks y equals 10. Both of these are kept secret. Alice's message to Bob is 47, 3, 28, because 38 mod 47 is 28. Bob's message to Alice is 17. Alice computes 178 mod 47, which is 4. Bob computes 2810 mod 47, which is 4. Alice and Bob have now independently determined that the secret key is now 4. To find the key, Trudy now has to solve the equation 3x mod 47 equals 28, which can be done by exhaustive search for small numbers like this, but not when all the numbers are hundreds of bits long. All currently known algorithms simply take far too long, even on massively parallel, lightning-fast supercomputers. Despite the elegance of the Diffie-Hellman algorithm, there is a problem. When Bob gets the triple, 47, 3, 28, how does he know it is from Alice, and not from Trudy? There is no way he can know. Unfortunately, Trudy can exploit this fact to deceive both Alice and Bob, as illustrated in figure 8.238. Here, while Alice and Bob are choosing x and y, respectively, Trudy picks her own random number, z. Alice sends message 1, intended for Bob. Trudy intercepts it, and sends message 2 to Bob, using the correct g and n, which are public anyway, but with her own z instead of x. She also sends message 3 back to Alice. Later Bob sends message 4 to Alice, which Trudy again intercepts and keeps. Now everybody does the modular arithmetic. Alice computes the secret key as gxz mod n, and so does Trudy, for messages to Alice. Bob computes giz mod n, and so does Trudy, for messages to Bob. Alice thinks she is talking to Bob, so she establishes a session key with Trudy. So does Bob. Every message that Alice sends on the encrypted session is captured by Trudy, stored, modified if desired, and then, optionally, passed on to Bob. Similarly, in the other direction, Trudy sees everything and can modify all messages at will, while both Alice and Bob are under the illusion that they have a secure channel to one another. For this reason, the attack is known as the man-in-the-middle attack. It is also called the Bucket Brigade attack because it vaguely resembles an old-time volunteer fire department passing buckets along the line from the fire truck to the fire. Alice picks x, Trudy picks z, 3gz mod n, g, gx mod n, Trudy 2, Bob picks y, 4gi mod n, g, gz mod n, Bob. Alice figure 8.238. The man-in-the-middle attack 8.7.3 authentication using a key distribution center. Setting up a shared secret with a stranger almost worked, but not quite. On the other hand, it probably was not worth doing in the first place. Sour grapes attack. To talk to n people this way, you would need n keys. For popular people, key management would become a real burden, especially if each key had to be stored on a separate plastic chip card. A different approach is to introduce a trusted key distribution center. In this model, each user has a single key shared with the KDC. Authentication and session key management now go through the KDC. The simplest known KDC authentication protocol involving two parties and a trusted KDC is depicted in figure 8.239. 1a, cap, b, ks, KDC2 Bob Alice KB, a, ks, figure 8.239. A first attempt at an authentication protocol using a KDC. The idea behind this protocol is simple. Alice picks a session key, KS, and tells the KDC that she wants to talk to Bob using KS. This message is encrypted with the secret key Alice shares, only with the KDC, cap. The KDC decrypts this message, extracting Bob's identity and the session key. It then constructs a new message containing Alice's identity and the session key, and sends this message to Bob. This encryption is done with KB, the secret key Bob shares with the KDC. When Bob decrypts the message, he learns that Alice wants to talk to him, and which key she wants to use. The authentication here happens for free. The KDC knows that message 1 must have come from Alice, since no one else would have been able to encrypt it with Alice's secret key. Similarly, Bob knows that message 2 must have come from the KDC, whom he trusts, since no one else knows his secret key. Unfortunately, this protocol has a serious flaw. Trudy needs some money, so she figures out some legitimate service she can perform for Alice, makes an attractive offer, and gets the job. After doing the work, Trudy then politely requests Alice to pay by bank transfer. Alice then establishes a session key with her banker, Bob. Then she sends Bob a message requesting money to be transferred to Trudy's account. Meanwhile, Trudy is back to her old ways, snooping on the network. She copies both message to in figure 8239 and the money transfer request that follows it. Later, she replays both of them to Bob, who thinks Alice must have hired Trudy again. She clearly does good work. Bob then transfers an equal amount of money from Alice's account to Trudy's. Sometime after the 50th message pair, Bob runs out of the office to find Trudy to offer her a big loan so she can expand her obviously successful business. This problem is called the replay attack. Several solutions to the replay attack are possible. The first one is to include a timestamp in each message. Then, if anyone receives an obsolete message, it can be discarded. The trouble with this approach is that clocks are never exactly synchronized over a network, so there has to be some interval during which a timestamp is valid. Trudy can replay the message during this interval and get away with it. The second solution is to put a nonce in each message. Each party then has to remember all previous nonces and reject any message containing a previously used nonce. But nonces have to be remembered forever, lest Trudy try replaying a 5-year-old message. Also, if some machine crashes and it loses its nonce list, it is again vulnerable to a replay attack. Timestamps and nonces can be combined to limit how long nonces have to be remembered, but clearly the protocol is going to get a lot more complicated. A more sophisticated approach to mutual authentication is to use a multi-way challenge response protocol. A well-known example of such a protocol is the Needham-Schroeder authentication protocol, Needham and Schroeder, 1978, one variant of which is shown in figure 8240. The protocol begins with Alice telling the KDC that she wants to talk to Bob. This message contains a large random number, RAP, as a nonce. The KDC sends back message 2 containing Alice's random number, a session key, and a ticket 1 RAP A, B2 cap RAP B, KS, KB, A, KS, KDC 3 Bob Alice KB, A, KS, KS, RA2, 4 KS, RA2-1, RB5 KS, RB-1. Figure 8240. The Needham-Schroeder authentication protocol that she can send to Bob. The point of the random number, RAP, is to assure Alice that message 2 is fresh and not a replay. Bob's identity is also enclosed in case Trudy gets any funny ideas about replacing B in message 1 with her own identity, so the KDC will encrypt the ticket at the end of message 2 with night instead of KB. The ticket encrypted with KB is included inside the encrypted message to prevent Trudy from replacing it with something else on the way back to Alice. Alice now sends the ticket to Bob, along with a new random number, RA2, encrypted with the session key, KS. In message 4, Bob sends back KS, RA2, 1, to prove to Alice that she is talking to the real Bob. Sending back KS, RA2, would not have worked, since Trudy could just have stolen it from message 3. After receiving message 4, Alice is now convinced that she is talking to Bob and that no replays could have been used so far. After all, she just generated RA2 a few milliseconds ago. The purpose of message 5 is to convince Bob that it is indeed Alice he is talking to, and no replays are being used here either. By having each party both generate a challenge and respond to one, the possibility of any kind of replay attack is eliminated. Although this protocol seems pretty solid, it does have a slight weakness. If Trudy ever manages to obtain an old session key in plain text, she can initiate a new session with Bob by replaying the message 3 that corresponds to the compromised key and convince him that she is Alice, Denning and Sacco, 1981. This time she can plunder Alice's bank account without having to perform the legitimate service even once. Needham and Schroeder, 1987, later published a protocol that corrects this problem. In the same issue of the same journal, Otway and Rees, 1987, also published a protocol that solves the problem in a shorter way. Figure 8-41 shows a slightly modified Otway-Rees protocol. In the Otway-Rees protocol, Alice starts out by generating a pair of random numbers, R, which will be used as a common identifier, and RAP, which Alice will use to challenge Bob. When Bob gets this message, he constructs a new message from the encrypted part of Alice's message and an analogous one of his own for cap, RAP, KS, 3, to KB, RB, KS, KDC1 Bob Alice A, B, R, cap A, B, R, RAP A, cap A, B, R, RAP B, KB, A, B, R, RB, figure 8-41. The Otway-Rees authentication protocol, slightly simplified. Both the parts encrypted with CAB and KB identify Alice and Bob, contain the common identifier, and contain a challenge. The KDC checks to see if the R in both parts is the same. It might not be if Trudy has tampered with R in message 1 or replaced part of message 2. If the two rupee match, the KDC believes that the request message from Bob is valid. It then generates a session key and encrypts it twice, once for Alice and once for Bob. Each message contains the receiver's random number, as proof that the KDC, and not Trudy, generated the message. At this point, both Alice and Bob are in possession of the same session key and can start communicating. The first time they exchange data messages, each one can see that the other one has an identical copy of KS, so the authentication is then complete. 8.7.4 Authentication using Kerberos, an authentication protocol used in many real systems, including Windows 2000 and later versions, is Kerberos, which is based on a variant of Needham. Schroeder. It is named for a multi-headed dog in Greek mythology that used to guard the entrance to Hades, presumably to keep undesirables out. Kerberos was designed at MIT to allow workstation users to access network resources in a secure way. Its biggest difference from Needham-Schroeder is its assumption that old clocks are fairly well synchronized. The protocol has gone through several iterations. V5 is the one that is widely used in industry and defined in RFC 4120. The earlier version, V4, was finally retired after serious flaws were found, U and others, 2004. V5 improves on V4 with many small changes to the protocol and some improved features, such as the fact that it no longer relies on the now dated Ds. For more information, see Norman and So, 1994. Kerberos involves 3 servers in addition to Alice, a client workstation. 1. Authentication server, as, verifies users during login. 2. Ticket granting server, TGS, issues proof of identity tickets. 3. Bob the server, actually does the work Alice once performed. As is similar to a KDC, in that it shares a secret password with every user. The TGS's job is to issue tickets that can convince the real servers that the bearer of a TGS ticket really is who he or she claims to be. To start a session, Alice sits down at an arbitrary public workstation and types her name. The workstation sends her name and the name of the TGS to the as in plain text, as shown in message 1 of figure 8-42. What comes back is a session key and a ticket, KTGS, A, KS, T, intended for the TGS. The session key is encrypted using Alice's secret key, so that only Alice can decrypt it. Only when message 2 arrives, does the workstation ask for Alice's password, not before then. The password is then used to generate CAP in order to decrypt message 2 and obtain the session key. At this point, the workstation overwrites Alice's password to make sure that it is only inside the workstation for a few milliseconds at most. If Trudy tries logging in as Alice, the password she types will be wrong and the workstation will detect this because the standard part of message 2 will be incorrect. Alice's TGS Bob Cap A T KB A B Cap T A TGS Cap TGS KS T, KTGS, A, KS, T, B, KS, A, T, KTGS, A, KS, T, KS, B, cap, T, KB, A, B, cap, T, cap, T, 6, 5, 2, 4, 1, 3 figure. 8242. The operation of Kerberos v5. After she logs in, Alice may tell the workstation that she wants to contact Bob the file server. The workstation then sends message 3 to the TGS asking for a ticket to use with Bob. The key element in this request is the ticket KTGS, A, KS, T, which is encrypted with the TGS's secret key and used as proof that the sender really is Alice. The TGS responds in message 4 by creating a session key, cap, for Alice to use with Bob. Two versions of it are sent back. The first is encrypted with only KS, so Alice can read it. The second is another ticket, encrypted with Bob's key, KB, so Bob can read it. Trudy can copy message 3 and try to use it again, but she will be foiled by the encrypted timestamp, T, sent along with it. Trudy cannot replace the timestamp with a more recent one, because she does not know KS, the session key Alice uses to talk to the TGS. Even if Trudy replays message 3 quickly, all she will get is another copy of message 4, which she could not decrypt the first time, and will not be able to decrypt the second time either. Now Alice can send CAB to Bob via the new ticket to establish a session with him, message 5. This exchange is also timestamped. The optional response, message 6, is proof to Alice that she is actually talking to Bob, not to Trudy. After this series of exchanges, Alice can communicate with Bob under cover of CAB. If she later decides she needs to talk to another server, Carol, she just repeats message 3 to the TGS, only now specifying C instead of B. The TGS will promptly respond with a ticket encrypted with KC that Alice can send to Carol, and that Carol will accept as proof that it came from Alice. The point of all this work is that now Alice can access servers all over the network in a secure way, and her password never has to go over the network. In fact, it only had to be in her own workstation for a few milliseconds. However, note that each server does its own authorization. When Alice presents her ticket to Bob, this merely proves to Bob who sent it. Precisely what Alice is allowed to do is up to Bob. Since the Kerberos designers did not expect the entire world to trust a single authentication server, they made provision for having multiple realms, each with its own AS and TGS. To get a ticket for a server in a distant realm, Alice would ask her own TGS for a ticket accepted by the TGS in the distant realm. If the distant TGS has registered with the local TGS, the same way local servers do, the local TGS will give Alice a ticket valid at the distant TGS. She can then do business over there, such as getting tickets for servers in that realm. Note, however, that for parties in two realms to do business, each one must trust the other's TGS. Otherwise, they cannot do business. 8.7.5 Authentication using public key cryptography. Mutual authentication can also be done using public key cryptography. To start with, Alice needs to get Bob's public key. If a PKI exists with a directory server that hands out certificates for public keys, Alice can ask for Bob's, as shown in figure 8-43 as message 1. The reply, in message 2, is an X509 certificate containing Bob's public key. When Alice verifies that the signature is correct, she sends Bob a message containing her identity and a nonce. When Bob receives this message, he has no idea whether it came from Alice or from Trudy, but he plays along and asks the directory server for Alice's public key, message 4, which he soon gets, message 5. He then sends Alice message 6, containing Alice's RAP, his own nonce, RB, and a proposed session key, KS3EB, A, RAP, 7KS, RB, 6EA, RAP, RB, KS, Bob Alice directory 2. Here is EB4. Give me EA5. Here is EA1. Give me EB figure 8-43. Mutual authentication using public key cryptography. When Alice gets message 6, She decrypts it using her private key. She sees RAM in it, which gives her a warm feeling inside. The message must have come from Bob, since Trudy has no way of determining RAM. Furthermore, it must be fresh, and not a replay, since she just sent Bob RAM. Alice agrees to the session by sending back message 7. When Bob sees RB encrypted with the session key he just generated, he knows Alice got message 6 and verified RAM. Bob is now a happy camper. What can Trudy do to try to subvert this protocol? She can fabricate message 3 and trick Bob into probing Alice, but Alice will see in RAM that she did not send and will not proceed further. Trudy cannot forge message 7 back to Bob because she does not know RB or KS and cannot determine them without Alice's private key. She is out of luck. 8.8 email security. When an email message is sent between two distant sites, it will generally transit dozens of machines on the way. Any of these can read and record the message for future use. In practice, privacy is non-existent, despite what many people think. Nevertheless, many people would like to be able to send email that can be read by the intended recipient and no one else, not their boss, and not even their government. This desire has stimulated several people and groups to apply the cryptographic principles we studied earlier to email to produce secure email. In the following sections we will study a widely used secure email system, PGP, and then briefly mention one other, S/MIME. For additional information about secure email, see Kaufman and others, 2002, and Skneia, 1995, 8.8.1 PGP. Pretty Good Privacy. Our first example, PGP, Pretty Good Privacy, is essentially the brainchild of one person. Phil Zimmermann, 1995A, 1995B. Zimmermann is a privacy advocate whose motto is, if privacy is outlawed, only outlaws will have privacy. Released in 1991, PGP is a complete email security package that provides privacy, authentication, digital signatures, and compression, all in an easy-to-use form. Furthermore, the complete package, including all the source code, is distributed free of charge via the internet. Due to its quality, price, zero, and easy availability on Unix, Linux, Windows, and macOS platforms, it is widely used today. PGP encrypts data by using a block cipher called IDEA, International Data Encryption Algorithm, which uses 128-bit keys. It was devised in Switzerland at a time when DES was seen as tainted, and DES had not yet been invented. Conceptually, IDEA is similar to DES and EAS. It mixes up the bits in a series of rounds, but the details of the mixing functions are different from DES and EAS. Key management uses RSA and data integrity uses MD5, topics that we have already discussed. PGP has also been embroiled in controversy since day one. Levy, 1993. Because Zimmermann did nothing to stop other people from placing PGP on the internet, where people all over the world could get it, the US government claimed that Zimmermann had violated US laws prohibiting the export of munitions. The US government's investigation of Zimmermann went on for 5 years, but was eventually dropped, probably for two reasons. First, Zimmermann did not place PGP on the internet himself, so his lawyer claimed that he never exported anything, and then there is the little matter of whether creating a website constitutes export at all. Second, the government eventually came to realize that winning a trial meant convincing a jury that a website containing a downloadable privacy program was covered by the arms trafficking law prohibiting the export of war material such as tanks, submarines, military aircraft, and nuclear weapons. Years of negative publicity probably did not help much either. As an aside, the exports are bizarre, to put it mildly. The government considered putting code on a website to be an illegal export and harassed Zimmermann about it for 5 years. On the other hand, when someone published the complete PGP source code in C as a book in a large font with a checksum on each page to make scanning it easy, and then exported the book, that was fine with the government, because books are not classified as munitions. The sword is mightier than the pen, at least for Uncle Sam. Another problem PGP ran into involved patent infringement. The company holding the RSA patent, RSA Security Incorporated, alleged that PGP's use of the RSA algorithm infringed on its patent, but that problem was settled with releases starting at 2.6. Furthermore, PGP uses another patented encryption algorithm, IDEA, whose use caused some problems at first. Since PGP is open source, various people and groups have modified it and produced a number of versions. Some of these were designed to get around the munitions laws, others were focused on avoiding the use of patented algorithms, and still others wanted to turn it into a closed source commercial product. Although the munitions laws have now been slightly liberalized, otherwise, products using these would not have been exportable from the US, and the RSA patent expired in September 2000. The legacy of all these problems is that several incompatible versions of PGP are in circulation, under various names. The discussion below focuses on classic PGP, which is the oldest and simplest version. Another popular version, OpenPGP, is described in RFC 2440. Yet another is a new privacy guard. PGP intentionally uses existing cryptographic algorithms, rather than inventing new ones. It is largely based on algorithms that have withstood extensive peer review, and were not designed or influenced by any government agency trying to weaken them. For people who distrust government, this property is a big plus. PGP supports text compression, secrecy, and digital signatures, and also provides extensive key management facilities, but, oddly enough, not email facilities. It is like a preprocessor that takes plain text as input and produces signed ciphertext in base 64 as output. This output can then be emailed, of course. Some PGP implementations call a user agent as the final step to actually send the message. To see how PGP works, let us consider the example of figure 8244. Here, Alice wants to send a signed plain text message, P, to Bob in a secure way. Both Alice and Bob have private, DX, and public, X, RSA keys. Let us assume that each one knows the other's public key. We will cover PGP key management shortly. Alice starts out by invoking the PGP program on her computer. PGP first hashes her message, P, using MD5, and then encrypts the resulting hash using her private RSA key, DA. When Bob eventually gets the message, he can decrypt the hash with Alice's public key and verify that the hash is correct. Even if someone else, for instance, Trudy, could acquire the hash at this stage and decrypt it with Alice's known public key, the strength of MD5 guarantees that it would be computationally infeasible to produce another message with the same MD5 hash. The encrypted hash and the original message are now concatenated into a single message, P1, and compressed using the ZIP program, which uses the Ziv-Limpel algorithm, Ziv and Limpel, 1977. Call the output of this step P1.Z. Next PGP prompts Alice for some random input. Both the content and the typing speed are used to generate a 128-bit IDEA message key, kilometers, called a session key in the PGP literature, but this is really a misnomer, since there is no session. Kilometers is now used to encrypt P1.Z with IDEA in cipher feedback mode. In addition, kilometers is encrypted with Bob's public key, EB. These two components are then concatenated and converted to base 64, as we discussed in the section on MIME in chapter 7. The resulting message contains only letters, digits, and the symbols plus, slash, and equals, which means it can be put into an RFC 822 body and be expected to arrive unmodified. MD5 RSA zip IDEA base 64 RSA ASCII text to P1.Z. The network PP1 original plain text message from Alice concatenation of P and the signed hash of P concatenation of P1.Z encrypted with IDEA and kilometer encrypted with EB Alice's private RSA key, DAP1 compressed Bob's public RSA key, EB kilometers, one-time message key for IDEA, concatenation kilometer figure 8244. PGP in operation for sending a message. When Bob gets the message, he reverses the base 64 encoding and decrypts the IDEA key using his private RSA key. Using this key, he decrypts the message To get P1.Z after decompressing it, Bob separates the plain text from the encrypted hash and decrypts the hash using Alice's public key. If the plain text hash agrees with his own MD5 computation, he knows that P is the correct message and that it came from Alice. It is worth noting that RSA is only used in two places here, to encrypt the 128-bit MD5 hash and to encrypt the 128-bit IDEA key. Although RSA is slow, it has to encrypt only 256 bits, not a large volume of data. Furthermore, all 256 plaintext bits are exceedingly random, so a considerable amount of work will be required on Trude's part just to determine if a guessed key is correct. The heavy encryption is done by IDEA, which is orders of magnitude faster than RSA. Thus, PGP provides security, compression, and a digital signature, and does so in a much more efficient way than the scheme illustrated in Figure 8.2.19. PGP supports 4 RSA key lengths. It is up to the user to select the one that is most appropriate. The lengths are 1. Casual, 384 bits, can be broken easily to date 2. Commercial, 512 bits, breakable by 3-letter organizations 3. Military, 1024 bits, not breakable by anyone on Earth 4. Alien, 2048 bits, not breakable by anyone on other planets either. Since RSA is only used for small computations, everyone should use alien strength keys all the time. The format of a classic PGP message is shown in Figure 8.2.45. Numerous other formats are also in use. The message has 3 parts, containing the IDEA key, the signature, and the message, respectively. The key part contains not only the key, but also a key identifier, since users are permitted to have multiple public keys. IDEA Web IDEA VASIG HDR MD5 hash MSG HDR file name TIMETYPES kilometer message encrypted by IDEA compressed, encrypted by IDEA base 64 signature part message key part message part Figure 8.2.45. A PGP message. The signature part contains a header, which will not concern us here. The header is followed by a timestamp, the identifier for the sender's public key, that can be used to decrypt the signature hash, some type information that identifies the algorithms used to allow MD6 and RSA2 to be used when they are invented, and the encrypted hash itself. The message part also contains a header, the default name of the file to be used if the receiver writes the file to the disk, a message creation timestamp, and, finally, the message itself. Key management has received a large amount of attention in PGP as it is the Achilles heel of all security systems. Key management works as follows. Each user maintains 2 data structures locally, a private key ring and a public key ring. The private key ring contains 1 or more personal private/public key pairs. The reason for supporting multiple pairs per user is to permit users to change their public keys periodically or when one is thought to have been compromised without invalidating messages currently in preparation or in transit. Each pair has an identifier associated with it so that a message sender can tell the recipient which public key was used to encrypt it. Message identifiers consist of the low-order 64 bits of the public key. Users are themselves responsible for avoiding conflicts in their public key identifiers. The private keys on disk are encrypted using a special, arbitrarily long, password to protect them against sneak attacks. The public key ring contains public keys of the user's correspondence. These are needed to encrypt the message keys associated with each message. Each entry on the public key ring contains not only the public key, but also its 64-bit identifier and an indication of how strongly the user trusts the key. The problem being tackled here is the following. Suppose that public keys are maintained on bulletin boards. One way for Trudy to read Bob's secret email is to attack the bulletin board and replace Bob's public key with one of her choice. When Alice later fetches the key allegedly belonging to Bob, Trudy can mount a bucket brigade attack on Bob. To prevent such attacks, or at least minimize the consequences of them, Alice needs to know how much to trust the item called Bob's key on her public key ring. If she knows that Bob personally handed her a CD-ROM containing the key, she can set the trust value to the highest value. It is this decentralized, user-controlled approach to public key management that sets PGP apart from centralized PKI schemes. Nevertheless, people do sometimes obtain public keys by querying a trusted key server. For this reason, after X509 was standardized, PGP supported these certificates as well as the traditional PGP public key ring mechanism. All current versions of PGP have X509 support. 8.8.2s/MIME ETF's venture into email security, called S/MIME, Secure/MIME, is described in RFCs 2632 through 2643. It provides authentication, data integrity, secrecy, and non-repudiation. It also is quite flexible, supporting a variety of cryptographic algorithms. Not surprisingly, given the name, S/MIME integrates well with MIME, allowing all kinds of messages to be protected. A variety of new MIME headers are defined, for example, for holding digital signatures. S/MIME does not have a rigid certificate hierarchy beginning at a single root, which had been one of the political problems that doomed an earlier system called PEM, Privacy Enhanced Mail. Instead, users can have multiple trust anchors. As long as a certificate can be traced back to some trust anchor the user believes in, it is considered valid. S/MIME uses the standard algorithms and protocols we have been examining so far, so we will not discuss it any further here. For the details, please consult the RFCs. 8.9 Web security. We have just studied two important areas where security is needed: communications and email. You can think of these as the soup and appetizer. Now it is time for the main course, web security. The web is where most of the truders hang out nowadays and do their dirty work. In the following sections, we will look at some of the problems and issues relating to web security. Web security can be roughly divided into three parts. First, how are objects and resources named securely? Second, how can secure, authenticated connections be established? Third, what happens when a website sends a client a piece of executable code? After looking at some threats, we will examine all these issues. 8.9.1 Threats. One reads about website security problems in the newspaper almost weekly. The situation is really pretty grim. Let us look at a few examples of what has already happened. First, the home pages of numerous organizations have been attacked and replaced by new home pages of the crackers' choosing. The popular press calls people who break into computers hackers, but many programmers reserve that term for great programmers. We prefer to call these people crackers. Sites that have been cracked include those belonging to Yahoo, the US Army, the CIA, NASA, and the New York Times. In most cases, the crackers just put up some funny text and the sites were repaired within a few hours. Now let us look at some much more serious cases. Numerous sites have been brought down by denial of service attacks, in which the cracker floods a site with traffic, rendering it unable to respond to legitimate queries. Often, the attack is mounted from a large number of machines that the cracker has already broken into, DDoS attacks. These attacks are so common that they do not even make the news anymore, but they can cost the attacked sites thousands of dollars in lost business. In 1999, a Swedish cracker broke into Microsoft's Hotmail website and created a mirror site that allowed anyone to type in the name of a Hotmail user and then read all of the person's current and archived email. In another case, a 19-year-old Russian cracker named Maxim broke into an e-commerce website and stole 300,000 credit card numbers. Then he approached the site owners and told them that if they did not pay him $100,000, he would post all the credit card numbers to the internet. They did not give in to his blackmail, and he indeed posted the credit card numbers, inflicting great damage on many innocent victims. In a different vein, a 23-year-old California student emailed a press release to a news agency falsely stating that the Emulex Corporation was going to post a large quarterly loss and that the CEO was resigning immediately. Within hours, the company's stock dropped by 60%, causing stockholders to lose over $2 billion. The perpetrator made $250,000 by selling the stock short just before sending the announcement. While this event was not a website break-in, it is clear that putting such an announcement on the homepage of any big corporation would have a similar effect. We could, unfortunately, go on like this for many more pages. But it is now time to examine some of the technical issues related to web security. For more information about security problems of all kinds, see Anderson, 2008A, Stuttard and Pinto, 2007, and Skneia, 2004. Searching the internet will also turn up vast numbers of specific cases. 8.9.2 Secure naming. Let us start with something very basic. Alice wants to visit Bob's website. She types Bob's URL into her browser and a few seconds later, a web page appears. But is it Bob's? Maybe yes and maybe no. Trudy might be up to her old tricks again. For example, she might be intercepting all of Alice's outgoing packets and examining them. When she captures an HTTP GET request headed to Bob's website, she could go to Bob's website herself to get the page, modify it as she wishes, and return the fake page to Alice. Alice would be none the wiser. Worse yet, Trudy could slash the prices at Bob's e-store to make his goods look very attractive, thereby tricking Alice into sending her credit card number to Bob to buy some merchandise. One disadvantage of this classic man-in-the-middle attack is that Trudy has to be in a position to intercept Alice's outgoing traffic and forge her incoming traffic. In practice, she has to tap either Alice's phone line or Bob's, since tapping the fiber backbone is fairly difficult. While active wiretapping is certainly possible, it is a fair amount of work, and while Trudy is clever, she is also lazy. Besides, there are easier ways to trick Alice. DNS spoofing. One way would be for Trudy to crack the DNS system or maybe just the DNS cache at Alice's ISP and replace Bob's IP address, say 36.1.2.3, with her, Trudy's, IP address, say 42.9.9.9. That leads to the following attack. The way it is supposed to work is illustrated in figure 8 to 46. Here, Alice, 1, asks DNS for Bob's IP address, 2, gets it, 3, asks Bob for his homepage, and 4, gets that too. After Trudy has modified Bob's DNS record to contain her own IP address instead of Bob's, we get the situation in figure 8 to 46, B. Here, when Alice looks up Bob's IP address, she gets Trudy's, so all her traffic intended for Bob goes to Trudy. Trudy can now mount a man-in-the-middle attack without having to go to the trouble of tapping any phone lines. Instead, she has to break into a DNS server and change one record, a much easier proposition. How might Trudy fool DNS? It turns out to be relatively easy. Briefly summarized, Trudy can trick the DNS server at Alice's ISP into sending out a query to look up Bob's address. Unfortunately, since DNS uses UDP, the DNS server has no real way of checking who supplied the answer. Trudy can exploit this property by forging the expected reply and thus injecting a false IP address into the DNS server's cache. For simplicity, we will assume that Alice's ISP does not initially have an entry for Bob's website, bob.com. If it does, Trudy can wait until it times out and try later, or use other tricks. 1. Give me Bob's IP address to 36.1.2.3, Bob's IP address, 3. Get index.html 4. Bob's homepage, Bob's web server, 36.1.2.3, DNS server Alice 1, 2, 3, 4, 1. Give me Bob's IP address 242.9.9.9, Trudy's IP address, 3. Get index.html 4. Trudy's fake of Bob's homepage, Trudy's web server, 42.9.9.9, cracked DNS server Alice 1, 2, 3, B, 4 figure 8 to 46. Normal situation, B, an attack based on breaking into a DNS server and modifying Bob's record. Trudy starts the attack by sending a lookup request to Alice's ISP asking for the IP address of bob.com. Since there is no entry for this DNS name, the cache server queries the top level server for the com domain to get one. However, Trudy beats the com server to the punch and sends back a false reply saying bob.com is 42.9.9.9, where that IP address is hers. If her false reply gets back to Alice's ISP first, that one will be cached, and the real reply will be rejected as an unsolicited reply to a query no longer outstanding. Tricking a DNS server into installing a false IP address is called DNS spoofing. A cache that holds an intentionally false IP address like this is called a poisoned cache. Actually, things are not quite that simple. First, Alice's ISP checks to see that the reply bears the correct IP source address of the top level server. But since Trudy can put anything she wants in that IP field, she can defeat that test easily, since the IP addresses of the top level servers have to be public. Second, to allow DNS servers to tell which reply goes with which request, all requests carry a sequence number. To spoof Alice's ISP, Trudy has to know its current sequence number. The easiest way to learn the current sequence number is for Trudy to register a domain herself, say, trudytheintruder.com. Let us assume its IP address is also 42.9.9.9. She also creates a DNS server for her newly hatched domain, dns.trudytheintruder.com. It too uses Trudy's 42.9.9.9 IP address, since Trudy has only one computer. Now she has to make Alice's ISP aware of her DNS server. That is easy to do. All she has to do is ask Alice's ISP for trudytheintruder.com, which will cause Alice's ISP to find out who serves Trudy's new domain by asking the top level com server. With dns.trudytheintruder.com safely in the cache at Alice's ISP, the real attack can start. Trudy now queries Alice's ISP for www.trudytheintruder.com. The ISP naturally sends Trudy's DNS server a query asking for it. This query bears the sequence number that Trudy is looking for. Quick like a bunny, Trudy asks Alice's ISP to look up Bob. She immediately answers her own question by sending the ISP a forged reply, allegedly from the top level com server, saying bob.com is 42.9.9.9. This forged reply carries a sequence number 1 higher than the one she just received. While she is at it, she can also send a second forgery with a sequence number 2 higher, and maybe a dozen more with increasing sequence numbers. One of them is bound to match. The rest will just be thrown out. When Alice's forged reply arrives, it is cached. When the real reply comes in later, it is rejected, since no query is then outstanding. Now when Alice looks up bob.com, she is told to use 42.9.9.9, Trudy's address. Trudy has mounted a successful man-in-the-middle attack from the comfort of her own living room. The various steps to this attack are illustrated in figure 8.247. This one specific attack can be foiled by having DNS servers use random IDs in their queries, rather than just counting, but it seems that every time one hole is plugged, another one turns up. In particular, the IDs are only 16 bits, so working through all of them is easy when it is a computer that is doing the guessing one. Look up for trudytheintruder.com to force it into the ISP's cache. 2. Look up www.trudytheintruder.com to get the ISP's next sequence number. 3. Request for www.trudytheintruder.com carrying the ISP's next sequence number. N. 4. Quick like a bunny, look up bob.com to force the ISP to query the com server in step 5. 5. Legitimate query for bob.com with sec equals n+1. 6. Trudy's forged answer, Bob is 42.9.9.9, sec equals n+1. 7. Real answer, rejected. to late. Alice's ISP's cached DNS server for ComTrudy 5, 7, 1, 2, 3, 4, 6 figure 8247. How Trudy spoofs Alice's ISP. Secure DNS. The real problem is that DNS was designed at a time when the internet was a research facility for a few hundred universities, and neither Alice, nor Bob, nor Trudy was invited to the party. Security was not an issue then, making the internet work at all was the issue. The environment has changed radically over the years, so in 1994 IETF set up a working group to make DNS fundamentally secure. This ongoing project is known as DNSSEC, DNS Security. Its first output was presented in RFC 2535. Unfortunately, DNSSEC has not been fully deployed yet, so numerous DNS servers are still vulnerable to spoofing attacks. DNSSEC is conceptually extremely simple. It is based on public key cryptography. Every DNS zone, in the sense of figure 725, has a public/private key pair. All information sent by a DNS server is signed with the originating zone's private key, so the receiver can verify its authenticity. DNSSEC offers three fundamental services. 1. Proof of where the data originated. 2. Public key distribution. 3. Transaction and request authentication. The main service is the first one, which verifies that the data being returned has been approved by the zone's owner. The second one is useful for storing and retrieving public keys securely. The third one is needed to guard against playback and spoofing attacks. Note that secrecy is not an offered service, since all the information in DNS is considered public. Since phasing in DNSSEC is expected to take several years, the ability for security-aware servers to interwork with security-ignorant servers is essential, which implies that the protocol cannot be changed. Let us now look at some of the details. DNS records are grouped into sets called resets, resource record sets, with all the records having the same name, class, and type being lumped together in a set. An reset may contain multiple A records. For example, if a DNS name resolves to a primary IP address and a secondary IP address. The resets are extended with several new record types, discussed below. Each reset is cryptographically hashed, for instance, using SHA-1. The hash is signed by the zone's private key, for instance, using RSA. The unit of transmission to clients is the signed reset. Upon receipt of a signed reset, the client can verify whether it was signed by the private key of the originating zone. If the signature agrees, the data are accepted. Since each reset contains its own signature, resets can be cached anywhere, even at untrustworthy servers, without endangering the security. DNSSEC introduces several new record types. The first of these is the key record. This record holds the public key of a zone, user, host, or other principal, the cryptographic algorithm used for signing, the protocol used for transmission, and a few other bits. The public key is stored naked. X509 certificates are not used due to their bulk. The algorithm field holds a 1 for MD5/RSA signatures, the preferred choice, and other values for other combinations. The protocol field can indicate the use of IPsec or other security protocols, if any. The second new record type is the SIG record. It holds the signed hash according to the algorithm specified in the key record. The signature applies to all the records in the reset, including any key records present, but excluding itself. It also holds the times when the signature begins its period of validity and when it expires, as well as the signer's name and a few other items. The DNSSEC design is such that a zone's private key can be kept offline. Once or twice a day, the contents of a zone's database can be manually transported, for instance, on CD-ROM, to a disconnected machine on which the private key is located. All the resets can be signed there, and the SIG records thus produced can be conveyed back to the zone's primary server on CD-ROM. In this way, the private key can be stored on a CD-ROM locked in a safe, except when it is inserted into the disconnected machine for signing the day's new resets. After signing is completed, all copies of the key are erased from memory in the disk and the CD-ROM are returned to the safe. This procedure reduces electronic security to physical security, something people understand how to deal with. This method of presigning resets greatly speeds up the process of answering queries, since no cryptography has to be done on the fly. The trade-off is that a large amount of disk space is needed to store all the keys and signatures in the DNS databases. Some records will increase tenfold in size due to the signature. When a client process gets assigned reset, it must apply the originating zone's public key to decrypt the hash, compute the hash itself, and compare the two values. If they agree, the data are considered valid. However, this procedure begs the question of how the client gets the zone's public key. One way is to acquire it from a trusted server, using a secure connection, for instance, using IPsec. However, in practice, it is expected that clients will be pre-configured with the public keys of all the top-level domains. If Alice now wants to visit Bob's website, she can ask DNS for the reset of bob.com, which will contain his IP address and a key record containing Bob's public key. This reset will be signed by the top-level com domain, so Alice can easily verify its validity. An example of what this reset might contain is shown in figure 8248. Domain name time to live class type value bob.com 86436.1.2.3 bob.com 86400 and key 3,682,793 A7B73 F731,029 SA 2737D bob.com 86,400 and SIG 86,947,503 A8B 848 F5272 E 53,930C. Figure 8248. An example reset for bob.com. The key record is Bob's public key. The SIG record is the top-level com server's signed hash of the A and key records to verify their authenticity. Now armed with a verified copy of Bob's public key, Alice can ask Bob's DNS server, run by Bob, for the IP address of www.bob.com. This reset will be signed by Bob's private key, so Alice can verify the signature on the reset Bob returns. If Trudy somehow manages to inject a false reset into any of the caches, Alice can easily detect its lack of authenticity, because the SIG record contained in it will be incorrect. However, IPsec also provides a cryptographic mechanism to bind a response to a specific query to prevent the kind of spoof Trudy managed to pull off in figure 8247. This optional anti-spoofing measure adds to the response a hash of the query message signed with the respondent's private key. Since Trudy does not know the private key of the top-level com server, she cannot forge a response to a query Alice's ISP sent there. She can certainly get a response back first, but it will be rejected due to its invalid signature over the hashed query. IPsec also supports a few other record types. For example, the cert record can be used for storing, for instance, X509 certificates. This record has been provided because some people want to turn DNS into a PKI. Whether this will actually happen remains to be seen. We will stop our discussion of IPsec here. For more details, please consult RFC 25358.9.3 SSL. The secure sockets layer secure naming is a good start, but there is much more to web security. The next step is secure connections. We will now look at how secure connections can be achieved. Nothing involving security is simple, and this is not either. When the web burst into public view, it was initially used for just distributing static pages. However, before long, some companies got the idea of using it for financial transactions, such as purchasing merchandise by credit card, online banking, and electronic stock trading. These applications created a demand for secure connections. In 1995, Netscape Communications Corp., the then dominant browser vendor, responded by introducing a security package called SSL, Secure Sockets Layer, to meet this demand. This software and its protocol are now widely used, for example, by Firefox, Safari, and Internet Explorer, so it is worth examining in some detail. SSL builds a secure connection between two sockets, including 1. Parameter negotiation between client and server. 2. Authentication of the server by the client. 3. Secret communication. 4. Data integrity protection. We have seen these items before, so there is no need to elaborate on them. The positioning of SSL in the usual protocol stack is illustrated in Figure 8.249. Effectively, it is a new layer interposed between the application layer and the transport layer, accepting requests from the browser and sending them down to TCP for transmission to the server. Once the secure connection has been established, SSL's main job is handling compression and encryption. When HTTP is used over SSL, it is called HTTPS, Secure HTTP, even though it is a standard HTTP protocol. Sometimes it is available at a new port, 443, instead of port 80. As an aside, SSL is not restricted to web browsers, but that is its most common application. It can also provide mutual authentication. Application, HTTP, security, SSL, transport, TCP, network, IP, data link, PPP, physical, modem, ADSL, cable TV, Figure 8.249. Layers and protocols for a home user browsing with SSL. The SSL protocol has gone through several versions. Below we will discuss only version 3, which is the most widely used version. SSL supports a variety of different options. These options include the presence or absence of compression, the cryptographic algorithms to be used, and some matters relating to export restrictions on cryptography. The last is mainly intended to make sure that serious cryptography is used only when both ends of the connection are in the United States. In other cases, keys are limited to 40 bits, which cryptographers regard as something of a joke. Netscape was forced to put in this restriction in order to get an export license from the US government. SSL consists of two subprotocols, one for establishing a secure connection, and one for using it. Let us start out by seeing how secure connections are established. The connection establishment subprotocol is shown in Figure 8-50. It starts out with message 1 when Alice sends a request to Bob to establish a connection. The request specifies the SSL version Alice has and her preferences with respect to compression and cryptographic algorithms. It also contains a nonce wrap to be used later. Now it is Bob's turn. In message 2, Bob makes a choice among the various algorithms that Alice can support and sends his own nonce, RB. Then, in message 3, he sends a certificate containing his public key. If this certificate is not signed by some well-known authority, he also sends a chain of certificates that can be followed back to 1. All browsers, including Alice's, come preloaded with about 100 public keys, so if Bob can establish a chain anchored to one of these, Alice will be able to verify Bob's public key. At this point, Bob may send some other messages, such as a request for Alice's public key certificate. When Bob is done, he sends message 4 to tell Alice it is her turn. Alice responds by choosing a random 384-bit master key and sending it to Bob encrypted with his public key, message 5. The actual session key used for encrypting data is derived from the master key combined with both nonces in a complex way. After message 5 has been received, both Alice and Bob are able to compute the session key. For this reason, Alice tells Bob to switch to the SSL version, preferences, SSL version, choices, RBX509 certificate change server Duneb, master key, change cipher finished, change cipher finished 9, 7, 8 Alice Bob 6, 5, 4, 3, 2, 1 Figure 8-50. A simplified version of the SSL connection establishment subprotocol new cipher, message 6, and also that she is finished with the establishment subprotocol, message 7. Bob then acknowledges her, messages 8 and 9. However, although Alice knows who Bob is, Bob does not know who Alice is, unless Alice has a public key and a corresponding certificate for it, an unlikely situation for an individual. Therefore, Bob's first message may well be a request for Alice to log in using a previously established login name and password. The login protocol, however, is outside the scope of SSL. Once it has been accomplished, by whatever means, data transport can begin. As mentioned above, SSL supports multiple cryptographic algorithms. The strongest one uses triple Ds with 3 separate keys for encryption and SHA-1 for message integrity. This combination is relatively slow, so it is mostly used for banking and other applications in which the highest security is required. For ordinary e-commerce applications, RC4 is used with a 128-bit key for encryption and MD5 is used for message authentication. RC4 takes the 128-bit key as a seed and expands it to a much larger number for internal use. Then it uses this internal number to generate a key stream. The key stream is stored with the plain text to provide a classical stream cipher, as we saw in figure 8.2.14. The exports also use a C4 with 128-bit keys, but 88 of the bits are made public to make the cipher easy to break. For actual transport, a second subprotocol is used, as shown in figure 8.2.51. Messages from the browser are first broken into units of up to 16 KB. If data compression is enabled, each unit is then separately compressed. After that, a secret key derived from the 2 nonces and per master key is concatenated with the compressed text and the result is hashed with the agreed on hashing algorithm, usually MD5. This hash is appended to each fragment as the MAC. The compressed fragment plus MAC is then encrypted with the agreed on symmetric encryption algorithm, usually by XORing it with the RC4 key stream. Finally, a fragment header is attached, and the fragment is transmitted over the TCP connection. Message authentication code header added encryption MAC added compression fragmentation part 1 part 2 message from browser figure 8.2.51. Data transmission using SSL. A word of caution is in order, however. Since it has been shown that RC4 has some weak keys that can be easily cryptanalyzed, the security of SSL using RC4 is on shaky ground. Fleur and others, 2001. Browsers that allow the user to choose the cipher suite should be configured to use triple Ds with 168-bit keys and SHA-1 all the time, even though this combination is slower than RC4 and MD5. Or, better yet, users should upgrade to browsers that support the successor to SSL that we describe shortly. A problem with SSL is that the principals may not have certificates, and even if they do not always verify that the keys being used match them. In 1996, Netscape Communications Corp turned SSL over to IETF for standardization. The result was TLS, Transport Layer Security. It is described in RFC 5246. TLS was built on SSL version 3. The changes made to SSL were relatively small, but just enough that SSL version 3 and TLS cannot interoperate. For example, the way the session key is derived from the premaster key and nonces was changed to make the key stronger, that is, harder to cryptanalyze. Because of this incompatibility, most browsers implement both protocols, with TLS falling back to SSL during negotiation if necessary. This is referred to as SSL/TLS. The first TLS implementation appeared in 1999 with version 1.2 defined in August 2008. It includes support for stronger cipher suites, notably ease. SSL has remained strong in the marketplace, although TLS will probably gradually replace it. 8.9.4 Mobile code security naming and connections are 2 areas of concern related to web security. But there are more. In the early days, when web pages were just static HTML files, they did not contain executable code. Now they often contain small programs, including Java applets, ActiveX controls, and JavaScripts. Downloading and executing such mobile code is obviously a massive security risk, so various methods have been devised to minimize it. We will now take a quick peek at some of the issues raised by mobile code and some approaches to dealing with it. Java Applet Security. Java applets are small Java programs compiled to a stack-oriented machine language called JVM, Java Virtual Machine. They can be placed on a web page for downloading along with the page. After the page is loaded, the applets are inserted into a JVM interpreter inside the browser, as illustrated in Figure 8 to 52. Untrusted applet, trusted applet, web browser sandbox interpreter, virtual address space 0xFFFFFFFF0, Figure 8 to 52. Applets can be interpreted by a web browser. The advantage of running interpreted code over compiled code is that every instruction is examined by the interpreter before being executed. This gives the interpreter the opportunity to check whether the instruction's address is valid. In addition, system calls are also caught and interpreted. How these calls are handled is a matter of the security policy. For example, if an applet is trusted, for instance, it came from the local disk, its system calls could be carried out without question. However, if an applet is not trusted, for instance, it came in over the internet, it could be encapsulated in what is called a sandbox to restrict its behavior and trap its attempts to use system resources. When an applet tries to use a system resource, its call is passed to a security monitor for approval. The monitor examines the call in light of the local security policy and then makes a decision to allow or reject it. In this way, it is possible to give applets access to some resources but not all. Unfortunately, the reality is that the security model works badly and that bugs in it crop up all the time. ActiveX controls are x86 binary programs that can be embedded in web pages. When one of them is encountered, a check is made to see if it should be executed, and if passes the test, it is executed. It is not interpreted or sandboxed in any way, so it has as much power as any other user program, and can potentially do great harm. Thus, all the security is in the decision whether to run the ActiveX control. In retrospect, the whole idea is a gigantic security hole. The method that Microsoft chose for making this decision is based on the idea of code signing. Each ActiveX control is accompanied by a digital signature, a hash of the code that is signed by its creator using public key cryptography. When an ActiveX control shows up, the browser first verifies the signature to make sure it has not been tampered with in transit. If the signature is correct, the browser then checks its internal tables to see if the program's creator is trusted or there is a chain of trust back to a trusted creator. If the creator is trusted, the program is executed, otherwise, it is not. The Microsoft system for verifying ActiveX controls is called Authentification. It is useful to contrast the Java and ActiveX approaches. With the Java approach, no attempt is made to determine who wrote the applet. Instead, a runtime interpreter makes sure it does not do things the machine owner has said applets may not do. In contrast, with code signing, there is no attempt to monitor the mobile code's runtime behavior. If it came from a trusted source and has not been modified in transit, it just runs. No attempt is made to see whether the code is malicious or not. If the original programmer intended the code to format the hard disk and then erase the flash ROM so the computer can never again be booted, and if the programmer has been certified as trusted, the code will be run and destroy the computer unless ActiveX controls have been disabled in the browser. Many people feel that trusting an unknown software company is scary. To demonstrate the problem, a programmer in Seattle formed a software company and got it certified as trustworthy, which is easy to do. He then wrote an ActiveX control that did a clean shutdown of the machine and distributed his ActiveX control widely. It shut down many machines, but they could just be rebooted, so no harm was done. He was just trying to expose the problem to the world. The official response was to revoke the certificate for this specific ActiveX control, which ended a short episode of acute embarrassment, but the underlying problem is still there for an evil programmer to exploit. Garfinkel with Spafford, 2002. Since there is no way to police the thousands of software companies that might write mobile code, the technique of code signing is a disaster waiting to happen. JavaScript does not have any formal security model, but it does have a long history of leaky implementations. Each vendor handles security in a different way. For example, Netscape Navigator version 2 used something akin to the Java model, but by version 4 that had been abandoned for a code signing model. The fundamental problem is that letting foreign code run on your machine is asking for trouble. From a security standpoint, it is like inviting a burglar into your house and then trying to watch him carefully so he cannot escape from the kitchen into the living room. If something unexpected happens and you are distracted for a moment, bad things can happen. The tension here is that mobile code allows flashy graphics and fast interaction, and many website designers think that this is much more important than security, especially when it is somebody else's machine at risk. Browser extensions as well as extending web pages with code. There is a booming marketplace in browser extensions, add-ons, and plugins. They are computer programs that extend the functionality of web browsers. Plugins often provide the capability to interpret or display a certain type of content, such as PDFs or flash animations. Extensions and add-ons provide new browser features, such as better password management or ways to interact with pages by, for example, marking them up or enabling easy shopping for related items. Installing an extension, add-on, or plugin is as simple as coming across something you want when browsing and following the link to install the program. This action will cause code to be downloaded across the internet and installed into the browser. All of these programs are written to frameworks that differ depending on the browser that is being enhanced. However, to a first approximation, they become part of the trusted computing base of the browser. That is, if the code that is installed is buggy, the entire browser can be compromised. There are two other obvious failure modes as well. The first is that the program may behave maliciously, for example, by gathering personal information and sending it to a remote server. For all the browser knows, the user installed the extension for precisely this purpose. The second problem is that plugins give the browser the ability to interpret new types of content. Often this content is a full-blown programming language itself. PDF and Flash are good examples. When users view pages with PDF and Flash content, the plugins in their browser are executing the PDF and Flash code. That code had better be safe. Often there are vulnerabilities that it can exploit. For all of these reasons, add-ons and plugins should only be installed as needed and only from trusted vendors. Viruses are another form of mobile code. Only, unlike the examples above, viruses are not invited in at all. The difference between a virus and ordinary mobile code is that viruses are written to reproduce themselves. When a virus arrives, either via a web page, an ML attachment, or some other way, it usually starts out by infecting executable programs on the disk. When one of these programs is run, control is transferred to the virus, which usually tries to spread itself to other machines. For example, by emailing copies of itself to everyone in the victim's email address book. Some viruses infect the boot sector of the hard disk, so when the machine is booted, the virus gets to run. Viruses have become a huge problem on the internet and have caused billions of dollars worth of damage. There is no obvious solution. Perhaps a whole new generation of operating systems, based on secure microkernels and tight compartmentalization of users, processes, and resources might help. 8.10 Social issues. The internet and its security technology is an area where social issues, public policy, and technology meet head-on, often with huge consequences. Below we will just briefly examine three areas: privacy, freedom of speech, and copyright. Needless to say, we can only scratch the surface. For additional reading, see Anderson, 2008a, Garfinkel with Spafford, 2002, and Skneyer, 2004. The internet is also full of material. Just type words such as privacy, censorship, and copyright into any search engine. Also, see this book's website for some links. It is at http://www.personhired.com/Tanenbaum. 8.10.1 Privacy. Do people have a right to privacy? Good question. The Fourth Amendment to the US Constitution prohibits the government from searching people's houses, papers, and effects without good reason, and goes on to restrict the circumstances under which search warrants shall be issued. Thus, privacy has been on the public agenda for over 200 years, at least in the US. What has changed in the past decade is both the ease with which governments can spy on their citizens and the ease with which the citizens can prevent such spying. In the 18th century, for the government to search a citizen's papers, it had to send out a policeman on a horse to go to the citizen's farm demanding to see certain documents. It was a cumbersome procedure. Nowadays, telephone companies and internet providers readily provide wiretaps when presented with search warrants. It makes life much easier for the policeman and there is no danger of falling off a horse. Cryptography changes all that. Anybody who goes to the trouble of downloading and installing PGP, and who uses a well-guarded alien strength key can be fairly sure that nobody in the known universe can read his email, search warrant or no search warrant. Governments well understand this, and do not like it. Real privacy means it is much harder for them to spy on criminals of all stripes, but it is also much harder to spy on journalists and political opponents. Consequently, some governments restrict or forbid the use or export of cryptography. In France, for example, prior to 1999, all cryptography was banned, unless the government was given the keys. France was not alone. In April 1993, the US government announced its intention to make a hardware cryptoprocessor, the Clipper chip, the standard for all networked communication. It was said that this would guarantee citizens' privacy. It also mentioned that the chip provided the government with the ability to decrypt all traffic via a scheme called key escrow, which allowed the government access to all the keys. However, the government promised only to snoop when it had a valid search warrant. Needless to say, a huge furor ensued, with privacy advocates denouncing the whole plan and law enforcement officials praising it. Eventually, the government backed down and dropped the idea. A large amount of information about electronic privacy is available at the Electronic Frontier Foundation's website, www.f.org. Anonymous remailers PGP, SSL, and other technologies make it possible for two parties to establish secure, authenticated communication, free from third-party surveillance and interference. However, sometimes privacy is best served by not having authentication, in fact, by making communication anonymous. The anonymity may be desired for point-to-point messages, news graphs, or both. Let us consider some examples. First, political dissidents living under authoritarian regimes often wish to communicate anonymously to escape being jailed or killed. Second, wrongdoing in many corporate, educational, governmental, and other organizations has often been exposed by whistleblowers, who frequently prefer to remain anonymous to avoid retribution. Third, people with unpopular social, political, or religious views may wish to communicate with each other via email or newsgraphs without exposing themselves. Fourth, people may wish to discuss alcoholism, mental illness, sexual harassment, child abuse, or being a member of a persecuted minority in a newsgroup without having to go public. Numerous other examples exist, of course. Let us consider a specific example. In the 1990s, some critics of a non-traditional religious group posted their views to a Usenet newsgroup via an anonymous remailer. This server allowed users to create pseudonyms and send email to the server, which then remailed or reposted them using the pseudonyms, so no one could tell where the messages really came from. Some postings revealed what the religious group claimed were trade secrets and copyrighted documents. The religious group responded by telling local authorities that its trade secrets had been disclosed and its copyright infringed, both of which were crimes, where the server was located. A court case followed, and the server operator was compelled to turn over the mapping information that revealed the true identities of the persons who had made the postings. Incidentally, this was not the first time that a religious group was unhappy when someone leaked its trade secrets. William Tyndale was burned at the stake in 1536 for translating the Bible into English. A substantial segment of the internet community was completely outraged by this breach of confidentiality. The conclusion that everyone drew is that an anonymous remailer that stores a mapping between real email addresses and pseudonyms, now called a type 1 remailer, is not worth much. This case stimulated various people into designing anonymous remailers that could withstand subpoena attacks. These new remailers, often called cypherpunk remailers, work as follows. The user produces an email message, complete with RFC 822 headers, except from, of course, encrypts it with the remailer's public key, and sends it to the remailer. There the outer RFC 822 headers are stripped off, the content is decrypted and the message is remailed. The remailer has no accounts, and maintains no logs, so even if the server is later confiscated, it retains no trace of messages that have passed through it. Many users who wish anonymity chain their requests through multiple anonymous remailers, as shown in figure 8 to 53. Here, Alice wants to send Bob a really anonymous Valentine's Day card, so she uses 3 remailers. She composes the message, M, and puts a header on it containing Bob's email address. Then she encrypts the whole thing with remailer 3's public key, E3, indicated by horizontal hatching. To this she prepends a header with remailer 3's email address in plain text. This is the message shown between remailers 2 and 3 in the figure. Then she encrypts this message with remailer 2's public key, E2, indicated by vertical hatching, and prepends a plain text header containing remailer 2's email address. This message is shown between 1 and 2 in figure 8 to 53. Finally, she encrypts the entire message with remailer 1's public key, E1, and prepends a plain text header with remailer 1's email address. This is the message shown to the right of Alice in the figure, and this is the message she actually transmits. Alice 1 Bob to 1, 2, 3 to 2 anonymous remailer encrypted with E1 encrypted with E2 encrypted with E3 to Bob to 3 meters, to Bob M to 3 to Bob M to 3 to 2 to Bob M figure 8 to 53. How Alice uses 3 remailers to send Bob a message. When the message hits remailer 1, the outer header is stripped off. The body is decrypted and then emailed to remailer 2. Similar steps occur at the other 2 remailers. Although it is extremely difficult for anyone to trace the final message back to Alice, many remailers take additional safety precautions. For example, they may hold messages for a random time, add or remove junk at the end of a message, and reorder messages, or to make it harder for anyone to tell which message output by a remailer corresponds to which input, in order to thwart traffic analysis. For a description of this kind of remailer, see Mazy _Reason Kashok, 1998. Anonymity is not restricted to email. Services also exist that allow anonymous web surfing using the same form of layered path in which one node only knows the next node in the chain. This method is called onion routing because each node peels off another layer of the onion to determine where to forward the packet next. The user configures his browser to use the anonymizer service as a proxy. Tor is a well-known example of such a system, Dingladine and others, 2004. Henceforth, all HTTP requests go through the anonymizer network, which requests the page and sends it back. The website sees an exit node of the anonymizer network as the source of the request, not the user. As long as the anonymizer network refrains from keeping a log, after the fact no one can determine who requested which page. Privacy relates to individuals wanting to restrict what other people can see about them. A second key social issue is freedom of speech, and its opposite, censorship, which is about governments wanting to restrict what individuals can read and publish. With the web containing millions and millions of pages, it has become a census paradise. Depending on the nature and ideology of the regime, banned material may include websites containing any of the following. 864 Network Security Chapter 8 1. Material inappropriate for children or teenagers. 2. Hate aimed at various ethnic, religious, sexual or other groups. 3. Information about democracy and democratic values. 4. Accounts of historical events contradicting the government's version. 5. Manuals for picking locks, building weapons, encrypting messages, etc. The usual response is to ban the bad sites. Sometimes the results are unexpected. For example, some public libraries have installed web filters on their computers to make them child-friendly by blocking pornography sites. The filters veto sites on their blacklists, but also check pages for dirty words before displaying them. In one case in Loudoun County, Virginia, the filter blocked a patron's search for information on breast cancer because the filter saw the word breast. The library patron sued Loudoun County. However, in Livermore, California, a parent sued the public library for not installing a filter after her 12-year-old son was caught viewing pornography there. What's a library to do? It has escaped many people that the World Wide Web is a World Wide Web. It covers the whole world. Not all countries agree on what should be allowed on the web. For example, in November 2000, a French court ordered Yahoo, a California corporation, to block French users from viewing auctions of Nazi memorabilia on Yahoo's website because owning such material violates French law. Yahoo appealed to a US court, which sided with it, but the issue of whose laws apply where is far from settled. Just imagine what would happen if some court in Utah instructed France to block websites dealing with wine because they do not comply with Utah's much stricter laws about alcohol. Suppose that China demanded that all websites dealing with democracy be banned as not in the interest of the state. Do Iranian laws on religion apply to more liberal Sweden? Can Saudi Arabia block websites dealing with women's rights? The whole issue is a veritable Pandora's box. A relevant comment from John Gilmore is, the net interprets censorship as damage and roots around it. For a concrete implementation, consider the Eternity Service, Anderson, 1996. Its goal is to make sure published information cannot be depublished or rewritten, as was common in the Soviet Union during Joseph Stalin's reign. To use the Eternity Service, the user specifies how long the material is to be preserved, pays a fee proportional to its duration and size, and uploads it. Thereafter, no one can remove or edit it, not even the uploader. How could such a service be implemented? The simplest model is to use a peer-to-peer system in which stored documents would be placed on dozens of participating servers, each of which gets a fraction of the fee, and thus an incentive to join the system. The servers should be spread over many legal jurisdictions for maximum resilience. Lists of 10 randomly selected servers would be stored securely in multiple places, so that if some were compromised, others would still exist. An authority bent on destroying the document could never be sure it had found all copies. The system could also be made self-repairing in the sense that, if it became known that some copies had been destroyed, the remaining sites would attempt to find new repositories to replace them. The Eternity Service was the first proposal for a censorship-resistant system. Since then, others have been proposed and, in some cases, implemented. Various new features have been added, such as encryption, anonymity, and fault tolerance. Often the files to be stored are broken up into multiple fragments, with each fragment stored on many servers. Some of these systems are Freenet, Clark and others, 2002, Passis, Wally and others, 2000, and Publius, Waldman and others, 2000. Other work is reported by Sargentov, 2002. Increasingly, many countries are trying to regulate the export of intangibles, which often include websites, software, scientific papers, email, telephone help desks, and more. Even the UK, which has a centuries-long tradition of freedom of speech, is now seriously considering highly restrictive laws that would, for example, define technical discussions between a British professor and his foreign PhD student, both located at the University of Cambridge, as regulated export needing a government license. Anderson, 2002. Needless to say, many people consider such a policy to be outrageous. Steganography in countries where censorship abounds, dissidents often try to use technology to evade it. Cryptography allows secret messages to be sent, although possibly not lawfully, but if the government thinks that Alice is a bad person, the mere fact that she is communicating with Bob may get him put in this category too, as repressive governments understand the concept of transitive closure, even if they are short on mathematicians. anonymous remailers can help, but if they are banned domestically and messages to foreign ones require a government export license, they cannot help much. But the web can. People who want to communicate secretly often try to hide the fact that any communication at all is taking place. The science of hiding messages is called steganography, from the Greek words for covered writing. In fact, the ancient Greeks used it themselves. Herodotus wrote of a general who shaved the head of a messenger, tattooed a message on his scalp, and let the hair grow back before sending him off. Modern techniques are conceptually the same, only they have a higher bandwidth, lower latency, and do not require the services of a barber. As a case in point, consider figure 8 to 54. This photograph, taken by one of the authors, Ast, in Kenya, contains 3 zebras contemplating an acacia tree. Figure 8 to 54, B, appears to be the same 3 zebras and acacia tree, but it has an extra added attraction. It contains the complete, unabridged text of 5 of Shakespeare's plays embedded in it: Hamlet, King Lear, Macbeth, The Merchant of Venice, and Julius Caesar. Together, these plays total over 700 KB of text. B, figure 8 to 54. 3 zebras and a tree. B, 3 zebras, a tree, and the complete text of 5 plays by William Shakespeare. How does this steganographic channel work? The original color image is 1024 x 768 pixels. Each pixel consists of 3 8-bit numbers, one each for the red, green, and blue intensity of that pixel. The pixel's color is formed by the linear superposition of the 3 colors. The steganographic encoding method uses the low order bit of each RGB color value as a covert channel. Thus, each pixel has room for 3 bits of secret information, one in the red value, one in the green value, and one in the blue value. With an image of this size, up to 1024 x 768 x 3 bits or 294,912 bytes of secret information can be stored in it. The full text of the 5 plays and a short notice add up to 734,891 bytes. This text was first compressed to about 274 KB using a standard compression algorithm. The compressed output was then encrypted using IDEA and inserted into the low order bits of each color value. As can be seen, or actually, cannot be seen, the existence of the information is completely invisible. It is equally invisible in the large full color version of the photo. The eye cannot easily distinguish 21-bit color from 24-bit color. Viewing the 2 images in black and white with low resolution does not do justice to how powerful the technique is. To get a better feel for how steganography works, we have prepared a demonstration, including the full color high resolution image of figure 8 to 54, B, with the 5 plays embedded in it. The demonstration, including tools for inserting and extracting text into images, can be found at the book's website. To use steganography for undetected communication, dissidents could create a website bursting with politically correct pictures, such as photographs of the great leader, local sports, movie, and television stars, etc. Of course, the pictures would be riddled with steganographic messages. If the messages were first compressed and then encrypted, even someone who suspected their presence would have immense difficulty in distinguishing the messages from white noise. Of course, the images should be fresh scans. Copying a picture from the internet and changing some of the bits is a dead giveaway. Images are by no means the only carrier for steganographic messages. Audio files also work fine. Hidden information can be carried in a voice over IP call by manipulating the packet delays, distorting the audio, or even in the header fields of packets, loopbacks and others. 2010. Even the layout and ordering of tags in an HTML file can carry information. Although we have examined steganography in the context of free speech, it has numerous other uses. One common use is for the owners of images to encode secret messages in them stating their ownership rights. If such an image is stolen and placed on a website, the lawful owner can reveal the steganographic message in court to prove whose image it is. This technique is called watermarking. It is discussed in Piver and others, 2002. For more on steganography, see Weiner, 2008, 8.10.3 Copyright privacy and censorship are just two areas where technology meets public policy. A third one is the copyright law. Copyright is granting to the creators of IP, intellectual property, including writers, poets, artists, composers, musicians, photographers, cinematographers, choreographers, and others, the exclusive right to exploit their IP for some period of time, typically the life of the author plus 50 years or 75 years in the case of corporate ownership. After the copyright of a work expires, it passes into the public domain and anyone can use or sell it as they wish. The Gutenberg Project, www.promo.net/pg, for example, has placed thousands of public domain works, for instance, by Shakespeare, Twain, and Dickens, on the web. In 1998, the US Congress extended copyright in the US by another 20 years at the request of Hollywood, which claimed that without an extension nobody would create anything anymore. By way of contrast, patents last for only 20 years and people still invent things. Copyright came to the forefront when Napster, a music swapping service, had 50 million members. Although Napster did not actually copy any music, the courts held that its holding a central database of who had which song was contributory infringement, that is, it was helping other people infringe. While nobody seriously claims copyright is a bad idea, although many claim that the term is far too long, favoring big corporations over the public, the next generation of music sharing is already raising major ethical issues. For example, consider a peer-to-peer network in which people share legal files, public domain music, home videos, religious tracts that are not trade secrets, etc., and perhaps a few that are copyrighted. Assume that everyone is online all the time via ADSL or cable. Each machine has an index of what is on the hard disk, plus a list of other members. Someone looking for a specific item can pick a random member and see if he has it. If not, he can check out all the members in that person's list, and all the members in their lists, and so on. Computers are very good at this kind of work. Having found the item, the requester just copies it. If the work is copyrighted, chances are the requester is infringing. Although for international transfers, the question of whose law applies matters, because in some countries uploading is illegal, but downloading is not. But what about the supplier? Is it a crime to keep music you have paid for and legally downloaded on your hard disk where others might find it? If you have an unlocked cabin in the country and an IP thief sneaks in carrying a notebook computer and scanner, scans a copyrighted book to the notebook's hard disk, and sneaks out, are you guilty of the crime of failing to protect someone else's copyright? But there is more trouble brewing on the copyright front. There is a huge battle going on now between Hollywood and the computer industry. The former wants stringent protection of all intellectual property, but the latter does not want to be Hollywood's policeman. In October 1998, Congress passed the DMCA, Digital Millennium Copyright Act, which makes it a crime to circumvent any protection mechanism present in a copyrighted work or to tell others how to circumvent it. Similar legislation has been enacted in the European Union. While virtually no one thinks that pirates in the Far East should be allowed to duplicate copyrighted works, many people think that the DMCA completely shifts the balance between the copyright owner's interest and the public interest. A case in point, in September 2000, a music industry consortium charged with building an unbreakable system for selling music online sponsored a contest inviting people to try to break the system, which is precisely the right thing to do with any new security system. A team of security researchers from several universities, led by Professor Edward Felton of Princeton, took up the challenge and broke the system. They then wrote a paper about their findings and submitted it to a Usenix security conference, where it underwent peer review and was accepted. Before the paper was to be presented, Felton received a letter from the Recording Industry Association of America that threatened to sue the authors under the DMCA if they published the paper. Their response was to file a lawsuit asking a federal court to rule on whether publishing scientific papers on security research was still legal. Fearing a definitive court ruling against it, the industry withdrew its threat and the court dismissed Felton's suit. No doubt the industry was motivated by the weakness of its case. It had invited people to try to break its system and then threatened to sue some of them for accepting its own challenge. With the threat withdrawn, the paper was published. Craver and others, 2001. A new confrontation is virtually certain. Meanwhile, pirated music and movies have fueled the massive growth of peer-to-peer networks. This has not pleased the copyright holders, who have used the DMCA to take action. There are now automated systems that search peer-to-peer networks and then fire off warnings to network operators and users who are suspected of infringing copyright. In the United States, these warnings are known as DMCA takedown notices. This search is an arms race because it is hard to reliably catch copyright infringers. Even your printer might be mistaken for a culprit. Biotech and others, 2008. A related issue is the extent of the fair use doctrine, which has been established by court rulings in various countries. This doctrine says that purchasers of a copyrighted work have certain limited rights to copy the work, including the right to quote parts of it for scientific purposes, use it as teaching material in schools or colleges, and in some cases, make backup copies for personal use in case the original medium fails. The tests for what constitutes fair use include 1. Whether the use is commercial, 2. What percentage of the whole is being copied, and 3. The effect of the copying on sales of the work. Since the DMCA and similar laws within the European Union prohibit circumvention of copy protection schemes, these laws also prohibit legal fair use. In effect, the DMCA takes away historical rights from users to give content sellers more power. A major showdown is inevitable. Another development in the works that dwarfs even the DMCA in its shifting of the balance between copyright owners and users is trusted computing as advocated by industry bodies such as the TCG, Trusted Computing Group, led by companies like Intel and Microsoft. The idea is to provide support for carefully monitoring user behavior in various ways, for instance, playing pirated music at a level below the operating system in order to prohibit unwanted behavior. This is accomplished with a small chip called a TPM, Trusted Platform Module, which it is difficult to tamper with. Most PCs sold nowadays come equipped with a TPM. The system allows software written by content owners to manipulate PCs in ways that users cannot change. This raises the question of who is trusted in trusted computing. Certainly, it is not the user. Needless to say, the social consequences of this scheme are immense. It is nice that the industry is finally paying attention to security, but it is lamentable that the driver is enforcing copyright law rather than dealing with viruses, crackers, intruders, and other security issues that most people are concerned about. In short, the lawmakers and lawyers will be busy balancing the economic interests of copyright owners with the public interest for years to come. Cyberspace is no different from meat space. It constantly pits one group against another, resulting in power struggles, litigation, and, hopefully, eventually some kind of resolution, at least until some new disruptive technology comes along. 8.11 Summary: Cryptography is a tool that can be used to keep information confidential and to ensure its integrity and authenticity. All modern cryptographic systems are based on Kirchhoff's principle of having a publicly known algorithm and a secret key. Many cryptographic algorithms use complex transformations involving substitutions and permutations to transform the plain text into the ciphertext. However, if quantum cryptography can be made practical, the use of one-time pads may provide truly unbreakable cryptosystems. Cryptographic algorithms can be divided into symmetric-key algorithms and public-key algorithms. Symmetric-key algorithms mangle the bits in a series of rounds parameterized by the key to turn the plain text into the ciphertext. Ease, Ridge and Deal, and Triple Ds are the most popular symmetric-key algorithms at present. These algorithms can be used in electronic codebook mode, cipher blockchaining mode, stream cipher mode, counter mode, and others. Public key algorithms have the property that different keys are used for encryption and decryption, and that the decryption key cannot be derived from the encryption key. These properties make it possible to publish the public key. The main public key algorithm is RSA, which derives its strength from the fact that it is very difficult to factor large numbers. Legal, commercial, and other documents need to be signed. Accordingly, various schemes have been devised for digital signatures, using both symmetric key and public key algorithms. Commonly, messages to be signed are hashed using algorithms such as SHA-1, and then the hash is assigned, rather than the original messages. Public key management can be done using certificates, which are documents that bind a principal to a public key. Certificates are signed by a trusted authority or by someone, recursively, approved by a trusted authority. The root of the chain has to be obtained in advance, but browsers generally have many root certificates built into them. These cryptographic tools can be used to secure network traffic. IPsec operates in the network layer, encrypting packet flows from host to host. Firewalls can screen traffic going into or out of an organization, often based on the protocol and port used. Virtual private networks can simulate an old leased line network to provide certain desirable security properties. Finally, wireless networks need good security, lest everyone read all the messages, and protocols like 802.11i provide it. When two parties establish a session, they have to authenticate each other and, if need be, establish a shared session key. Various authentication protocols exist, including some that use a trusted third party, Diffie-Hellman, Kerberos, and public key cryptography. ML security can be achieved by a combination of the techniques we have studied in this chapter. PGP, for example, compresses messages, then encrypts them with a secret key, and sends the secret key encrypted with the receiver's public key. In addition, it also hashes the message, and sends the signed hash to verify message integrity. Web security is also an important topic, starting with secure naming. DNSSEC provides a way to prevent DNS spoofing. Most e-commerce websites use SSL/TLS to establish secure, authenticated sessions between the client and server. Various techniques are used to deal with mobile code, especially sandboxing and code signing. The internet raises many issues in which technology interacts strongly with public policy. Some of the areas include privacy, freedom of speech, and copyright. Problems 1. Break the following monoalphabetic substitution cipher. The plain text, consisting of letters only, is an excerpt from a poem by Lewis Carroll Mvyibekniksen of Jisnejrinvkin Mvjniden Vjurien Fefavi Pyrorovd Pndquri JHRNQVDT Edzbijan Vyuem Bruntrib Jurjrhendq Jurjik Jurina INQLNDPR Jub Ben HRMNVJVDT Edjurayavd Team Vyibek Pezarndq of Jurqndpr Vyibek, Mejbek, Vyibek, Mejbek, Vyibek Wev Jurqndpr Vyibek, Mejbek, Vyibek, Mejbek, Mejbek Wev Jurqndpr2. An affine cipher is a version of monoalphabetic substitution cipher, in which the letters of an alphabet of size m are first mapped to the integers in the range 0 to m1. Subsequently, the integer representing each plain text letter is transformed to an integer representing the corresponding ciphertext letter. The encryption function for a single letter is x equals x plus b mod m, where m is the size of the alphabet and a and b are the key of the cipher, and are co-prime. Trudy finds out that Bob generated a ciphertext using an affine cipher. She gets a copy of the ciphertext and finds out that the most frequent letter of the ciphertext is R, and the second most frequent letter of the ciphertext is K. Show how Trudy can break the code and retrieve the plain text 3. Break the following column transposition cipher. The plain text is taken from a popular computer textbook, so computer is a probable word. The plain text consists entirely of letters, no spaces. The ciphertext is broken up into blocks of 5 characters for readability and Valrera and many epbetastisat and mi go gorchsrasoknti meharuf pagsivt psital balarotogs 4. Alice used a transposition cipher to encrypt her messages to Bob. For added security, she encrypted the transposition cipher key using a substitution cipher, and kept the encrypted cipher in her computer. Trudy managed to get hold of the encrypted transposition cipher key. Can Trudy decipher Alice's messages to Bob? Why or why not? 5. Find a 77-bit one-time pad that generates the text hello world from the ciphertext of figure 824. 6. You are a spy and, conveniently, have a library with an infinite number of books at your disposal. Your operator also has such a library at his disposal. You have agreed to use Lord of the Rings as a one-time pad. Explain how you could use these assets to generate an infinitely long one-time pad. 7. Quantum cryptography requires having a photon gun that can, on demand, fire a single photon carrying 1 bit. In this problem, calculate how many photons a bit carries on a 250 Gbps fiber link. Assume that the length of a photon is equal to its wavelength, which for purposes of this problem is 1 micron. The speed of light in fiber is 20 cm/sec8. If Trudy captures and regenerates photons when quantum cryptography is in use, she will get some of them wrong and cause errors to appear in Bob's one-time pad. What fraction of Bob's one-time pad bits will be in error, on average? 9. A fundamental cryptographic principle states that all messages must have redundancy. But we also know that redundancy helps an intruder tell if a guessed key is correct. Consider 2 forms of redundancy. First, the initial n bits of the plain text contain a known pattern. Second, the final n bits of the message contain a hash over the message. From a security point of view, are these 2 equivalent? Discuss your answer. 10. In figure 8-6, the P boxes and S boxes alternate. Although this arrangement is aesthetically pleasing, is it any more secure than first having all the P boxes and then all the S boxes? Discuss your answer. 11. Design an attack on these, based on the knowledge that the plain text consists exclusively of uppercase ASCII letters, plus space, comma, period, semicolon, carriage return, and line feed. Nothing is known about the plain text parity bits. 12. In the text, we computed that a cipher-breaking machine with 1,000,000 processors that could analyze a key in 1 nanosecond would take 1016 years to break the 128-bit version of ease. Let us compute how long it will take for this time to get down to 1 year, still a long time, of course. To achieve this goal, we need computers to be 1016 times faster. If Moore's law, computing power doubles every 18 months, continues to hold, how many years will it take before a parallel computer can get the cipher breaking time down to a year? 13. E supports a 256-bit key. How many keys does E's 256 have? See if you can find some number in physics, chemistry, or astronomy of about the same size. Use the internet to help search for big numbers. Draw a conclusion from your research. 14. Suppose that a message has been encrypted using D's encounter mode. 1 bit of ciphertext in block CI is accidentally transformed from a 0 to a 1 during transmission. How much plain text will be garbled as a result? 15. Now consider ciphertext blockchaining again. Instead of a single 0 bit being transformed into a 1 bit, an extra 0 bit is inserted into the ciphertext stream after block CI. How much plain text will be garbled as a result? 16. Compare cipher blockchaining with cipher feedback mode in terms of the number of encryption operations needed to transmit a large file. Which one is more efficient, and by how much? 17. Using the RSA public key crypto system, with R equals 1, B equals 2, Y equals 25, Z equals 26, if P equals 5 and Q equals 13, list 5 legal values for D, B, if P equals 5, Q equals 31, and D equals 37, find D, C, using P equals 3, Q equals 11, and D equals 9, find D and encrypt hello 18. Alice and Bob use RSA public key encryption in order to communicate between them. Trudy finds out that Alice and Bob shared one of the primes used to determine the number n of their public key pairs. In other words, Trudy found out that NA equals par xq and NB equals pbxq. How can Trudy use this information to break Alice's code? 19. Consider the use of counter mode, as shown in figure 8 to 15, but with fourth equals 0. Does the use of 0 threaten the security of the cipher in general? 20. In figure 8 to 20, we see how Alice can send Bob a signed message. If Trudy replaces P, Bob can detect it. But what happens if Trudy replaces both P and the signature? 21. Digital signatures have a potential weakness due to lazy users. In e-commerce transactions, a contract might be drawn up, and the user asked to sign its SHA-1 hash. If the user does not actually verify that the contract and hash correspond, the user may inadvertently sign a different contract. Suppose that the Mafia try to exploit this weakness to make some money. They set up a pay website, for instance, pornography, gambling, etc., and ask new customers for a credit card number. Then they send over a contract saying that the customer wishes to use their service and pay by credit card, and ask the customer to sign it, knowing that most of them will just sign without verifying that the contract and hash agree. Show how the Mafia can buy diamonds from a legitimate internet jeweler and charge them to unsuspecting customers. 22. A math class has 25 students. Assuming that all of the students were born in the first half of the year between January 1st and June 30th, what is the probability that at least 2 students have the same birthday? Assume that nobody was born on leap day, so there are 181 possible birthdays. 23. After Ellen confessed to Marilyn about tricking her in the matter of Tom's tenure, Marilyn resolved to avoid this problem by dictating the contents of future messages into a dictating machine and having her new secretary just type them in. Marilyn then planned to examine the messages on her terminal after they had been typed in to make sure they contained her exact words. Can the new secretary still use the birthday attack to falsify a message, and if so, how? Hint, she can. 24. Consider the failed attempt of Alice to get Bob's public key in figure 8 to 23. Suppose that Bob and Alice already share a secret key, but Alice still wants Bob's public key. Is there now a way to get it securely? If so, how? 25. Alice wants to communicate with Bob using public key cryptography. She establishes a connection to someone she hopes is Bob. She asks him for his public key, and he sends it to her in plain text along with an X509 certificate signed by the root CA. Alice already has the public key of the root CA. What steps does Alice carry out to verify that she is talking to Bob? Assume that Bob does not care who he is talking to. For instance, Bob is some kind of public service. 26. Suppose that a system uses PKI based on a tree-structured hierarchy of CAs. Alice wants to communicate with Bob and receives a certificate from Bob, signed by a CAX, after establishing a communication channel with Bob. Suppose Alice has never heard of X. What steps does Alice take to verify that she is talking to Bob? 27. Can IPsec using R be used in transport mode if one of the machines is behind an ad box? Explain your answer. 28. Alice wants to send a message to Bob using SHA-1 hashes. She consults with you regarding the appropriate signature algorithm to be used. What would you suggest? 29. Give one reason why a firewall might be configured to inspect incoming traffic. Give one reason why it might be configured to inspect outgoing traffic. Do you think the inspections are likely to be successful? 30. Suppose an organization uses VPN to securely connect its sites over the internet. Jim, a user in the organization, uses the VPN to communicate with his boss, Mary. Describe one type of communication between Jim and Mary which would not require use of encryption or other security mechanism, and another type of communication which would require encryption or other security mechanisms. Explain your answer. 31. Change one message in the protocol of figure 8 to 34 in a minor way to make it resistant to the reflection attack. Explain why your change works. 32. The Diffie-Hellman key exchange is being used to establish a secret key between Alice and Bob. Alice sends Bob 227, 5, 82. Bob responds with 125. Alice's secret number, X, is 12, and Bob's secret number, Y, is 3. Show how Alice and Bob compute the secret key 33. Two users can establish a shared secret key using the Diffie-Hellman algorithm, even if they have never met, share no secrets, and have no certificates. Explain how this algorithm is susceptible to a man-in-the-middle attack. B. How would this susceptibility change if N or G were secret? 34. In the protocol of figure 8 239, Y is A sent in plain text along with the encrypted session key. 35. In the Needham-Schroeder protocol, Alice generates 2 challenges, Ra and Ra2. This seems like overkill. Would one not have done the job? 36. Suppose an organization uses Kerberos for authentication. In terms of security and service availability, what is the effect if a ZORTGS goes down? 37. Alice is using the public key authentication protocol of figure 8 to 43 to authenticate communication with Bob. However, when sending message 7, Alice forgot to encrypt RB. Trudy now knows the value of RB. Do Alice and Bob need to repeat the authentication procedure with new parameters in order to ensure secure communication? Explain your answer. 38. In the public key authentication protocol of figure 8 to 43, in message 7, RB is encrypted with KS. Is this encryption necessary, or would it have been adequate to send it back in plain text? Explain your answer. 39. Point of sale terminals that use magnetic stripe cards and PIN codes have a fatal flaw. A malicious merchant can modify his card reader to log all the information on the card and the PIN code in order to post additional, fake, transactions in the future. Next generation terminals will use cards with a complete CPU, keyboard, and tiny display on the card. Devise a protocol for this system that malicious merchants cannot break. 40. Is it possible to multicast a PGP message? What restrictions would apply? 41. Assuming that everyone on the internet used PGP, could a PGP message be sent to an arbitrary internet address and be decoded correctly by all concerned? Discuss your answer. 42. The attack shown in figure 8 to 47 leaves out one step. The step is not needed for the spoof to work, but including it might reduce potential suspicion after the fact. What is the missing step? 43. The SSL data transport protocol involves 2 nonces as well as a premaster key. What value, if any, does using the nonces have? 44. Consider an image of 2048 x 512 pixels. You want to encrypt a file size 2.5 megabytes. What fraction of the file can you encrypt in this image? What fraction would you be able to encrypt if you compressed the file to a quarter of its original size? Show your calculations. 45. The image of figure 8 to 54, B, contains the ASCII text of 5 plays by Shakespeare. Would it be possible to hide music among the zebras instead of text? If so, how would it work, and how much could you hide in this picture? If not, why not? 46. You are given a text file of size 60 megabytes, which is to be encrypted using steganography and the low order bits of each color in an image file. What size image would be required in order to encrypt the entire file? What size would be needed if the file were first compressed to a third of its original size? Give your answer in pixels and show your calculations. Assume that the images have an aspect ratio of 3:2, for example, 3000 x 2000 pixels. 47. Alice was a heavy user of a type 1 anonymous remailer. She would post many messages to her favorite newsgroup, alt.fanclub.alice, and everyone would know they all came from Alice, because they all bore the same pseudonym. Assuming that the remailer worked correctly, Trudy could not impersonate Alice. After type 1 remailers were all shut down, Alice switched to a cypherpunk remailer and started a new thread in her newsgroup. Devise a way for her to prevent Trudy from posting new messages to the newsgroup, impersonating Alice. 48. Search the internet for an interesting case involving privacy and write a one-page report on it. 49. Search the internet for some court case involving copyright versus fair use and write a one-page report summarizing your findings. 50. Write a program that encrypts its input by XORing it with a key stream. Find or write as good a random number generator as you can to generate the key stream. The program should act as a filter, taking plain text on standard input and producing ciphertext on standard output, and vice versa. The program should take one parameter, the key that seeds the random number generator 51. Write a procedure that computes the SHA-1 hash of a block of data. The procedure should have two parameters, a pointer to the input buffer and a pointer to a 20-byte output buffer. To see the exact specification of SHA-1, search the internet for FIPS 180-1, which is the full specification 52. Write a function that accepts a stream of ASCII characters and encrypts this input using a substitution cipher with the cipher blockchaining mode. The block size should be 8 bytes. The program should take plain text from the standard input and print the ciphertext on the standard output. For this problem, you are allowed to select any reasonable system to determine that the end of the input is reached, and or when padding should be applied to complete the block. You may select any output format as long as it is unambiguous. The program should receive two parameters. 1. A pointer to the initializing vector, and 2. A number, k, representing the substitution cipher shift, such that each ASCII character would be encrypted by the kth character ahead of it in the alphabet. For example, if x equals 3, then A is encoded by D, B is encoded by E, etc. Make reasonable assumptions with respect to reaching the last character in the ASCII set. Make sure to document clearly in your code any assumptions you make about the input and encryption algorithm 53. The purpose of this problem is to give you a better understanding as to the mechanisms of RSA. Write a function that receives as its parameters primes P and Q, calculates public and private RSA keys using these parameters, and outputs N, Z, D, and E as printouts to the standard output. The function should also accept a stream of ASCII characters and encrypt this input using the calculated RSA keys. The program should take plain text from the standard input and print the ciphertext to the standard output. The encryption should be carried out character-wise, that is, take each character in the input and encrypt it independently of other characters in the input. For this problem, you are allowed to select any reasonable system to determine that the end of the input is reached. You may select any output format as long as it is unambiguous. Make sure to document clearly in your code any assumptions you make about the input and encryption algorithm.